Hello? Okay.
Good. Hello?
Yes, it works.
Good morning, everyone. Thank you for joining us this morning. My name is Kerry Kors-Nicholson. I'm from the NASA Jet Propulsion Laboratory working on EcoStress at SPG, and I'm pleased to be co-chairing this session with Philippe.
Good morning, everyone. I'm Philippe Maison-Grande. I'm the Trishna Program Manager. And we are both very, very glad to welcome you during this second day. We're going to begin very, very quickly with, right now, I mean, with Kanishka Malik. I don't know if Kanishka is here. Hello. And Kanishka is a very teasing title. You're going to give a talk on a missing biophysical link in evapotranspiration modeling. So we are looking to hear what you're going to say about that. Thanks a lot. The floor is yours.
Thanks, Gary. Thanks, Philip. Good morning, everyone. This particular study heavily or mainly emphasized on the role of two most critical biophysical conductants that affects the LST and evaporation interaction and how their meaningful integration and some deeper level understanding can help us to advance the evaporation science from the future thermal mission with respect to evaporation monitoring and understanding the water cycle variability. The story starts back with late John Monteith, whose seminal work on evaporation and surface temperature was the first work on who postulated the theory of evaporation and surface temperature. So when we see this particular graph, so this shows two very contrasting behavior of evaporation with respect to surface temperature. And on one side, it shows that evaporation increases kind of exponentially with surface temperature and vapor pressure gradient under non-restricted water condition where plants are transferring very happily, where the conductances are constant. On the other side, another extreme limit is the bare soil evaporation, where evaporation decreases with increasing LST. And because all the net available energy is consumed by the sensible heat flux, that is making the evaporation zero. But the most important thing is, in the real world ecosystem, it is never operating in two extreme limits. It is operating within these two extreme limits. As a result, all the interaction and their behavior is happening from the point of crossover where the ecosystems are interacting. As a result, to know or understand the deeper detail, this whole talk is about how do we see the LST and evaporation interacting from the observational data set. Why do we really care about the conductances with respect to the surface energy balance equation theory, and what are the perplexity of the conductances in two different extremes representing energy and water limited conditions? And then if we can see some different view angle of mapping and or modeling evaporation, and what are the concepts and results. So this is the starting point here, taking the observational data sets over California in the summertime. This is the hourly data sets, and for June, July, August, September, it's alfalfa Mediterranean ecosystem. And this particular ecosystem receives 400 to 450 millimeters of annual precipitation. Here you can clearly see that there are two different conditions. One is non-restricted operating limit, and there is the restricted operating limit, where evaporation increases with increasing LST and net available energy, and after some point, it starts getting asymptotic. On the other side, evaporation decreases with increasing LST, and these are the points where net available energy is even decreasing. To understand it in a bit deeper manner, what we did is we plotted exactly the similar graph, but color-coded by time, and we found that, yes, latent heat increases with increasing LST until 10 o'clock or 11 o'clock or 12 o'clock, depending on the time of the year or the season. But after that, after the afternoon hours, even if LST is increasing, still latent heat is not increasing, rather it is decreasing with net available energy. But still it didn't give us much more clear conception that why it is happening so. Then we thought of plotting latent heat with the upwelling long wave radiation and a vapor pressure deficit. So while the long wave radiation gives a kind of proxy of surface drying because it has a direct relationship with the fourth power of surface temperature, and vapor pressure deficit is an indicator of atmospheric drying or atmospheric aridity, that gave us even more clear picture. One is the humidity controlled and another is aridity controlled. So in the humidity controlled environment, latent heat increases with increasing surface drying. It's very obvious because you can see that the long wave radiation, the magnitude is between 350 to 450 watts per meter square, and vapor pressure deficit is very low. So that means atmosphere is not so hungry and there is plenty of moisture, and so latent heat flux is increasing. But the moment it is reaching to some limit, that is 500 watts per meter square, and it is reaching the extreme limit of aridity, then again latent heat flux starts decreasing. So this gives us a kind of clear indication that evaporation is not only energy and water control through LST and net available energy, but also there is a very strong control by VPD. So this triple interaction, and then when we plotted it in Tonzi Ranch, which is a oak savanna, even we saw even more deeper interaction. And this interaction we found for a very narrow range of evaporation, where evaporation is almost 1/4 of what we found in alpha-alpha, but still there is a kind of restricted and non-restricted operating limit. But here this limit varies because this oak savanna is evaporating in a very different way. And here also we can see that evaporation increases with increasing LST and net available energy only until 10 o'clock in the morning, after which it decreases. And here also, the vapor pressure deficit and long wave radiation, it is even much bigger magnitude as compared to what we found in alpha-alpha. So now the question is, why do we care about conductances? Because we could have easily formed an artificial intelligence or machine learning and make a global function of latent heat flux or evaporation with LST and VPD and net available energy. Because these conductances are the fused forces. They act as a valency of surface energy balance. And as a result, in the classical Penman-Monteith equation, you can see that there is no role of LSTs there, because Monteith was so clever, because when he formulated his idea, that time we cannot think of getting any land surface temperature. But he gave us clear indication that if we are able to model these conductances as a function of LST, we should be able to put back those functions inside Penman-Monteith to run it in a forward mode and get a realistic solution of evaporation. So as a result, if we see through this cartoon diagram how it works, everything starts with the surface energy balance, where net available energy is dissipated into 3 different fluxes, and 3 different fluxes are invisible. And in these invisible fluxes, there are the hidden invisible conductances. And what we do is, if we want to, for the sake of scaling to understand the biotic and abiotic processes, what is the common practice is we develop some empirical equation to model these conductances. But now the question is, do we really need to model them? Can we really retrieve them from the observational data sets? So here is the equation of the conductances. I call them trinity in oneness of surface energy balance, because in the mystery of conductances, one is aerodynamic, one is canopy stomatal or canopy surface, and another is aerodynamic temperature, which is another mysterious temperature. So the first equation is the net available energy, and if you see that the whole information of land surface temperature is hidden if we do a second-order Taylor series approximation of the upwelling long wave radiation. And so this net available energy is dissipated into sensible heat, latent heat, and ground heat flux. And all these equations that I presented here, through some algebraic reorganization, we should be able to derive the physical expression of aerodynamic conductance, stomatal conductance, and aerodynamic temperature. So you can see that aerodynamic conductance is a physics, and that physics is apparently perpetuated into canopy soil substrate conductance, which is biology, and finally into aerodynamic temperature, which is a kind of amalgamation of both physics and biology. Now the question is how to solve this, and why do we find the missing biophysical link? Here again, for the same data sets that I presented, the scatter plots, here we plotted in the y-axis evaporation with vapor pressure deficit for an entire range of stomatal to aerodynamic conductance. So this gives us the real indication of the biophysical control. And here, these are calculated from the tower data. And the more these values are going towards 1, that means they have weak biophysical control. That means stomatal conductance is really high. That means wet condition. And the more and more these values are going to 0, that means it is a dry condition. That means the vegetation is really struggling to open up their stomata. And then here we can clearly see that latent heat flux increases with increasing vapor pressure deficit, even if there is strong control by the stomata, because these are the regions where vapor pressure deficit is kind of low, between 0 to 25 hectopascals. And the moment they cross that value, then it starts becoming asymptotic. And with increasing more vapor pressure deficit, again, the latent heat flux is coming down. So this is a strong kind of biophysical control. Then the obvious question arrives, how land surface temperature can help us? Then when we plotted this conductance ratio as a function of land surface temperature and color-coded with vapor pressure deficit, you can clearly see that the blue dots, these are the points where this conductance ratio is kind of wet condition, weak control, and they increase with increasing LST under low vapor pressure deficit condition. And the moment LST reaches at some point after 25 to 30 degrees Celsius, then the conductance is going down, because then the control of both atmosphere and the soil water stress are kind of putting a strong limitation for the plants to transpire. And in the inset, these are the figures, the same figure, which are color-coded according to different time of the day. And it's very obvious that this keeps on increasing until the afternoon or little bit noontime, and after noontime it is decreasing because there is a strong stomatal limitation imposed because of the deficit from the atmospheric water vapor and the soil water. And exactly we find the similar enormous LST and aridity control when we plotted the same data over Tonzi Ranch. And the most important part I would like you to notice that here, this ratio is just 0.1, and in the previous one, this ratio is 0.9. So that means here, the stomatal control is 10 times more as compared to what we found in alfalfa. So now the question is, how far do we follow this theory? So far, from my understanding, we have been doing a tug of war between thermal and non-thermal community, where one community is trying to model evaporation by using land surface temperature, and non-thermal community is trying to use VPD as a proxy of land surface temperature. But the most important point that I found out in my research, that the role of stomatal conductance is grossly overlooked in surface energy balance, and we are heavily concentrating on aerodynamic conductance parameterization to solve sensible heat and getting latent heat flux as a residual. And in that aerodynamic conductance parameterization, we run with so many different site-specific input parameters, and which I have no clue how can we map it globally, and how we can find out these coefficients specifically when it comes to the point of eco stress or the future thermal sensors, which are going to give us data at between 50 to 70 meter spatial resolution. So as a result, what I wanted to do is I wanted to bring both LST and VPD together, because they complement each other. When there is extremely high soil water stress, plants are transpiring less. As a result, it is automatically increasing the vapor pressure deficit of the atmosphere. So there is a feedback, but not direct feedback. So here is my 1 cent in the whole piggy bank of evaporation science. So if we see this explicit surface energy balance representation, of course, there are many component conductances. So what we started thinking is, we lump all the component aerodynamic conductance in a single aerodynamic conductance, which is, or resistance, which is RA, and all the lumped surface canopy substrate conductance in one single canopy soil stomatal conductance, which is RS, or 1 over GS. And then if we do the algebraic reorganization, you can clearly see that our aerodynamic conductance is a direct function of land surface temperature. And then finally, we are able to formulate these 4 state equations, where the land surface temperature information is percolating into GS, T0, and Fe is the evaporative fraction through this land surface temperature signal. But of course, in these 4 equations, there are 3 more unknowns. And to solve these unknowns, we solved it iteratively by using some other equations. So I can heavily recommend you to read these papers of Chaudhary and Monteith. It's one of the seminal paper, and it was very surprising to see that this paper has been cited only 100 times, despite it gives us so many richness of scientific information how to model evaporation. So with this model, then of course the thing is how best we can do the remote sensing based evaluation. So California could be one of the best test bed because I'm working with UC Berkeley and they have sites in multiple vegetation type, corn, alfalfa, oak savanna, and grassland, and all these sites are receiving 400 to 500 millimeters of annual precipitation. So what I did is I took Landsat 8 and 9 LST between 2018 to 2021, 4 years of data from March and October, and Sentinel-2 visible and SWIR and NIR bands, and try to evaluate them and see that whether this theory is really working. So here is the first-hand evaluation of how the satellite latent heat is behaving with the eddy covariance latent heat at the instantaneous scale. Of course, it's a bit disappointing to see that RMS is 69 watts per meter square, and only it is explaining 77% of the variability. But here we did not make any correction of the energy balance closure. And when we plotted our error with the energy balance closure, we could clearly see that there is a 17% relationship. So if we add this 17% with our own validation, so we are clearly getting more than 90% of the agreement. And then these errors we found out to be very strongly associated with fractional vegetation cover, which again shows that how much surface energy balance closure is important in this case. So now to understand the error, specifically we found out that we plotted our error with LST and atmospheric vapor pressure deficit, and we have clearly found that the model is not systematically biased because of high LST and high VPD, and also the model is not systematically biased because of high LST under fractional vegetation cover condition. Now the question is, do we see the same interaction? If you recall what I showed in the beginning, that how latent heat flux is combining with the long wave radiation, what we found out for the model, we found out exactly the similar kind of interaction in the left-hand slide plot for the observational data. And then we plotted the stomatal conductance observation versus our prediction. We found 67% relationship. Of course, the aerodynamic conductance performance is not good, and this needs further investigation. So here, this is the last slide, what transpired from the entire story, that we can, if we solve the surface energy balance theory, we should be able to reproduce the observational behavior of LST and evaporation. And as a result, we should be able to put the direct feedback of LST on the conductances without using any parameterization of site-specific coefficients. And this model runs with LST, emissivity, albedo, and environmental variables. And it should be spatially implementable with LST from all the future mission, and as we are currently doing it with our European EcoStress hub. So the idea is to bring back the legacy of Penman-Monteith and understand the evaporation and conductance variability from space. So with this, I would like to thank you all, and I would like to announce that our European EcoStress hub, ET and LST products are now available through WASDE, and you should be able to go and register and get this data freely available over Europe and Africa. Thank you so much.
Thank you, Kanishka. We'll have time at the end for questions for you. Thank you for giving us a really great, solid understanding of the theory of the drivers of evapotranspiration. And I'll hand over to the next speaker, if I can welcome Bukhra Al-Tassain, who will speak to us about an assessment of high-resolution evapotranspiration constrained by disaggregated land surface temperature. Thank you, Bukhra.
Thank you. Thank you so much. Hello, everyone. My name is Bukhra Al-Tassain. I'm an assistant professor in the Center for Remote Sensing Applications in Polytechnic University of Ben Guerir in Morocco. So today I'm going to present one axis of our ongoing works in the center, which is the assessment of the high resolution evapotranspiration constrained by disaggregated land surface temperature. So first, let's talk about the general context of our study. So we all know that the human survival depends on clean water, especially in arid and semi-arid areas. And this water is affected by several factors like the population growth, the increasing of demand on water resources, and also the overexploitation of these resources, especially in agricultural areas. There is also the problem of climate change that affects the distribution of precipitation in several areas, and also the increase of land surface temperature. So as I'm working in semi-arid areas, there is a need to react to those changes. And one of the the most known or the most ambitious initiatives is the adaptation of African agriculture to the climate change, and which is the sustainable, which has sustainable development goals. So, like the soil management, agricultural water control, and the climate risk. So the idea is the using of smart agriculture to ensure the water and food security. And to do this, we have to understand the hydrological fluxes. And the most one, which mentioned by our colleague Malik, is the evapotranspiration, which is the key variable for monitoring the crop water consumption. And we know that this is the most component result of the dissipation of more than 60% of the precipitation. So we need to partitionate evapotranspiration to serve the transpiration and optimize the management of practices and irrigation regimes. So the idea is doing a synergy between remote sensing, modeling, and using the in situ measurements to validate our results in evapotranspiration. So as we all know that the thermal data has historically been used because the land surface temperature is an indirect indicator of the vegetation water status in water limited conditions. But in remote sensing, we have those data are not available at high temporal and spatial scales. Like we have modest data that are available at daily scale, but the problem that 1 kilometer resolution is coarse for application on agricultural area, especially in our region. We have a Landsat data or ASTER. They are data at with a revisit of 16 days, but and a high spatial resolution. But 16 days it is not adequate to estimate evapotranspiration at daily time basis. So the trade-off is searching for a simple method that can conduct us to ensure at the same time the high spatial and temporal resolution of land surface temperature. So we think about a simple methodology which is combining Sentinel-2, all optical bands with modest land surface temperature, and we are using a simple multiple regression equations to retrieve the land surface temperature at 20 meter resolution. So to increase the temporal resolution, we added the Landsat 7 and 8 land surface temperature, which are at 30 meter resolution. So we can have at least 5 or 4 data. Each 4 days we have a land surface temperature, and we can assess this, the impact of those data on evapotranspiration estimates. So here in this study, we are using 2 energy balance models to assess the estimation of evapotranspiration model. The first one is the well-known TESAB model. There is a lot of improvement that have been made on this model by adding soil moisture as an additional constraint to improve the soil evaporation. But in this work, we are using the original version of the TESAB model, which is developed by Norman, and which use the land surface temperature and the vegetation index to estimate the evapotranspiration. The second model, which is the modified Penman-Monteith, which is the model developed by our colleague Amazigh Abdelhakim. He linked the stress indexes derived by the proxy of land surface temperature to RC, which is the surface resistance. So we tried to use those 2 models to see which of those models estimates the evapotranspiration, while evapotranspiration constrained by the disaggregated land surface temperature. the study area where we applied our methodology is located in Morocco, especially in 10 shifts in Marrakesh. So we tested our methodology over one rainfed wheat field, which is located at 60 kilometers east of Marrakesh. It is a parcel of 1 hectare of surface. And we tested also our methodology over 2 irrigated wheat fields located at 70 kilometers east of Marrakesh. So the reference parcel, it is irrigated according to the recommendation of FAO, ET0. And the controlled one, we applied a stress after the stage of development. So we chose the agricultural season of 2017 to 2018 to assess the estimation of evapotranspiration. So here, some preliminary results we received over the 3 sites. As you can see that the disaggregated land surface temperature, 5 minutes, okay. That the disaggregated land surface temperature are encouraging when comparing to the measured land surface temperature over the 3 sites, taken into account the division or the area seen by our apogee that measures the land surface temperature, and the pixel of the Sentinel-2, which is 20 per 20 meters. And here I'm presenting the results of the TSAB model while using the remote sensing LST, and in the red ones, while using the in-situ land surface temperature. So we quantified that there is a differences almost for the 3 sites of 10 watt per meter square of differences while using the 2 temperatures. And they are encouraging results until now, and we can get the best result if we improve or if we work on this version of TSAB model. So the results are more improved while using the modified Penman-Mounted model. So the quantified error while comparing the in-situ LST and remote sensing is almost 9 watt per meter square. So here I'm trying to spatialize our results of evapotranspiration using the 2 models. So what we can see that the TSAB model overestimates the evapotranspiration, and this is the problem of the alpha PT parameter taken 1.26, and this value always overestimates evapotranspiration, and like an important work have been made to invert this parameter at daily basis, and we found that at the senescence period, this parameter should be 0, and while taking it 1.26, it overestimates the evapotranspiration in our area, which is an irrigated area. And the results are almost important when compared to the land surface temperature while using the modified Penman-Mounted. So here they are the perspectives of our work. We are trying to assess the impact of disaggregated land surface temperature while using contextual models, and we are working on metric double source, which is a model developed by our colleague Jamal Al-Farh. And the second point is testing several models of data fusion, and we are working on fusion modest optical band with Sentinel-2 optical band to have a revisit of daily optical band, so we can receive a land surface temperature at daily basis. The third point is we are testing the sensibility of each band on disaggregated land surface temperature. And the first result, we found that the SWIR bands are the more correlated to the land surface temperature. So we will work on this point and find if this is a need to use all optical bands or just focus on the SWIR band to estimate or to disaggregate the land surface temperature. And the fourth point is using the TESAB soil moisture, which is the TESAB model constrained by soil moisture. As I worked on that on 2018, it is an improvement of TESAB model, so we can have an accurate estimate of evapotranspiration. The idea of this simple model is we want to build a model that can be used at large scale or at scale of Africa. So the physical models are good, but they are not, you cannot apply them at large scale, but the simplest one are incorrect, but they are useful in our case to go into the point. So I think that I reach the end of this presentation. Thank you so much, and welcome for your questions.
Thanks a lot, Bushra. I think we just have time for one short question in the audience, if you want. Does someone feel like asking a question? Okay, maybe. I was just wondering, you were talking about the correlation between LST and the shortwave infrared radiances. Would there be a link between what we've seen before from Malishka concerning the structural part of the vegetation and this kind of conclusion? I mean, perhaps it's a question for Malishka, and in fact, would it be interesting to use shortwave infrared in order to infer a relationship on conductances? Mike?
Hi, Philip. Yes, shortwave is water sensitivity, of course, and with increasing dryness, the spectral reflectance in the shortwave keeps on increasing, but the relationship is not very straightforward. Okay. So, a couple of years before, also we tried the same, and we are still working on it, but this is worthy trying and kind of exploring, of course. Thanks.
Thank you.
Thank you.
Okay, now we move toward the next speaker, Hector Nieto Solana. Good morning, Hector. I leave you the floor.
Okay, hello everybody, thank you. Yeah, I'm going to talk about a new project funded by ESA. It's a EU Africa Explorer project. We just started like 5 months ago. So actually, we don't have much results, sorry for that. So, I mean, instead of that, I'm going to show some previous work and the way that how we reached to this project. So yeah, I'm going to talk about starting point of water use and evapotranspiration, because I mean one of the final objectives of this EU Africa project is to water accounting and estimating crop yield. So in first point, we want to, I mean, we've done some work on evapotranspiration and water use. And then I've been working with some prototyping on the uses of thermal Earth observation, thermal infrared, in order to estimate gross primary productivity and crop yield. And finally, we will introduce the EU Africa Explorers called EOMAGI project. So yeah, the starting background are as well 2 ESA-funded projects which aim to estimate continuous or decadal evapotranspiration maps using Copernicus data. with objective of trying to do it in a operational fashion. These two projects are ZenIT, which deliver a plugin for Snap, and the continuation was CT4FAO, which was trying to in collaboration with FAO, to prove the utility of Copernicus Sentinel data to be implemented in their Vapor product. So the idea is, like, since so far we don't really have, with Copernicus data, high-resolution LST data, we have to bridge this gap doing some LST sharpening, what we've been talking about before in some talks, and there were some talks later on about sharpening. So I'm not going to be much in details, but yeah, we bridge this gap, and as well fusing Sentinel-3 with Sentinel-2, and as well incorporating actual LST data from Landsat and in the future EcoStress. We can get some continuous daily evapotranspiration and as well gap fill data. So these are results that I'm not going to be much in detail because there's a poster in the poster session by Rado Gudzinski. So please go to visit him. But yeah, we validated these decadal evapotranspiration maps in semi-arid sites in Spain and in Africa, and the results were quite promising. So at least for decadal evapotranspiration map, the sharpening provides a good opportunity when we don't have really actual LST data, with errors lower than 1 millimeter per day. So yeah, we've been talking also about the TCEP model. This is the model we are working in ZenIT and NT4FAO. The main reason is the model I'm used to work. The main particularity is like it's able to partition in soil evaporation from canopy transpiration. Although, honestly, I mean, since plant transpiration is quite challenging to validate, we don't really know how much well is doing the partitioning. And as well, we've been mentioned before that, yeah, TCEP requires some, besides LST data, some ancillary data, mainly leaf area index, fraction of green vegetation, and yeah, it's quite sensitive to the retrieval of these biophysical traits. And in particular, one of the most challenging is to get into account the canopy architecture, canopy height, and fractional cover. Luckily, we are continuously working in this code with the PI of TCEP, Bill Custas, and we provide the code in open source fashion in our GitHub account. So everybody is very welcome to access and try it. And of course, we will be more than happy to provide some assistance in setting up the model. So what we're doing right now, what we are working now, so we are trying to explore, and this is kind of very in line with what Kaniska has been presenting, trying to bridge the knowledge gap between energy balance and crop physiology, and trying to get an actual link between water and CO2 fluxes. This will help us to get an estimate of GPP using or with the help of thermal infrared information, and as well we aim as well to estimate crop yield. So similarly, I mean, this is the kind of two-source approach of TCEP, and since we are able to get an estimate of canopy transpiration, we can as well consider as well the carbon fluxes in this approach. So for the stomatal conductal retrieval, this is a kind of different approach as in Kaniska. This is more a kind of sequential approach. Kaniska is quite very nicely gathering all the processes in one single model. In our case, we run TCEP. We get our estimate of canopy transpiration, and as well from the estimates of our aerodynamic resistance, we can reinvert the model to get canopy stomatal conductance. We've been validated this stomatal conductance using either flux-based estimates of conductance, as well gas exchange conductance. These are vineyards in California with different stress regimes in terms of irrigation, and the results are quite promising. This is kind of a paper that's been published in Irrigation Science last year. Once we have these stomatal conductance, what we can do is to fit these, use these stomatal conductance into a kind of Farquhar-based model, typical like a scope and so on. But instead of estimating the stomatal conductance within the scope, we force our stomatal conductor derived by TSEP into the GPP model. Again, this is preliminary results, and this is just prototyping. In this case, we are using proximal sensing from LST derived from the actual eddy covariance data. So these are continuous measurements, kind of high-quality LST and in situ meteorological data. And the results, when you compare our thermal-based GPP estimates versus the eddy covariance GPP, the results are quite promising. This gathers like 3 years of the ICOS database, so includes a wide range of biomes and a wide range of climatic conditions. This is the dry winter database of 2020. So now we have GPP, but crop yield is a different stuff. I mean, of course, we can still use GPP to get an estimate of crop yield, because at this is productivity, and at some point the yield is related to the productivity. But in this case, we are testing a kind of different approach, and this is kind of simulation-based hybrid approach. We are using a crop model. And it's a kind of very similar approach as in the SNAP biophysical processor is based on in order to retrieve LAI. So we have, instead of radiative transfer model, we have our crop model. We run many simulations trying to cover the widest range of conditions, simulating a full range of meteorological conditions using 30 years of climate, of meteorological data, different range of soils, randomly changing texture, density, and so on, and different management scenarios. With all these simulations, we get time series of the crop simulation that can simulate leaf area index, biomass, nitrogen content, of course, ET, and finally yield. And the idea is to regress through a machine learning model the relationship between yield and some of these time series metrics that we expect that we can derive it from Earth observation, leaf area index, chlorophyll, ET, and so on. And finally, apply this regression model with the Earth observation data. We haven't arrived yet to the application to Earth observation data, but I'm going to show you some results on the crop model simulations. And so, yeah, we've been using, I'm not an expert on machine learning, so sorry. We're running, we used, in that case, simulated wheat in Spain, so with the climatic condition of Spain. And with only 3 metrics, we are able to get pretty good results in order to predicting yield. The main important metrics, as we can see, well, this is kind of the, I mean, we know that machine learning is a kind of black boxes. So, but yeah, by some techniques, like a feature permutation, we can get some idea of the variable importance of the weight of each variable have into the model. So in this case, it's interesting that the most important or the largest weight into the model is the transpiration deficit during the late spring, which is precisely the moment in which the grain, the ears of the weeds are still photosynthetic active, and they're using this energy into filling the grain. So this is quite critical time. So this deficit, which is very related to transpiration and thermal infrared information, is the most important variable, followed with the peak biomass and the mean nitrogen content per leaf. As I mentioned, I have no idea of machine learning models, so I just wanted to test different models to see if we still have some robust results. We did the same with Gaussian process regression, similar prediction capability, and same weights, or very similar weights, and as well we support vector machine regression. So we are kind of pretty confident that the approach is working adequately, and we are as well optimistic that the use of thermal infrared can be used as a predictor, one of the predictors for predicting yield. And finally, this is what we are doing so far in this project, is EOMAGI, is Earth Observation System to manage Africa's food system by joint knowledge of crop production and irrigation digitalization. We are using EcoStress Prisma data with the help of Sentinel-2 and Sentinel-3 to run our models, estimate yield, but also map irrigation and account for irrigation. So thank you so much.
Thank you, Hector. I really like the way that you provided a real-life use case for some of the theoretical discussions we've had already. I think we have 1 minute for one question, if anyone would like. No, we will also have time for questions later, but thank you, Hector.
Thank you.
I will now welcome the next speaker, Paulina Barkowiak, who will speak about the potential of Sentinel-3 LST downscaling. Thank you, Paulina.
Good morning, everyone. I am Paulina. I am postdoc researcher at URAC Research at the Institute for Earth Observation. And today I would like to talk about potential of Sentinel-3 LST downscaling for estimating evapotranspiration from two-source energy balance model. This work has been financed by European Space Agency in the framework of 4DMate hydrology project. So firstly, I would like to say very shortly about the context and motivation on evapotranspiration modeling. So why we are interested in evapotranspiration? So the first reason is environment. So evapotranspiration, as you know, is a variable that can allow monitoring water from soil and vegetation components. In the context of climate change and intensification of drought events, it is a very important eco-hydrological variable since it corresponds to around 60% of yearly terrestrial precipitation. But there is another component and reason why we want to monitor evapotranspiration. There is technological aspect. First of all, it's of course Earth observation data sets that allow us to monitor continuous evapotranspiration. And on the other hand, computing resources. Apart from storing our data sets, there are a increasing amount of cloud computing providers that deliver us Earth observation data as our inputs for the modeling. And thanks to high computing resources, we are able to estimate evapotranspiration much faster, thanks to high memory and high performance of cloud computing platforms. So my objective is to estimate evapotranspiration maps at daily scale at higher spatial resolution of 100 meters and with a temporal coverage of 5 years between 2017 and 2021. Since the project of 4DMate hydrology is focused on a Mediterranean region, we are working on 4 basins over Mediterranean region, over Po Basin in Italy, Hérault in France, Ebro in Spain, and Medjerda in Tunisia. So now, shortly, I will just say a couple of words about the methodology and processing workflow. The method, as Hector mentioned before, for me, the situation is the same. I model evapotranspiration based on two-source energy balance model, and in general, creates separate components of energy fluxes from soil and canopy. So the practical retrieval is based on the fusion of different data sets. The model is forced by thermal data from Sentinel-3, multispectral information from Sentinel-2, and climate data from ERA5. The entire algorithms were implemented within Sanity projects, where we combine all SNAP biophysical processor workflow with scripts for TSEP and so on, developed in Python. Processing pipeline. So as I mentioned, we perform here data assimilation using different resources from Sentinel-3, so land surface temperature, multispectral information from Sentinel-2, ERA5 at 100 meter spatial resolution. So our intermediate outputs are land surface temperature, biophysical properties, and structural parameters from Sentinel-2, and climatological components from ERA5. Based on these parameters, we incorporate data sets into two-source energy balance model to derive instantaneous energy fluxes. And next, to extrapolate our fluxes using solar radiation from ERA5 to derive daily evapotranspiration maps. So in general, the entire processing workflow is kind of complex because first we need to, of course, derive land surface temperature at higher spatial resolution, since Sentinel-3 gives us 1 kilometer pixel, so we need to perform pre-processing and downscaling to 100 meter. Secondly, we need to pre-process Sentinel-2 data and derive biophysical properties. And of course, climate data from ERA5 need to be processed as well. Considering the complexity and the high computational demand of the process, we decided to distribute our processing workflow into 3 different, let's say, computing platforms. The first one is of our in-house resources of URAC, and then we tested infrastructure provided by ODC and Cloudflare. Considering the spatial overlap between Sentinel-2 and Sentinel-3, we delivered our maps at Sentinel-2 tiling system, and in total it is 52 tiles. So just to give like a picture of space demand, so one 5-year tile it's around 600 gigabytes, so it's very, very demanding considering space and memory. So now the results. So over Mediterranean region, we had unfortunately only 8 flux towers location from 2 different providers, from EFDC and ICOS. The stations were located at different land covers, 4 on grasslands, 3 on forest, and 1 on vineyard area. Terrain was very diversified as well, starting from 1 meter to over 2,000 meters above sea level. And the mountain region was, the stations were located both at slope and plateau areas. So the overall results from all stations, considering pixel-wise validation, give us a collation coefficient of around only 60%. So, however, if we separate our results considering different land cover classes, we can observe that the model was very performant over vineyard regions with around 90% of Pearson correction, and we got moderate results over grasslands, while forest sites were, not performant at all. So here I just I would like to show examples for the time series. So here we have vineyard eddy covariance stations located close to Venice. And we can see that model is very performant in the case and really follows the eddy covariance measurements. The next good results were obtained for grassland region located in the Alps at around 1,500 meters. Here, model was capable of modeling pretty well. However, we have to know that this region is located on plateau, so there is much easier conditions considering solar radiation, for example. So now here there's example when we compared our simulations with different data sets. So here you have eco-stress data and MSG Severi. So here it's kind of promising because Sanity can provide, let's say, better results than eco-stress. However, this analysis was performed only for 25 observations because we need to consider temporal overlapping of the observations. Yeah, anyway, this is very promising. So now I will move to our worst results. Here we have grassland at alpine region over 2,000 meters. Here we can unfortunately observe huge underestimation of the model. Similarly, worse results we derive from forests. One forest, even green needle leaf forest. Here as well there is kind of underestimation, while for forests in Pushabun there is lack of correlation and observation are completely not corresponding to each other. So just to sum up, so two-source energy balance model is capable of modeling daily evapotranspiration at relatively satisfactory accuracies. However, the model is very sensitive to land cover and terrain complexity. We can observe still existing heterogeneity within 1 kilometer LST pixel and, of course, climate data. And we have to be aware that the entire workflow is very high computing demanding, so we need to be prepared considering our infrastructure. So overlook, we would like to share our evapotranspiration data sets using OpenEO platform. And the next step would be data paper when we describe entire workflow and data sets itself. Of course, the model still needs to be improved. So we would like for future research, we're gonna work on the improvement of the model, considering forested areas. And since LST is prone to cloud coverage, we would like to perform tests to predict missing pixels under cloudy skies. Thank you very much for your attention.
Thank you, Paulina. We have time for 1 or 2 questions. Yes.
maybe microphone. Okay.
No, there are some people connected that need to.
Thanks a lot. You mentioned MSG for geostationary data that could be useful.
Yes.
Now there is MTG in orbit with a
Yes.
1 kilometer spatial resolution and 10-minute images temporal frequency. What do you think about that? Would it be something that you
Yes.
could benefit from?
Yes, actually, yes. Currently, in our current project, Kaleidoscope, we are planning to update model using higher resolution data sets. Yes, exactly.
Okay, thanks.
Hi, Paulina. Like, do you have any explanation for the large uncertainty for the TSAP over forest as compared to grassland and vineyard?
Of course, first of all, I presented 2 cases for forest. One forest is located in the Alps, so it's a relatively heterogeneous region in terms of land cover and topography. So this can be a reason. Another reason can be like the different layers of the forests. So they are behaving different. And of course, in this, we sharpen LST, but still the information is very much mixed of land surface temperature. So, and shadows, of course, I think. But I think there's so many different aspects that, yeah, data and conditions, it's difficult.
Thank you.
Maybe just a very last question. I would have one otherwise. You've shown results, comparison between Sentinel-3 and EcoStress. Could you give additional comments on the results?
Actually, this work was done by my colleague. I shared the data sets I generated using SenET over Monte Bondone. Of course, he didn't compare strictly the same models because from EcoStress he used model PT, JPL model, evapotranspiration, and he derived better results, yes, using my data set.
Could there be a link with heterogeneity at the scale of the Sentinel-3 pixel? I don't know what are the assumptions concerning the heterogeneity. Is your landscape very homogeneous on the resolution?
Yeah, this even though it's mountainous, Monte Bondone, this is plateau, so it's relatively plain, and there is a huge surface of grasslands. So I suppose that there is maybe smaller impact of the different land covers as well.
Thank you.
Thank you.
Okay, thanks a lot, Paulina. Now we move toward the next speaker. I'll use this one. Go ahead, because Carlis Zalit, who's going to talk about the simulation of high spatial temporal land surface temperature at scale. Carlis.
Hey.
Okay.
Hello. My name is Carlis Zalit, and I'm a geodata engineer at eLeaf. And eLeaf provides data for the Vapor portal, which probably a lot of you have heard about, hopefully. Openly, there's freely available historical and NRT evapotranspiration data available on the portal at different scales. And the version 3 of the data will have 300-meter data on a global scale, 100-meter data on continental scale, and 20-meter data on a regional scale. The ET data is based on the ET-LOOK model, which uses surface energy balance model and inputs from satellites, so NDVI, albedo, and LST. And the current LST missions sometimes have limitations to provide data for agricultural applications. So we went the way of image enhancement and basically took the available thermal missions and sharpened the thermal data to a higher resolution. And yeah, the approaches are probably also already kind of well known. The data miner sharpener approach and its implementation in Python, and I believe the author is also here of that implementation. So this is kind of what my presentation will be about. I'll walk you through how the sharpening is done for the level 2, the 100-meter data. I will end this presentation at basically what we do with the soil moisture outputs, and then my colleague later is going to give you a presentation where he will show some results at scale and talk about those. Thermal sharpening can be roughly divided into 2 parts. It's the selection of input features and preparation, and then the sharpening itself. And I'm going to walk you through each of the components. So we start with the inputs. So because the target resolution is 100 meters, so we take Sentinel-2 data, we reproject it also to 100 meters to the target resolution, and the same we do with the Copernicus DEM. And then from these inputs, we create the features for the sharpening. In total, we evaluated about 50 input features, and we selected some of them. It's a balance of the quality of the outputs and the computation complexity, the time it takes. So the final features were the 2 bands of Sentinel-2, the blue and near infrared, then the elevation, and also 2 features calculated from the elevation, the slope and aspect, and also Sentinel-2 based indices. And as you can see, there's also shortwave infrared bands in the indices, so that's part of the sharpening, the idea that you use optical and shortwave infrared features to model the thermal infrared. Then, as a first step, the high-resolution 100-meter features are resampled to 375 meters, which is the resolution of your low-resolution thermal inputs. In this case, we are using data from VIIRS. It's very nice revisit times over, you can get even 3 acquisitions, even more per day, about a pixel, a point on Earth. So this is the band 5 is our low resolution brightness temperature input. Then we need to select pixels which will be used to train the regression. And the idea here is that we want to use the homogeneous pixels. And homogeneous in this case is if we take the low resolution pixel and we calculate statistics in that low resolution pixel of the high resolution pixels, we calculate the coefficient of variance over all of the input features and take the average, and then we select like a threshold. So if the high resolution pixels are they have a high coefficient of variance, we will not use them, and you can select the threshold in the method yourself. Here's an example just how it looks on band 8. yeah, as I mentioned, so then you have the low resolution, the brightness temperature input from VIIRS. It's 375 meters. And then, so this data miner sharpener, it basically builds regression trees between the thermal infrared and the shortwave and optical data. And it basically does two types of regression, local and global. And the local one is done with a sliding window. And while the idea is that the local regression will be, in general, should provide better data, you might run into issues when, let's say, it's a very heterogeneous area, so you'll have very few pixels, and your regression will be not very representative, and the regression will have issues fitting some outliers or poorly represented pixels. So for that, you also run a global regression on the whole image. And also to make, because you're using local regressions, but in the end, you're looking at the whole image reconstructed again, to make it a bit more smoother, the windows overlap. The moving windows they overlap. As I told, the global regression, of course, is a bit more representative, but might not capture the local features. And then the final result, the final fit, final prediction is based on weighted local and a global regression. And how do you assign those weights? Basically, you calculate from the input low resolution, you calculate residuals between the input low resolution brightness temperature and then the predicted brightness temperature, but at low resolution. So you first predict at low resolution, and you use the local regression, you use the global regression, you calculate residuals between the input and the outputs, and then for each pixel, you select basically which regression you will use, or what weights you will apply to the local or global regressions based on the residuals. So here, for example, you can see kind of a representation. So for each pixel, here it's marked green if you have more weights for the local regression, or purple if the global regression has a higher weight. And then the result is, so yeah, it's kind of a weighted prediction using both of the regressions. And this is a tile in Morocco. And this is then a 100-meter brightness temperature output. And the residuals are then again redistributed in a 100-meter image to account for some poor predictions by the model. So this is the final result with the residuals redistributed. And I think it looks pretty nice. Also, if you compare to Landsat, for example. Did it switch? Yes, okay. So this is the Landsat, yeah. And here's you can see the example of the 300-meter input and the output at 100 meters. And then just shortly, not the purpose of this presentation, but then the brightness temperature is converted to the land surface temperature using a single channel algorithm. And then the LST is converted to soil moisture using the trapezoid method. Then yesterday we heard some interesting presentations about the look angle, the importance of it. So when we have these instantaneous soil moisture measurements, we apply additional smoothing over the whole period using Whittaker smoothing. And for each instantaneous soil moisture prediction, we apply weights based on the distance to clouds. We use the provided cloud mask by VIIRS. So the further from clouds, the higher the weight. And also viewing angle impacts the weight. So the larger the angle, the lower the weight. And we also apply the same technique for our so for level 3 data for 20 meters, and pretty much the same approach. Then just your high resolution features are at 20 meters. And yeah, these are examples from Lebanon, from Bekaa Valley. And so this is an image from Google Maps, and the 100-meter result and a 20-meter result. Yeah, thank you. And if you have any questions, you can find me around the conference. And yeah, as I said, stay for the follow-up presentation by my colleague as well. Thank you.
We're having some trouble with our mics, but thank you very much to our
Thank you.
speaker. If I can welcome our final speaker for the session, Albert Lioso. Thank you for sharing with us your work on uncertainty quantification and ensembles.
Thank you. So I'm not going to talk about the hotspot today, so I will have less trouble. So I'm going to present a work that was done in the frame of ESA project to investigate the uncertainty in estimating evapotranspiration from remote sensing data. And the problem is that, okay, we use the remote sensing data and we think, next, okay, that remote sensing data are the main driver for uncertainty, usually. And actually, this is not true, is what I'm going to show there. Okay, so I'm not going to say something about evapotranspiration. There was so many talk before talking about that. But one thing is that there is many models to compute evapotranspiration. It's very difficult to know which one is performing the best, or when, where. It's changing all the time. It's changing also depending on the author. So in this type of situation, one solution which is used in different fields of research is to use an ensemble modeling, which is to gather the different models in order to provide different estimates of evapotranspiration, and after that to derive some kind of average, which is supposed to be an optimal or suboptimal estimate of evapotranspiration, and also that provides an estimation of uncertainty. And it is the kind of uncertainty I'm going to talk about there. When you look at evapotranspiration, you have a lot of different inputs. So first, in this workshop, of course, is surface temperature. But surface temperature, you get it with some uncertainty related to the sensor, but a lot related to the atmosphere characterization when you have to do the atmospheric correction. There is a large number of models, so I was saying before. You need a lot of other data to obtain evapotranspiration. So, for example, the albedo, which is coming also from remote sensing data, but in another spectral domain. The vegetation density can be LAI, fraction cover, or whatever, and also the meteorological data. And when you want meteorological data over a large area, it's not so simple to have something at the pixel scale. Another source of uncertainty, if you want to have evapotranspiration for the day or for some period, is the way you can upscale the instantaneous estimate from remote sensing data to the daily scale or the seasonal scale. So here, as there is first no consensus on which is the best model, so we can use ensemble estimation for evapotranspiration. But not just with the model, it's also possible to use the ensemble technique by considering different sources of data. So it's not just an ensemble modeling, but it's also an ensemble modeling and data ensemble that are going to come together to estimate ensemble evapotranspiration. When you look at what is in the literature, there is very few information on the uncertainty in evapotranspiration estimation. And the ensemble system is able to provide some information on this uncertainty. And for example, by using the standard deviation of the different estimates for one pixel. Here I'm going to show results with two different types of models. So there is what I call evaporative fraction models, which is based on the triangle approach some people were talking about before. So in this model, you need to scale the temperature between a dry limit and a wet limit. And the position of your pixel in comparison to this limit is assumed to give you an information on the evaporative fraction. And when you multiply the evaporative fraction with the available energy, which consists mainly of the net radiation, you get an estimate of evapotranspiration. To run this, you need surface temperature, of course, the albedo, the surface temperature, the solar irradiance, and the atmospheric irradiance. To compute the grounded flux, which is part of the equation, you also need some estimation of the density of vegetation, for example, from fraction cover. The second model is a residual aerodynamic equation. So in this model, you use a framework of resistance. So here I use a monodimensional one, not like that was presented before with TSEB or the work by Kanishka, but so it's just an illustration. And in order to compute the turbulent flux in this type of model, you need to have information on the air temperature, the wind speed, and the roughness of the surface. Okay, here I say, so I will present also results at the daily scale. So there is an upscaling from the instantaneous scale to the daily scale, which is done by using the ratio between the solar radiation at the time of the measurements and the solar radiation for the day. I was doing this work on an experiment that was implemented by ESA. So it's in Grosseto in 2018, in July, and I used data for 2 different days. So data are coming from airborne sensors. And after that, in order to get evapotranspiration, we need a lot of different input data, in particular with different sources for incident radiations, LAI, F-cover, surface temperature also we show. And also we're using in the calculation different versions of the models for grounded flux, evaporative fraction, and albedo, and also the roughnesses. So this is the different type of the variation that we can have when doing this work. On the left, you have the evaporative fraction. So I say that you have to scale or to position your pixel against a dry limit and a wet limit. So it is the line, the red line and the blue line. And depending on the algorithm, you may have different estimate of this line. And this is going to generate uncertainty in the system. On the right, you have a function to compute the grounded flux from net radiation. And also, we don't have too much information on that, so there are different equations to estimate that, and equations also with different parameters. and we don't have the real information at the ground, so we need that generate uncertainty. And on the bottom right, you have the different measurements or estimations of solar radiation that I obtained on this area. So this is coming from reanalysis or coming from the Meteosat data or coming from ground data, and you see that there is a large variation in solar radiation in this estimate. Considering uncertainty, on the left, there will be in my presentation what we call the novice case, which means that we use all the available data to estimate evapotranspiration and then uncertainty, or the expert case where knowing some information on some of the data, we can discard some of the data. For example, in solar radiation, there is one of the reanalyses that we know that it is usually underestimating solar radiation, so we drop it from the analysis, and that changes the uncertainty. And of course, not everyone can do that. You need to have a lot of information before in order to say, I'm going to use this data source or not. We define also two types of uncertainty. One, it is a global one, where we combine all the different sources of data and type of models. And another one is a one factor at the time uncertainty, which is related to the variation of just one of the factors. This is the surface temperature estimation that we have for this area and for this one of the day. And there was 4 different estimates of surface temperature with different way of doing the test method and doing the atmospheric correction. And this generates 5? Okay. So this generates an uncertainty or variability of surface temperature estimate. So on the right, you have a map of the standard deviation of surface temperature. And you can see that this standard deviation can be quite high, like 1.5 degree or more. And of course, this has an impact on the uncertainty of evapotranspiration. This is 2 maps doing the ensemble system. So having all the cases together and doing the average of that. So the novice case on the left and the expert case on the right is almost the same thing. There is a small difference in the average value for the area, a lot because I dropped the solar radiation, which was underestimated in some cases. Here you have the first map, the map before was the evapotranspiration map, the average, and here you have the standard deviation map for evapotranspiration for pixel by pixel. And on the right of each map, you have the average value of this standard deviation, which is considered as the uncertainty here. So you see the uncertainty in the expert case is like half the case for the novice case. And this uncertainty is quite okay. So, but it is the average at the scale of the map. Here, at the top, you still have the same map, but at the bottom, you have the uncertainty, which is only related to surface temperature, and which is very low compared to the full uncertainty. So it's less than 0.1 millimeter a day compared to, let's say, 0.5 millimeter a day. So which means that the surface temperature impact is not so large in the estimation of ET. And here you have the breakdown of all the sources of uncertainty on the estimation. So you have the 2 types of model and the 2 types of uncertainties, the novice and the expert range. And you see that some factors have a very large impact on the estimation. So if you look at the aerodynamic model, it is the wind speed and the ratio for grounded flux to net radiation, and also the air temperature, and also the roughnesses, Z0H. And if you look at the evaporative fraction model, the evaporative fraction calculation is the main source of uncertainty. And if you look at the surface temperature here, you see that the surface temperature, the uncertainty in surface temperature has not such a large impact compared to the other source. If you aggregate all the other sources of uncertainty, the surface temperature in the range we were computing, this surface temperature, has not too much an impact on the final uncertainty. This process is going to be applied in a simplified way in the production for the level 2 evapotranspiration with Trishna. And this is an example of what we can do for apply to Moody's data on an area which is like 500 kilometers square. And on this graph, you have the two Moody's average we obtained from the ensemble modeling. So the Terra and the Aqua ensemble modeling. And all the gray lines are the different estimates we have depending on the uncertainty, mostly in this case, mostly related to the evaporative fraction calculation. And to conclude, so we feel that we can use this type of ensemble modeling, combining models and data sources in order to monitor evapotranspiration, and at the same time to provide uncertainty in evapotranspiration. This uncertainty is not the error, so it is just the range related to the range of the estimation. Is not related to the comparison between the estimates and the measurements at the ground, for example, or the real value of evapotranspiration. And what we found here also is that the surface temperature is not the main driver, and that we need to put effort also in the way we're going to have the meteorological data. So when you want to map evapotranspiration over, I don't know, 100 kilometer by 100 kilometer, you need to distribute all this atmospheric data at the pixel level, and that generates an uncertainty which may be large and larger than the impact of surface temperature. Also, we found that the contextual models have less uncertainties than the aerodynamic models. In the aerodynamic model, there is many parameters that are more complex to obtain than the parameters that are required for the evapotranspiration fraction model. And in particular, it is the meteorological data that have a strong impact. And yeah, this algorithm called EVASPA is going to be implemented for the Trishna product. Thank you.
Thank you, Albert. We'll now enter the discussion time for this session. Will all the speakers please come to the front? As they're coming to the front, I'll quickly summarize. So Kanishka began with an excellent illustration of the drivers of ET and advocated for the combination of LST and VPD in ET models. Boucha followed with an analysis in Morocco showing that some standard models overestimate ET in semi-arid regions, and she showed the benefit of incorporating the SWIR data in a disaggregation model, which ties to Kanishka's observation that the SWIR represents water stress, which is a driver in semi-arid regions. Hector aimed to bridge the gap between energy balance and crop physiology. He showed a real use case in yield prediction, where late spring transpiration deficit was the most significant provider. Paulina and Carles both showed some downscaling and high-resolution simulation methodologies, which really illustrated the importance of high-resolution thermal data going forward. And in particular, Paulina illustrated this by showing how it was really difficult to simulate high-res data in the highly heterogeneous forested regions. And then we had Albert's really interesting discussion on uncertainty quantification and showed the benefit of combining different ET models in an ensemble while characterizing the uncertainties of each component in each of the models. And it was interesting that land surface temperature wasn't necessarily the driving uncertainty. Thank you all for some excellent talks, and now I'll open the floor to questions.
Good morning. My name is Zuri Greisman. I'm from Elbit Systems in Israel. The workshop is very exciting for us as we also develop today multi-band and multispectral thermal EO satellite. I hope next year we'll be able to present what we are doing and what we think we can bring. But one of the things that puzzle us, and maybe you can help us with, is how can we monetize and quantify the economic value to the end customer, given the services of all the value that we create here, and how do we communicate and approach the market value in order to get the message to the end customer and create this demand being pushed to us instead of us convincing them. Thank you.
I think the committee selected me to answer the question. To be honest, there's not an answer, I will say, because it depends as well on the socioeconomic conditions of each country and its farming situation and each product you want to provide. For instance, if we think about irrigation and precision agriculture and water saving, at least in Spain, water is very cheap, unfortunately, but energy is not. So you have to monetize and convince farmers and farmers association that saving water will save you energy, and you can monetize the amount of energy. But it's in our case. In other countries might be different, and so I don't know if anybody else wants to provide any different answer or different opinion.
Yes, go ahead.
I mean, this is a very viable question. The most important thing is we can do this monetization in different steps. In the beginning, the most important part is thermal data can be used for near real-time monitoring of crop water stress. So we can start forecasting flash drought based on the thermal remote sensing and all these variables. And we can show what are the vulnerable areas where we have higher risk. So it can directly go into the crop insurance scheme. And then slowly we can just show that how can we kind of replace the traditionally used irrigation scheduling algorithm with better high spatial resolution evaporation maps, and whether we are getting any difference in the irrigation water requirement that we used to compute with the old method and we are using the new method, and what kind of per kilometer square area, how much water we can save with respect to the irrigation water requirement.
Excuse me, yes, but if this monetization wasn't done yet and we cannot really have good estimation of the economic value, how do we justify the huge investment in the satellite segment and in the upstream? We are puzzled with this, yes? This is challenging for us. And how do we justify to our management and to our financing angels, I would say, this business case?
So I think the best thing to do is doing case studies where we have intensive observation with respect to both satellite and measurements are available, and doing historical case studies and especially in those regions where irrigation, crop yield, and all the observations are historically available. And then with those case studies, you can just see that how much percentage of improvement you are getting. And those case studies can be how can I say, as a catalyst for the future investment. You're welcome.
Last comment I forgot, I mean, as well there's a way, because I mean, me as a EO Africa beneficiary, one of the objectives of EO Africa Explorers projects are trying to, well, we have African, what's called early adopters and users, and we're trying to work together with them to, I mean, propose them products, algorithms, and they will get some feedbacks. And these end users are, in our case, is the Ministry of Agriculture of Burkina Faso, Ministry of Agriculture of Botswana. So, I mean, these people are the really ones that know or can predict more or less how much money or can monetize the benefit of this. I mean, in our case, we are scientists. We are not extensionists so far. I mean, this is not really our field of expertise. So it's just a guess.
Okay, perhaps before I have actually a question to scientists, but just one comment to the question beforehand. I mean, the public institutional missions are driven by normally policies questions, and so environmental monitoring, making sure that certain policies are being met and being monitored and implemented accordingly. So it's not so much a business case driven case, and I think the question should have been asked yesterday to the New Space session, where there are actually many people putting the money on the table to invest in these type of space infrastructure. And so I do have a question to the scientists here. You have put several applications on the evapotranspiration modeling part on the place, and you're building on the space assets which are there and coming up. But to make it really operational, I think in all of your modeling you need additional data sets, and there we really are aware of that is needed, and we would like to understand how we can support that the right informations are always there to make sure that this operational evapotranspiration conversion from LST to a more final information content can be ensured. And perhaps you can list a number of parameters which are very, well, the most crucial one. I saw something on Albert's study where the most critical parameters are, but I mean, perhaps between you can bring some experience here on the table so we can try to respond to that.
I mean, this is one of the point that I personally keep on pushing about using analytical or the non-parametric modeling framework, because complex models are excellent when we have all the in situ variable recorded at the ecosystem scale to understand the level of complexity. But when it goes with the operational application or operational data generation, we need to have some kind of optimization. So the most important part is, of course, satellites are giving us land surface temperature, emissivity. From the optical, we have vegetation index, we have other semi kind of water stress related information from SWIR band. And with respect to environmental variable, what we see is this radiation, air temperature, humidity. They are available from ECMWF at 1/4 degree spatial resolution. And very often when we want to merge it with the high spatial resolution satellite data, we see a lot of uncertainties coming, but this is someone we all are facing for Trishna also. And so we are trying to see that what are the best variables we can use, for example, using solar radiation from geostationary. And so this is one of the things, but of course there are other different excellent quality models also which needs a lot of site-specific parameters. And I'm not one of those who are the users of those models or developers, but definitely those models are also strongly encouraged if they have the right solution on how to develop a spatial or spatial representativeness of the different input parameters that are required, which are less uncertain. So this is my own view. Thanks.
So I don't know if there is one point also is that some of the parameters in what I was showing is one case. So maybe the breakdown of uncertainty is going to change. Also, it's one case, one day. Well, one place, one day. And the thing is to find which variables are critical and all the time, let's say, and also to switch from, for example, there is parameters that we cannot get easily, like the vegetation height. So we have to drop models with vegetation height inside, or find a way to use them as and vegetation height as is not sensitive in the calculation. So for example, Kanishka has developed a model stick where vegetation height is dropped from the model. So we don't need to have this parameter we cannot know usually. And the same thing for the different variables. For example, wind speed, in this case, was very sensitive. It's the first time I found it is very sensitive. So we need to have models. If it is something classical, we have to use model without wind speed, maybe. So the evaporative fraction model has no wind speed. And your model is not using wind speed also. The type of things we have to think about. And after that, something which is very critical is the meteorological variables, to have them really at the right scale and in a timing very rapidly. So coming from analysis, meteorological analysis, which means also that there is some error in that, and we need to study that error. But if it was possible that the agency, when they provide the ET product, or a company is providing ET product, and if they can provide at the same time these variables, it would be a lot helpful, maybe to change the calculation and to have more that people can adapt maybe to their own situation and so on. Yeah. Thank you.
Maybe a quick follow-up, a bit more specific, Albert, on this. Thanks for all the budgets for the different methods. The breakdown for the error is very important. Just to understand, in your estimation of these contributors to the uncertainty overall, when you talk about uncertainty, you talk about the daily evapotranspiration, and I understand you upscale from the instantaneous evapotranspiration using the solar radiation throughout the day. How about the wind? Do you assume a variation of the wind over there, or it's built into this large part of your uncertainty? You have an assumption about the variation of the wind speed throughout the day?
Okay. We just upscale with radiation, assuming that the course of evapotranspiration is going to be similar to the course of solar radiation, that there is homothetic behavior, which is not completely true. There is stress and things. So it is the most convenient way we found to do that at the moment, from 1 point a day to the whole day. And any other variable is not accounted. Nothing is accounted. Albedo is changing, wind speed is changing, temperature is changing, air temperature is changing, surface temperature is changing, everything is changing, but we don't account of that. But there was many studies on that type of things. And this is providing a good estimate. And it's not critical with all the other inaccuracy we have at the instantaneous scale when the satellite is coming.
So the contribution of the wind speed, for example, assumes a given knowledge that you have on the wind speed as an auxiliary data. And this you assume that you maintain this knowledge throughout the day.
The wind speed was changing during the day, is not accounted, and it has an impact. And it is not in the impact of wind speed which was shown there. It will be in the impact which was not shown there of the upscaling to the daily scale. But it's more complex to compute, so it's not...
But this means it might be an even larger uncertainty if those...
It's missing, but it's not a large uncertainty compared to all the others. So it's why it's not accounted, actually.
Okay, thank you.
I have a comment or a question to you, but also maybe to previous speaker yesterday. There are many talks about using the field data or the field measurements to calibrate and validate the data. But we all know that there is a large mismatch between the field measurements and remote sensing data in sense of spatial but also temporal resolution. And I a little bit missed the discussion about that. So I think we should really consider this mismatch in interpreting our data and also calibrating it, because it's I understand there are many limits in collecting the field data, but on the other hand, the mismatch is great. Thanks.
Yes, this is a real problem. It's why everything I present, there is no flux data at the ground. Because if you are sure of your ground flux data, maybe you can do it, but the uncertainty or the error in the flux measurement are very large. You need to work like days and days to have something that maybe is okay and to validate your flux data before doing the comparison to what you get with remote sensing. Plus you have the footprint issue, you have everything which is really a problem. So maybe by doing a lot of comparison study between the remote sensing estimates and the ground data in many places for a long time period, maybe it's something, you get something which is statistically correct, but if you look just for few years and few places, it's maybe not enough to be sure. And this is also one of the reasons there are so many models, there are with a lot of different results. And this is a very deep problem, and I don't know how to solve it. Maybe by integrating the estimation of evapotranspiration in something else, like the water consumption or an hydrological balance, and check the hydrological balance with the flow, river flow or whatever, but it's complex, yes. And I don't know if there is a solution.
If there is no other question, the last one, no? Okay. Maybe we should finish now. We will finish now. We have a coffee break beginning right now for 20 minutes. Just a last remark. For sure, we've seen during these many presentations that there is a constant care for the reliability of the data, the reliability of the metrics that are provided by the modeling, thanks to the scientific activities. And we don't know precisely what is the market value of this information, but it's not the business of scientists to build up a business model. The business model is the problem of people who want to make money with that. But for sure there is no management. We know there is pressure on the water resource. There is pressure on the water resource, stressed by the climate change and so on. But since there is this increased pressure on the water resource, there is a need for management. And there is no management without metrics. And if the metrics are not reliable, we cannot do anything, either for security nor for business. This is precisely why we address the question, we address the issue of the reliability. And additionally, of course, it has been said, there is the issue of operationality, there is the issue of infrastructure, there is the issue that was addressed yesterday of latency, and all this stuff has to be considered. It's a very difficult question that has to be constructed from the market side and from the research side, both simultaneously. Sure. Mm-hmm. We will agree. Okay, we agree. Okay, go ahead.
All right, a big thank you to our speakers. A round of applause. Thank you.
Please take your seats.
I'm ready for it, yeah.
Okay, we are about to start, so please, if you can take your seats. So I hope you enjoy your coffee break and you notice that we let you 10 minutes more because the second speaker will not be there today. So we have a bit more time. Nevertheless, it's our pleasure to introduce you to the next part of the agriculture session, which is focusing on irrigation and evapotranspiration. So I'm Raphaël Landrimont from the European Commission Joint Research Center, and I'm pleased to share the session with...
Yes, hi, I'm Radosław Goziński from DHI. Yes, so I think we'll start straight away. Our first speaker is ready, Steven Wonnik, who will tell us about new developments in the Vapor database.
Thank you. Still good morning, everyone. I'm going to present our experience in developing and using the FAO Vapor dataset, which we have been working on in the last 7 years. And you have already seen 2 other presentations on the Vapor data. About an hour ago, my colleague Carlis Salantis gave a presentation on using the thermal sharpening methods. And yesterday morning, Livia Peiser from FAO presented the keynote speech on the FAO Vapor. And there's also a poster presentation from Bert Koerver on the PyVapor. Well, Livia Peiser yesterday already introduced why Vapor is there. Water is an increasing problem, or water shortage is an increasing problem, and it's threatening the food security and the livelihoods of hundreds of millions already, and it's only going to increase with droughts increasing in frequency all over the world. And climate change will only make this worse. And agriculture is by far the biggest user of fresh water. It's also a cause of the water shortages in many areas, but it's also at risk of further shortages and droughts. And so far, in the last decades, it has not been very high on the political agenda, and also most farmers don't see water saving as a high priority. But this sentiment is clearly changing. Last month, the UN Water Conference took place, the first in 50 years again. It was co-hosted by the Dutch government. And also the fact that here there's so much attention now for thermal data as one of the solutions for water dealing with water scarcity also shows that the sentiment is changing, which is good. But good intentions need actionable data, and lack of information is a major issue in tackling these problems. And it's an issue for all stakeholders, from the highest level international policy makers to small-scale farmers. And remote sensing can play a big role in supplying this information. And that's why the FAO Vapor portal was set up, to map agricultural water productivity from the field scale to the global level. And its main data products are actual evapotranspiration and net primary production. And the data is produced with the ETLOOK model, which was developed by eLeaf. And an open source version of the model was released in 2016 under the name Vapor ETLOOK. And prior to its release, the soil moisture algorithm changed substantially, where it was switched from passive radar to land surface temperature. If you still look up the publications, the last publication was 2012 that actually still refers to the old setup. However, the whole model is well documented on the FAO Vapor portal, so there you can find all information on the latest configuration and setup of the model. And we're also working on a new publication to bring us up to date again, which will be done in the coming month. It uses the Penrose-Monteith equation to calculate evapotranspiration, and it runs with a daily frequency. So we already had several versions of the Vapor model and data. So the first version was released in 2016, followed by 2 other versions. The last update was in 2019, and gradually the data coverage increased. So you see the light green area, the whole of Africa and the Middle East, in version 2 is available at 250 meters, the dark green at 100 meter, and also the orange was later added to the 100 meter, and the dots represent high resolution areas at 30 meters, and these were also added over the course of the project. We're now working on version 3, and that is a massive increase in coverage. So the version 3 will have a global coverage, just 300 meters. Africa and the Middle East at 100 meter, and over 20 irrigation areas at 20 meter. Last week we delivered the continental, so the Africa and the Middle East data set to the Vapor portal, and it will be available soon. So I'm going to show some results also of the 100 meter product that we have just produced. But first, a few things on the changes compared to version 3. The data improved significantly, and there are 3 main changes behind that. First is a switch from MODIS to FIRST thermal data from 1,000 meters to 375. Then the implementation of a thermal sharpening method to enhance the land surface temperature resolution. And we also improved the algorithms to create daily inputs. The ETLOOK model itself only slightly changed. This is the part that calculates actually the evapotranspiration. So most of the changes were actually done in the preparation of the data before it enters the model. So here you see the effect of the changes in land surface temperature. So on the left you see the difference between MODIS, 1 kilometer, and FIRST, 375. These are not taken at the same time, so you cannot compare the temperature data. And the other 3 show the impact of the thermal sharpening from 375 to 100 and to 10 meters. And you can clearly see that it becomes possible to really distinguish the fields in this way. Another improvement were new smoothing methods to create the inputs, the daily inputs. And here you see 2 clips running. One is on the left is the original data with a lot of gaps. And on the right you see the results after smoothing. And on the high resolution areas we also implemented the gap filling approach to improve the data quality even further. And the graph below shows 3 points where from instantaneous observations we go to daily smoothen time series. What's also new in version 3 is the soil moisture. We have a relative soil moisture product, and it scales the soil moisture between field capacity and the wilting point, and it's applied as a stress factor on the evapotranspiration. And it always was part of the ETLOOK model as an internal variable, but this is the first time that we release it as a beta version to the wider public. And we're currently assessing how to convert it proper into actual soil moisture content. The data is very new, so we had very little time to look into it yet, so a colleague of ours had one day to come up with something. So he converted the relative soil moisture into actual soil moisture based on soil characteristics and soil maps. And here you can see the comparison with SMAP. So it's scaled to 9 kilometers. So on the right side is our soil moisture products, and on the left side the SMAP products. You see that the general patterns are nicely matching up. What we see is we are a little bit wetter, but we also have some doubts about the result of SMOP in the wet tropics. And in some parts we're clearly wetter, and that's where you can see, for example, if you look at the Nile Delta in Egypt, which is quite well visible in our data, but you cannot see in the SMOP data. And this becomes more apparent when you look at the details. So in this slide, you see two tiles, one in the Gezira irrigation scheme, and on the right now, our data at 100 meter, and on the left, SMOP at 9 kilometers, and Office de Niger on the bottom. And they should also start playing. So here you see the seasonal patterns, and you can clearly see the irrigated fields in the images, and also how they change over time. So the resolution really is a big improvement to other soil moisture products. And in the bottom you can see Office de Niger, also an irrigation scheme. And you see also the seasonal patterns in the soil moisture. And this is then the results for the evapotranspiration. So on the top right, the transpiration, we separate transpiration and evaporation. Transpiration for whole of Africa, first decade of May. And below that's the evaporation. And the left two images are zoomed in on an irrigation scheme in Egypt, a pivot irrigation scheme. And on the left you see version 2, and on the right version 3. And here you clearly see the difference. And version 3 is much sharper, and the ET is much higher. And that effect is fully due to the higher resolution in thermal data and the thermal sharpening, because the desert has a very large background effect. Here's some more detail of the evapotranspiration, 100 meter compared to the Fuse 1 kilometer product for the Bekaa Valley, an irrigation scheme in Lebanon. And these are the annual totals of evapotranspiration. And here you also see that with this resolution you can see much more detailed the irrigation scheme and the different fields. So an additional challenge to produce this data set for the whole of Africa was, first, the new methods are quite computationally heavy, and the amount of data is also a challenge on itself. So we had to rebuild our whole processing infrastructure in the clouds. When we did that, we also separated the model from the processing infrastructure in a modular design so that we could flexibly run it. And just some numbers, we processed for Africa at 100 meter more than 2 million Sentinel tiles. The FIRS data that we processed, well, we collected as SWATs, but then we converted to the Sentinel tiles for processing, are about 8.5 million. The preparation of the inputs for the model is actually most work and also creates most data. So it has created more than 80 million daily input files, and the output is about 32 million files. And those files are Sentinel tiles, 100 meter. And with Sentinel, we've of course first resampled to 100 meter before we start processing. We don't process at 10 meter. And after that, it's sent to FAO and aggregated over time to 10 daily. So I don't have time to show much applications. So this is just one application, but there are many applications for which WAPR data can be used. And this is mapping irrigation volumes. We do this in New South Wales, in Australia. And here you see an irrigation scheme, and the time series shows the irrigated water. And it's a comparison between the irrigation ET of the field and the natural, the background ET. And the elevated level of evapotranspiration are attributed to irrigation. So I think one of the lessons we also have learned is that a lot of governments particularly governments like the open source nature of the WAPR and the WAPR data, the WAPR model, because governments like to know on which basis they take the decisions. And transparency is important in this case, and particularly when it comes to the public domain. For example, when using it for enforcing water allocation rights, you have to account how you come to these results. And I think that's the strength of the WAPR and the WAPR method, is that it's very transparent how it's done. The other thing is more thermal data is better, and that's also why I'm here. We use a lot of thermal data and a lot of optical data. Basically, we use all freely available, well, not all, but many freely available satellites. And I think what we have shown, particularly with the new data, is that we can get very good results. But it will get much better if the new missions that are all being discussed here, data will become available. And there are two reasons. One is cloud cover. In some areas, and we map the whole world, and we cannot skip clouded areas, cloud cover is very persistent. We have areas where over a 5-year period we maybe have 10 valid observations. So you can imagine it's very hard to make good quality data. Radar can play a role here, but in general our experience is if optical and thermal data is available, it gives better results because it better represents the biophysical processes. So more overpasses increase the chance of collecting valid observations and better data. The other thing is model versus observation. So these new methods of enhancing the data, recreating the data, filling gaps are becoming increasingly better. And we get pretty good results with that. And they're all based on generalized trends and correlations. But the interesting things, what we want to know is where those correlations do not hold up. So where the fields that you're monitoring deviates from the general trend, because there it may be drying up faster, or it may be harvested. And if you don't see it, the method will not recreate it. So that's why more observations will give better results. And then my final point, assessing the quality of the data. It's challenging. A lot of people have been talking about validation, but our experience is that it's all very limited. Project-based, we have to validate the whole of Africa, and particularly Africa is challenging. And collecting that data often is difficult. It's project-based, it's short time series, they're not really aligned. And I think there we can do much better as a community to work more on good reference data. That will support development, and also it will make it easier to explain the products to the wider publics. So my conclusions, WAPR version 3 is a big improvement over the previous version. Much of that improvement comes from higher resolution thermal data and the enhancement techniques, and new thermal data will definitely improve the quality further. And we should put more effort into validation and explaining the quality of our products to the wider public. So our next step, we will release the higher resolution data, or WAPR portal will release the higher resolution data in the coming weeks, the 20 meter. The global 300 meter data set will be delivered during the summer, and we will also start with assessing and validating these data sets. And we're also looking for expanding the collaboration with other organizations. Now that we expanded to a global reach, we are also producing data for the United States, for Europe, for Australia, where there's a lot more validation data available. So if you're interested in collaborating and validating the data and making better WAPR products and WAPR data, then please contact us. Based on those results, we will further improve the ETLOOK model and also test other model applications, other models to compare the results against, so that we have a better idea how accurate it is. And we will release a long-term, low-resolution time series for climate risk assessments. And finally, most important, we're really looking forward to all the new thermal data that we're definitely going to integrate in our production for WAPR. It was very short. I could have shown a lot more, but I don't have time. But you can see it all on the WAPR portal, so please check it and use it. Thank you.
Thank you, Stephen. Really exciting. So the next speaker, unfortunately, could not be there today. So we will welcome the third speaker of the day, which is Pablo Zarco-Terrada. Pablo is a professor at the University of Melbourne and also a member of the Consejo Superior de Investigation in Spain. The floor is yours, Pablo.
Thank you. Okay, thank you very much. So I'll be talking about the need of high-resolution thermal data along with hyperspectral, when the objective is to detect water stress combined with biotic-induced stress, in other words, diseases. I think that the link between stomata closure, transpiration rates, evaporative cooling, and therefore on the temperature is something that it's quite widely accepted and well known. That was something proposed in the 60s and 70s by Jackson and others. And the reason why canopy temperature it's so critical for understanding transpiration rates and making decisions in irrigation and precision irrigation techniques is because of the link between those processes. With sensors that we collect, that we use to collect canopy temperature on a daily basis and over different type of species, like for example in olive, vineyard, or almond, we have already demonstrated, I mean the scientific community has demonstrated for a long time that the link exists between ground temperature and high resolution and transpiration rates and therefore on water potentials. The main issue or the complexity or the main problems that we find when we are trying to do those type of things is that we are dealing with species which are heterogeneous. We have a complex type of orchards, which is the typical in Mediterranean and semi-arid regions. And what we see on the image is a hyperspectral mosaic of around 50 centimeter resolutions where we can see very large differences in terms of soil background, shadows, and planting grids. We don't have uniform canopies, and that heterogeneity makes everything extremely difficult. We do have large soil background differences in not just a matter of kilometers, it's in a matter of a few meters. We can see that the background is extremely different from one place to another. We have within crown structural features that we see within the tree crowns, and that is typical even for the same species when they are different varieties planted at the same time. And we also see very large shadow effects. Obviously, that depends on the crown structure, the whole architecture of the orchard, and also the species and the variety or the cultivar that we are dealing or we are talking about. This is challenging in terms of species with low transpiration rates, as it is the case of, for example, olive or citrus, planted in grids with low percentage cover and with large bare soil or low vegetation background effects on the images that we are collecting. So it's very difficult, particularly if we are doing high resolution, for example, thermal data that is not as high as the tree crowns that we are trying to quantify or to detect. So the scientific community, again, has developed in practical means and with the objectives of making decisions in terms of irrigation, precision irrigation, deficit irrigation techniques to go from tree crown temperature, like the map that you can see there in a more than 1,000 hectare almond orchard that we collected using airborne thermal sensors, through techniques that normalize the canopy temperature by ambient conditions in order to calculate CWSI crop water stress index, a thermal-based index that is related to the transpiration rates and also demonstrated as a link with water potentials. By doing that, we go into maps of CWSI that can be used by growers to make when making decisions about irrigation doses and also frequencies. The community has demonstrated that we can do that in different species. I'm here showing relationships between CWSI, thermal-based indicator, and water potential. Mind you that those are very high resolution. I'm talking about 40, 50 centimeter pixel size. That means that we are targeting pure tree crowns. Therefore, we are dealing exclusively on transpiration rates and water potential at the tree level. And we can do that. We have seen that in different species, like, again, those which are very heterogeneous, which are difficult and complex, like almond, grapevines, olive, peach, or citrus. And that is the way, in practical means, in precision agriculture, precision irrigation, we are making decisions about how much water we need to apply. The main issue with the detection of diseases, which is the main focus of the presentation I'm making, but I needed to explain the water status and the assessment of water stress. It's because those changes in the evaporative cooling and the stomata closure or the transpiration rates are confounded by the presence of pathogens. Like, for example, in the case of vascular plant pathogens, they colonize and block the vascular system, and they interfere with water and nutrient flows. That means, and we can see there the way it's blocked, the xylem, and the way the water flow is reduced. Those are confounding effects. So when we are at large scale trying to map and to detect diseases at early stages, particularly vascular diseases, it's extremely important that we understand the water relations and that we understand the water status. Otherwise, we are going to make large errors in the assessment and in the detection of those particular plant diseases or plant pathogens. I'm talking in particular about Verticillium daliae and Xylella fastidiosa. Both are vascular plant pathogens that generate similar symptoms. In fact, the farmers feel that what they have is a water stress at the beginning, because what they are getting is the desiccation, wilting of the leaves, and typically observed in cases of water stress cases. Verticillium daliae, it's a global issue. That's the presence of Verticillium worldwide, and it's in Mediterranean regions is one of the biggest problems in a number of species. I'm not talking about one in particular. Being in Italy here today, it's easy, or well, maybe difficult to talk about Xylella fastidiosa because everyone knows about the big problems that Xylella fastidiosa is creating in southern Italy, particularly destroying the olive industry with more than 20 million trees killed since the identification of Xylella in southern Italy back in around 2013, but originally arriving from Costa Rica in 2008. It's projected that losses will go up to more than 5 billion per year if Xylella fastidiosa is not contained successfully in southern Italy. It's already in mainland Spain and in the Balearic Islands. And the problem is not only the olive industry, because it's affecting also almond orchards, for example, in Spain, and several other species, is that in principle there are more than 500 species that could be under threat, and therefore it's an extremely huge problem. The objectives that we try to achieve, and this is part of the work I started doing when I was at the European Commission at JRC, as part of 2 different projects, now 3. Ponte project, 3 European projects, Ponte, X Factors, and then recently launched Bexil. And the objective is understanding the dynamics from the remote sensing perspective, obviously, understanding the dynamics of thermal and hyperspectral based traits underwater stress, as a function of stress levels and across species, because that is extremely important when we are trying to disentangle biotic versus abiotic-induced stress to improve the disease detection. If we imagine, if we imagine southern Italy, Puglia, anyone been there and walking around in thousands and thousands of hectares of olive orchards, what you see is a mixture of everything. It's a mixture of different varieties, different soil types, different management practices, different irrigation systems, diseases, Xylella, and also water stress. So everything is put together in a very complex conditions, and by disentangling biotic and abiotic stress, we hope that we can improve the disease detection. So airborne thermal and hyperspectral data has been collected since 2016, initially in southern Italy for a few years, and then also in the Balearic Islands and also in mainland Spain, in Alicante, where Xylella fastidiosa was identified. And the approach, when at the beginning we didn't know whether we were able to detect Xylella at earlier stages, because detecting Xylella once the tree is dead, it's very easy. With NDVI or something else, you can just find it. But the objective and the challenge was to detect it at earlier stages before our eyes could see anything to prevent the spread, was to use plant biochemistry and thermal data to put together into a scheme that would allow us to detect the disease as soon as possible. So we have been flying hyperspectral data over infected areas to retrieve the plant biochemistry, to quantify solar-induced fluorescence using sub-nanometer full width of max resolution hyperspectral images, and also narrow band around 5 to 6 nanometers full width of max hyperspectral imagers, because of the relationship and the link between SIF and photosynthesis in affected vegetation. And that is an example of the spectra that we get with the sub-nanometer hyperspectral imager that we've been flying. And again, as I said, is putting together thermal information that is related to transpiration rates and the reduction of the transpiration due to the presence of the disease, the pathogen, and also due to the presence of water stress levels, biochemical constituents in order to assess the physiology as a whole, understanding the dynamics of those biochemical constituents, depending on the stress levels, both biotic and abiotic, and also chlorophyll, solar-induced fluorescence. Those are examples of the images that we've been collecting over those areas. So we're talking about scanning more than 1 million trees using these hyperspectral and thermal images at 50, 60 centimeter resolutions, because we needed to identify single tree crowns to do the full quantification of parameters at the tree level, without any effects due to background or soil. And those are examples of the typical images with the hyperspectral sensor, and then the same but with thermal, where when we quantify the pure tree crown temperature and then apply the algorithms, then we get water stress levels using the thermal-based water stress indicator. The results were quite intriguing and quite interesting when we were looking only at non-infected trees. Here is the dynamics of the water stress without the presence of any pathogen. Before I click here, because it's going to start moving, the arrows on the left and the right, which are vertical, will show the stress levels. As they grow, will mean more water stress. And the bars, the horizontal bars, are the importance of the water, of each of those indicators to explain the water stress levels. So Interestingly, obviously, canopy temperature and thermal-based indicator is the most important when we are trying to explain water stress. But as water stress increases, canopy temperature is less important, and other biochemical constituents also show sensitivity to the water stress. That makes sense, but the important thing is that this is species dependent, and we found that depending on the species, obviously because of the physiology and the way trees react to water stress, that dynamics changes. I'm finishing now. So as water stress increases, the relative importance of thermal decreases. At earlier stages, thermal is the most important water stress indicator. That is critical because when we are interested in detecting a stress at earlier stages, thermal is the #1 indicator, as should be. After thermal, hyperspectral traits are highly sensitive to water stress. I'm talking about total coranoids, xanthophylls, and anthocyanins. So quantifying those parameters, those biochemical constituents, increase the chances of detecting water stress as stress increases. And both thermal and solar-induced fluorescence are extremely important because one of them is related to transpiration, the other one to photosynthesis. And they have inverse trends with increasing of water stress levels. When we put into the context the disease, I mean the pathogens, then we find something extremely interesting, which is that there are specific spectral-based indicators which are common across a species and other ones which are specific to the species. And that is, again, very critical because different species have different ways of dealing with the pathogen, and the physiological changes are different. We shouldn't expect that the same physiological changes will be the same for all the species. Some conclusions, because Rafael is looking at me. I think that we've made good progress in the past 20, 25 years with thermal and hyperspectral for biotic-induced stress. We are now talking about over-accuracies and kappas which are acceptable. We are talking about 90% over-accuracies with low errors of false positives and false negatives. And usually, it's remote sensing the one detecting the trees infected before the plant pathologists in the field can detect them. Thermal and any thermal-based indicator like CWSI, it's a direct link with transpiration or water stress. That's something that we know. But the important thing is that SIF, solar-induced fluorescence, and plant pigments with rapid dynamics, I'm talking about xanthophylls or, for example, anthocyanins as well, they contribute very much to their stress detection, both in the case of only stress, only water stress, and also with the presence of pathogens. Understanding the abiotic status is critical if we want to do a better detection of diseases. So it's extremely important for this particular species in the context of semi-arid regions that we understand the abiotic component before we attempt to detect diseases. And finally, thermal and hyperspectral need to go together. I think this is a conclusion that I like to highlight, particularly in this context and the venue here with this community. They are needed for water stress and disease detection. I don't think that we can do any of this with only thermal or with only thermal and maybe a couple of indices like NDVI or something else. We need to know the full physiology in addition to canopy temperature as indicator of transpiration rates to do a good job in the detection of both water stress and early detection of diseases. And that's all. Thank you.
Okay, thank you very much. Next speaker is Gabriel Eze from Planetech, who introduced us to the new EU Africa Explorers project.
There will be time for questions afterwards.
It is an honor and pleasure to share with you one of our contributions at Planetech Italia in increasing the adoption of thermal Earth data in agriculture. This project is under EU Africa Explorer Framework, or VISA, and the high-level objective is to evaluate the use of open source water resource management models together with thermal Earth observation data in generating consumption insights, the strength of which is supporting producers and policymakers to improve water management in irrigation farming. This project is funded by ESA and led by Planetech Italia. To ensure success, we adopted an open innovation approach because it is interactive by nature. The collection and consolidation of data to ensure that both the process and the needed requirement were determined and organized with the end users in mind. Secondly, in forming a consortium, we involved representative actors in science, policy, industry, and end users. For science, we have Mediterranean Agronomic Institute of Bari, also known as CM Bari. For policy, National Authority for Remote Sensing and Space Sciences in Egypt. For industry, Planetech Italia and Planetech Hellas. And for the end user, October 6th for agricultural projects. The concurrent presence of these representative entities will play a key role in enabling a co-creation and co-design process in which all the actors cooperate to foster socio-economic and ecological development. The agricultural sector is already the largest user of water resources, accounting for roughly 70% of all fresh water withdrawals globally, and requires even more water to sustain the continuous demand for food and biomass fostered by population growth and changes in rainfall and temperature patterns caused by climate change. This is a leading cause of an increase in competition and conflict among users and sectors, especially in water-limited areas for the use of these important resources. For a challenge as consequential as this, the frontline action to sustainable solution must include a responsive mechanism for measuring how much of this resource is added and how much is withdrawn. Because if you cannot measure something, it becomes really difficult to manage it. In order to reposition the agricultural sector for better water management, this experiment seeks to carry out a thorough re-evaluation of water losses through evaporation from soil and transpiration from crops, by crops. This precision measurement of moisture presents a unique approach for water management in irrigation farming. And to do so at scale, accurately and affordably, thermal Earth observation data offers an opportunity to precisely estimate water requirements on a crop-by-crop basis and planning a more efficient irrigation schedule. With better monitoring of water consumption, we can minimize vulnerabilities in the sector and thereby improving farmers' resilience to climate change and other related uncertainties. EO Africa Water Resource Management Project aims to validate open source models for predicting actual evapotranspiration on a farm field using a comparative EO-derived data. Egypt is facing a severe water shortage, hence why it made logical sense to demonstrate the potential of thermal Earth observation data in El Salhia under the Sharqiya Governorate. The demo site is a 13,800 hectares of farmland, housing 120 irrigation pivots. In today's Egypt, existing data on water use and the estimation of usage efficiency are rough estimates and not based on field observation. Due to this lack of precise data, irrigation management in the country is challenging. Given the country's rapidly rising population, the need for accurately estimating the water requirement for various crops to fulfill the country's increasing food demand cannot be overemphasized. Another reason for this selection is that the participating public and private stakeholders are on the same page. They are also keen to share their knowledge, local knowledge, and data with the project. This is an irresistible opportunity for us in mainstreaming the use of EO data in the country. One of the main bottlenecks in water losses due to failure to rationalize water consumption in an all-consuming sector like agriculture. In this context, employing thermal earth observation data to accurately estimate the effective crop water consumption represented by the actual evapotranspiration will assist decision makers in creating models to improve water usage efficiency. In a nutshell, our objective in this project is water accounting, comparing total water usage through the water supply chain to the actual water consumption through evapotranspiration, along with total and net crop yields to determine beneficial and non-beneficial agricultural water needs. This is a critical component for water management in irrigation systems, water resource planning, allocation, and use efficiency studies. The output product is an EO-driven decision support system specifically designed for irrigation management purposes. Since the outcome of a model is as good as the quality of the input data, ground truth sampling will be synchronized with the satellite over passing time, expected to be once every 15 days. The number of observations and measurement points location is made to best represent the area of interest at different microclimates. Estimation and mapping of crops evapotranspiration will take into account the EO-derived crop coefficient and water stress index. The spatial resolution needs to be high enough to provide real utility towards users' practice. At the same time, it should be a fair trade-off between accuracy and exploitability. Validation will surely require non-EO data. As such, this will be clearly defined. So far, preliminary requirements have been collected. The stakeholders proposed we adopt a water resource management model based on the so-called standalone remote sensing approach to estimate the reference evapotranspiration. It is capable of estimating and mapping actual crop evapotranspiration using EO-derived crop coefficient and crop water stress index. Our current project activities are focused on satellite data acquisition from Sentinel-2, Prisma, and Nmap. Setting up in-field campaign in order to organize in-situ data measurements on the same day of overpass of the satellites above mentioned. Analysis of state-of-the-art and initial testing of hyperspectral data for retrieval of evapotranspiration product. Next steps after that will be further requirements will be considered, also from a policy perspective. However, as agreed with the stakeholders, priority will be given to the fulfillment of requirements linked with the current modus operandi. Thank you for your time and attention.
Okay, we have time for one question. You can stay, sorry, because you were in time. So is there any quick question? Or not quick? No? Okay, so we can move to the next presentation then. Thank you very much, Eze. So we move from Egypt to California. For the next speaker, I'm pleased to welcome Oscar Rosario for University of Naples. Federico Due will present his work about integration thermal and optical data for mapping crop evapotranspiration. Please, the floor is yours.
Thank you for introduction. Good morning to everyone. I'm Oscar Belfiore. I'm research fellow at University of Naples, and I'm so glad to be here today. And then I want to discuss about crop evapotranspiration mapping by means the integration of thermal and optical models over irrigated tree crops in California. So that's the context. I mean, as you well know, crop evapotranspiration, these accurate estimates of crop evapotranspiration is one of the main issue nowadays. And then, especially when we want to, monitor the water consumption in agriculture, right? So that's the point. I mean, what we need. The best idea, the best scenario is to have daily ET maps at a field scale. And you know, we can do that by using thermal data, and that allows us to get good results, I mean, by using surface energy balance models, you know? And then I've seen great presentation yesterday where we have tons of models and algorithms to get, I mean, thermal sharpening, and then you get thermal data on a daily basis. But especially here in Italy, along to the high temporal resolution, we need high spatial resolution, you know, because here we have high fragmented parcel, and then often when we use, for example, Landsat data, we are not able to take advantages about thermal data in this context. And then, in addition, we have another technical problems. I mean, it's not easy to monitor daily evapotranspiration with passive sensor like Landsat 8 due to revisit time. And then often we are not able to detect some changes in surface moisture condition of crop phenology in a given time interval. In particular, when we have in particular overcast persistent conditions, right? So to address this challenge, we can easily implement common gap filling methods, such as the actual ETO ratio that allows us to interpolate ET across two acquisitions, and that method allows us to get advantages in an operational context. But you know, when we have wide range between two acquisitions, right, we are not able to follow the node dynamics and linearly dynamics of ET, especially when we are working on sparse canopy conditions. So what we did, I mean, we try to integrate thermal and optical model based in order to get dense time series of ET maps. In detail, we integrate this Alexi model based on Landsat thermal and optical data, along with Shuttleworth-Wallace ET model based on Sentinel-2 data. So where we are, I mean, I used two datasets coming from GRAPEX and TREX projects, kindly provided by Bill Kusta's research group. I spent great six months there. And then where respectively we have tons of instruments in vineyards and almond orchards in California. Here you can see the location of the test sites. I'm sorry, today I'm going to show you some preliminary results only for 2 of them. I mean, WWF is an almond orchard located in Voderland, close to Davis, I mean close to Sacramento area, with irrigated almond orchards, and Ripperdan 760 with vineyards included in GRAPEC project, located close to Fresno in Central Valley. For both of them, we have field instruments like flux tower data, where we are able to estimate ET by using eddy covariance method, and then to validate thermal and optical models outcomes. So here, just a quick overview about the algorithms used in this study. I mean, here you can see the Alexi-DisAlexi framework. As you well know, it allows us to estimate evaporation from soil and transpiration from crops, starting from TSEB algorithms. And by using, in this framework, different satellite, and then we are able to estimate ET mapping with multiple sensor and multiple scale approach. Okay. Here you can see instead the spectral-based model, I mean Shuttleworth-Wallace, based on Sentinel-2, where it's a physical-based model that allows us to estimate ET on a daily basis. We don't need upscaling. And then we take advantages by using Sentinel-2 data. First of all, thanks to spatial resolution on Sentinel-2 data, as you well know, 10 to 20 meters, and high revisit time, 5 days, taking account Sentinel-2A, Sentinel-2B. That model and that input data allows us to describe biophysical crop parameters. I mean, thanks to the albedo and leaf area index. And here you can see a new framework that which includes the Optron model. Optron model proposed by Sadeghi in 2017 allows us to estimate relative soil water content, and we used the Optron model in Shuttleworth-Wallace framework in order to modulate leaf and soil resistances, in order to get and split evaporation from soil and transpiration from crops without thermal data, okay? So we already tested this kind of approach in GRAPEC's campaign 2018, where we got good results over irrigated vineyards in California, again in Ripperdan, but in other test sites with 4 blocks with 4 flux tower. And in addition, let me focus on detail about this framework. I mean, in this framework, we try to link the substrate and canopy resistance with shortwave infrared observation. Optron model is based on, it's a trapezoidal approach. It's based on STR and NDVI. NDVI, you well know this famous index, but STR is a new index based on shortwave infrared that allows us to take into account soil water status. I mean, shortwave infrared is based on shortwave observation, and then we got wet condition with high values of STR and dry condition with low values of STR. So taking account the STR and DVI space for each pixel for given Sentinel-2 acquisition, we can estimate and compute the W index, which stands for relative soil water content. When we have values of W index equal to 1, we have in wet condition, and then instead when we have low values of W index, we are in dry condition. So we can draw wet age and dry age like we did for Totram, for example, right? But in this way, in this case, by using STR. So we can link those limits with leaf resistance and soil resistance. For example, we got high values of leaf resistance when we have pixel in close to dry age, while we have low values of leaf resistance and soil resistance when we have close to wet age, okay? So, as I said before, we can estimate W index pixel by pixel for each Sentinel-2 images, but we need an Optron parameterization, you see, in order to take into account spatial and temporal domains, in order to take into account the spatial and temporal variability of soil and plant water status ensemble, right? So for sure we can use Sentinel-2 data, and the best option is to use a long time series of STR and DVI by using for sure Sentinel-2 images. And another thing is to use only cropland pixel in order to avoid to put in STR and DVI space some noise. And in this case, we used a California Natural Resources Agency land cover map, and then with a spatial domain of 8 kilometers per 8 kilometers for each test site. So here you can see some preliminary results about this kind of framework for WWF, which means Almond test sites. On the left, you can see in green, I mean, the comparison with ET from Flux Tower on x-axis and y-axis with ET from Shuttleworth-Wallace based on Sentinel-2 data. On the right in red, you can see for the same dates, I mean, we have 53 acquisitions for Sentinel-2 data. And then in red, you can see the same dates taking account this Alexi and interpolated by ET-ETO fraction. As you can see here, we have more or less similar results, even if we have some weird outliers at the beginning of April in 2022. Okay. So we did the same for Ripperdan, again in vineyards close to Fresno in Central Valley. And here you can see again the same plots with more or less similar results between the two framework. As you can see here on the bottom, the temporal evolution of ET modeled observed ones, and the blue line is the leaf array index, derived by using artificial neural network implemented in SNAP software. Okay. Here you can see the comparison of the ensemble of this Alexi and Shuttleworth-Wallace, and in green you can see more than 82 acquisitions, taking account both framework and based on Landsat and Sentinel-2 data, with a good agreement. Instead, in red, you can see only this Alexi, and for sure, for the same time period, we have less acquisitions. I mean, just 35, and then we can have some problems. Especially in period when we don't have enough cloud-free images, right? The same for Ripperdan, where we get for 2021 and 2022 144 acquisition based on Landsat and Sentinel-2 data. In red, this Alexi again with so only with Landsat acquisition. And again, you can see when we have cloudy, during the winter months, we have not so much cloud-free acquisitions. Last but not least, you can see here the comparison of the full integration of this Alexi, Shuttleworth-Wallace based on Sentinel-2, and the ET-ETO fraction. And then in this way, we can interpolate ET on a daily basis for 2021 and 2022. And again, more or less, we got similar results between the two frameworks. The same for almonds, orchards, and for vineyards in Ripperdan. So to conclude, I mean, these Alexi and Shuttleworth-Wallace models confirm their reliability for the estimation of ET over irrigated tree crops. And the integration on thermal and spectral models is promising approach for the production of ET maps, but I mean, the ETO fraction interpolation method still offer advantages in operational context. I mean, for example, if you want to provide irrigation scheduling at farm scale to the farmers. So we are still fighting on this task. And I mean, for a robust validation, we have to homogenize the input data. And we are thinking about to use HLS dataset in order to homogenize Earth observation input data. And do the same also for weather data. And then by using for both framework the same weather variables, I mean by using CFSR or ERA5. And at the end, we want just to test additional gap filling methods, maybe try to gap filling and interpolate the interpolation of input Earth observation data instead of ET outcomes. Thank you.
Okay, thank you very much. So before we go into the discussions and question and answers, we have last speaker, and it's Gilles Boulet from CESBio.
Hi, everyone. So I'm going to present today the work. I've been combining two works, actually, one done by a PhD student who just submitted his studies, Samuel Mwangi, and a postdoc who finished his postdoc last year, Mohamed Zied Sassi. Yesterday, we've been talking a lot about the relationship between the canopy distribution of surface temperature and the radiative surface temperature as observed by the satellite, so the directional issue. Today, we have been speaking a lot about the relationship between the land surface temperature and evapotranspiration. So today I'm going to actually bring together both themes, both issues, with the main questions that regardless of the view angle or the view geometry acquisition of the land surface temperature, we want to have the same surface energy budget. So how can we relate the surface energy budget equation on mostly evaporation or latent heat inside this surface energy budget with the viewing geometry on the sun target sensor viewing geometry. So we are going to look at that issue in both a forward and inverse way. That is, can we, for a given water status, be able to simulate the landscape of temperature at the canopy level? And we are going to look at it in an inverse way, that giving a specific acquisition in a specific view angle, can we retrieve some evapotranspiration very robustly? So to actually do both, we have a range of models, which are either land surface models, combining a surface energy budget equation and a water budget equation. And we have, so that's a forward mode. And for the surface energy budget, we are using land surface temperature as an input to force or constrain the surface energy budget equation. So usually for products, we are using inverse models. They are usually more simple. They are usually one layer or two layers or a few layers. And for forward models, we tend to have available more complex models with sometimes 3D canopies. So in the forward mode, I will give an example here for isolated rain-fed olive tree in Tunisia. What we wanted to answer is that, are we able to actually simulate the distribution of land surface temperature across the canopy? So to do so, we equipped our flux tower with several cameras in several configurations to try to sample the distribution of temperature across the canopy. And what we did is that, okay, we usually use one-dimensional models, such as the ISBA land surface model, which is used for the French Met Office. And we have as well available more complex models which are treating the canopy as a 3D system, especially for the radiation budget. So in our case, we employed the MAESPA land surface models. In this site, we had flux measurements and we have sap flow measurements, so we were able to simulate both evapotranspiration and transpiration and have an observation for the system. You can see we have a dry year, which is 2013, and we have a much wetter year, which is 2014. And MAESPA was much better in actually simulating the variability between these two years in terms of evapotranspiration and transpiration compared to ISBA. So now that we have looked at the performance of the model in simulated total fluxes or its components, we wanted to look at how good they are to simulate the average canopy temperature. So remember, the canopy temperature, the average is really well sampled by all those cameras. And you can see actually that the fact that ISBA is actually underestimating the water stress of the vegetation, which you can see in the transpiration in 2013. You can directly look at the consistency with the fact that it is underestimating the vegetation temperature, for instance, while MAESPA is actually much better in doing so. So this is for the average canopy temperature, but if we are going to have like all the satellites we've been speaking yesterday, we are going to have a wide range of acquisition angles. Are we actually able to simulate accurately the distribution of the temperature as observed by the cameras? In fact, not. Even so, MAESPA is actually having a 3D radiative transfer model and simulating a lot of land surface temperature inside the canopy. The range of simulated land surface temperature is much smaller than what actually is sampled by the cameras, which means that there is still a long way to go to have a very accurate three-dimensional surface energy budget model to simulate this kind of thing. So this was for the forward mode. Like, we have a land surface model driven by rain, for instance, which is adapted to simulate the health of a canopy according to rainfall events. Now, if we are moving to like irrigated perimeters, usually you don't really know what is the input of water, so you tend to apply more inverse mode type of surface energy budget model, so to use LST. But the question was that, okay, LST is observed again in different configurations. So can we retrieve actually the distribution of the individual components, or at least the extremums, from a single LST observation through a surface energy budget model? So what we did again, we used that small cameras with Verdu irrigated vineyards flux station in Spain during the Liège campaign. And what we did is that we used these cameras to actually sample the minimum and the maximum temperatures for the soil and the vegetation, that is the shaded soil, the shaded vegetation, the sunlit vegetation, and the sunlit soil, and then to reconstruct using different radiative transfer model with directional capability, reconstruct surface temperature in any kind of direction. So we used DART, for instance, to do so, because it is one of the most complex radiative transfer model which is actually able to simulate that. And what we did is that we make a change in a two-source surface energy budget model. The two-source classically is one soil and one vegetation source, and we moved to a four-source, just adding a few information on the canopy itself, the geometry of the canopy. And instead of having two surface energy budget to solve, we have four to solve, which are related to the shaded soils, the sunlit soils, the shaded vegetation, and the sunlit vegetation. So we evolved that, and then we compare it. So, of course, with a nadir acquisition, the performance in retrieving the sensible heat and the latent heat is not that different between both models. We have very similar performance. Here is in watt per square meter, and below you have in millimeter per day across the entire season. But if you are looking at the LST reconstruction, of course, by using a four-source model, you can better simulate the heterogeneity of land surface temperature inside the canopy. And we checked that the raw model version of SPERS 4 is actually very similar to what DART is simulating in terms of directional temperature, given the element surface temperatures that are sampled by the cameras. And of course, usual 1D models are using a very homogeneous radiative transfer model, and they are not able to see that. Now, how does it translate into a difference between the latent heat and the sensible heat, so the surface energy budget elements between off-nadir looking sensor and a nadir looking sensor? So these are those radius plots. You can see that for two dates that were simulated using DART, we reduce a lot the discrepancy between the surface energy budget that is retrieved nadir and off-nadir using the new four-component configuration compared to the classical two-source configuration, which is the one that is used for TSEB as well, for instance. Furthermore, we say, okay, like this is a reconstructed surface temperature. What about the actual temperatures that are sampled by the camera? So we actually compared the temperature time series that is retrieved from the model from a given brightness temperature to reconstruct what are the extremums, so the sunlit vegetation, the shaded vegetation, and the sunlit soil. And you can see that altogether it's fairly realistic. So you can actually reconstruct the canopy landscape of temperature. Up. Oops. Yes. So in conclusion, so for the forward method, it's actually difficult to build a 3D demonstrator for thermal infrared. That is a coupling between land surface model and a radiative transfer model. So the current work is to develop a version of energy budget version of the DART three-dimensional model. But what we are missing actually is 3D turbulent fluxes. So this is actually a fairly difficult task. We probably will have to couple it with a large eddy simulation kind of model. And what we checked as well is that we have a better consistency of surface energy budget retrievals when we are using a four-component model compared to the classical two-source model, when you know actually the crop geometry, which is the only difference in terms of input data between the two-source model and the four-source model. So as a reminder, those are results that were presented earlier. What we actually checked with this new model is that it improved two things. One, we had a better partitioning, like it improved the partitioning between evaporation and transpiration, and we had a better transpiration simulation for our charts. And the second thing is that it improves the consistency when you go from one angle to the other. Like in Trishna, we are going to have one day an acquisition in one angle, another day a complete different angle. If you don't take into account this change of viewing acquisition, you will end up into the left part is the SPERS one, which is something that is very different because it's not accounting for directional properties of the surface. But when you are using the four components, you have something that is consistent. So maybe it has not the best performance in latent heat retrieval, but at least it will be consistent from one acquisition to the other, which is a very important point. And that's it.
Okay, thank you for finishing on time. So we have actually time for some specific questions to Gilles before we go to the general discussion session.
Microphone. Can we bring a microphone here in front? Sorry, because otherwise people cannot hear. Maybe can you stand, Jose?
I can repeat the question, maybe.
It's coming.
It's coming.
I wonder if, because the vineyard is very small, if the results can depend on this or not. Or
on what, sorry?
On the size of the vineyard, because it was very small, what you saw in the image, no?
I don't get, sorry.
No, I say that the size of the vineyard is very small.
Ah, yes, no, that's the beginning. Sorry, I took this photo when we installed it, actually. So that's the beginning of the season. So it's growing to a full canopy. Yeah. But it is indeed, in that site, you have a lot of bare soil, interspace bare soil, because it's originally a rain-fed vineyard that has been converted to drip irrigation. So that's why the rows are quite wide, actually. But that's only the beginning when we install the equipment. Yeah.
Okay. I see no more questions, but I have one question. Do you see the potential of using the four-source modules in more operational setting with satellites, or do you really need such accurate geometry that it's only for experiments?
Yes, actually, that's I skip one line for my conclusion.
Yes.
Thanks.
Yes.
Yeah, in Trishna, what we are thinking about is that we are going to deliver products. Of course, for product, we have been talking a lot this morning about the mismatch between the atmospheric forcing and the resolution, so that you cannot use this kind of model. But we are going to develop a knowledge hub or toolbox as well, so that if a farmer, like for instance, people growing wine, usually they have a local meteorological station, they know the wine, so they can use the LST and they can combine it with this kind of model to actually perform some simulation of evaporation, transpiration on individual temperature. Yeah, thanks for that.
Okay, thank you very much. So now we can applaud it for all the speakers also. And can I call all the speakers to join us for the discussion and the question? The last 10 minutes before lunch. Okay, so let's start. Who wants to start with a question?
Okay, so maybe I'll start again. Yeah, I have a question to Steven, because you talked about the 100-meter vapor product, and then you mentioned very briefly the 20-meter product as well. Is it based on sharpened virs, or do you use Landsat, or combination of the two?
There are about 20 areas, and in some areas, in most areas we use spheres, thermal sharpened, and in a few areas we use Landsat. We don't mix them.
Any question in the audience? Yes, I see a hand over there.
Sorry, I'm not an expert on this field, but I have a general question for this session. I've seen that there is a use of ancillary data from numerical models, etc. What is the impact of going to tens of meters with the satellite data and still using models like the ERA5 that are 37 kilometers, etc.? There is is it worth? There is a budget, an error budget on this. Is it worth to go to high resolution when you still do not have for this field high resolution forcing for other variables, the meteorological variables, for example?
Well, this is exactly why for products in Trishna we are not using models that are using a lot of meteorological input data.
Okay, so the main model is a contextual model, EVASPA, that Albert has been presenting. And the only input data in terms of meteorology is incoming radiation. Okay, so you have the scale. It's still a problem to evaluate. He has been insisting on that this morning, but it is less difficult than having a full climate forcing at 100 meters. Okay, but more complex models are still useful because, as I said, some perimeters are equipped with local meteorological station, so they can use the future high resolution land surface temperature data with local knowledge in terms of climate forcing. So it's still useful, I think.
I also like to respond to that. I think you also have to keep in mind the purpose for which you make the data and the scale. So the ERA5 is a low resolution, but if you produce the data on a global scale, you have no alternative sources that you can use. There are no other meteorological sources that you can implement at that scale. So therefore, we have to use these global models also for consistency. Otherwise, you have a lot of problem in comparing different data sets, and that's something you will see when you make a global scale. If you go to very high resolution, then you can switch also to local measurements, of course. But that is not always better because they're not always in the right way implemented or situated at the right place. So that also gives its own challenges. So, but in general, we're quite happy with the ERA5 products, and they're globally very consistent and also give a good result.
Yeah, I have this is Ralph Basilio, JPL. I have a question for Pablo on the plant pathogens. So over the last day and a half, we've obviously heard a lot about vegetation indices, specifically NDVI. I was pleasantly surprised to see solar-induced chlorophyll fluorescence. And I was just wanting to get maybe a little bit more information about how you're using that. You know, my experience has been we use it as a proxy for gross primary production. But I'd like to maybe better understand how you use SIF in looking at plant diseases. So could you elaborate on that a little bit, please?
Sure. So the results I presented here are coming from flying 2 hyperspectral sensors and 1 thermal camera, everything in tandem on the aircraft. And the sub-nanometer hyperspectral imager is more for research purposes and to evaluate algorithms for the retrieval of chlorophyll fluorescence using the Fraunhofer lines and the 2 oxygen features. From narrowband hyperspectral imagers, which I'm talking about 5 to 6 nanometers full width of max, we have demonstrated that we can still retrieve part of the chlorophyll fluorescence emission, and that is compatible with the retrieval of the biochemical constituents that we do from the reflectance data from the hyperspectral imager. So what we normally do is to fly over these areas, which are either infected or with variability in terms of water stress, and then we process thermal data separately, and then the hyperspectral data from the radiance, we quantify chlorophyll fluorescence using the fluorescence infilling method, and we quantify biochemical constituents using model inversion methods. And then what we try to do is to evaluate using machine learning and other models what is the importance of each of those traits. Some of them are more dynamic than others, but we wanted to understand in the context of the early detection of stress, because that's another thing I didn't really mention that much, is that our main objective is the early detection, pre-visual, when people walking around cannot see the symptoms. We could see that the most important traits that could detect the presence of the disease with symptoms which are non-visual were canopy temperature and then chlorophyll fluorescence, in addition to some of the other plant traits like xanthophylls and anthocyanins. Now, how can we use it in the future? That is a different story. What we wanted to find out is whether those traits, any of them, it's sensitive and how much to the presence of the disease, I mean the pathogen, and the symptoms that are caused by the pathogen. But we treat it in that way. We quantify all the different parameters. We quantify by model inversion methods all the traits, and then we evaluate which of them is more sensitive to the biotic-induced stress.
Okay, we are reaching the end of the time, or if there is a burning question, it's no or never. No? So can we please applaud again all the speakers? Thank you very much. So now it's time to close this very interesting session. We've traveled a bit in the session from Stephen showing us the nice products that are being produced now at global and continental scale. Pablo with some phytopathology and also highlighting the fact that thermal and hyperspectral should be used in synergy. Then we had Gabriel showing us the water stress in Egypt. We then moved to California, where we saw the Optram approach and the nice work you've been doing. And then Gilles conclude with highlighting the challenge to build a 3D demonstrator for thermal data. So again, thank you all. Enjoy your lunch, and thank you also for my co-chair. So thank you a lot. Thank you.
Grazie, inutilissima.
Hello, yes. Hi, welcome back. If you can just take your seat, please, so that we can finish in time.
Hello, everyone. I'm Emmanuel Autrette, and I'm the co-chair of this session. I'm an oceanographer, and I work at Ifremer in France, in Brest.
Hi, I'm Gilles Boulet. I am working in India right now, actually, and I am working for the Ecosystem Stress Group of Trishna Mission. So we are going to start now. So this session is a mixture of ecosystem stress at the beginning on coastal, at the end, 3-3, and we are starting with European Ecosystem Stress Hub Phase 2 by Tian Hu.
Okay, thank you. So I will start, everybody. So good afternoon. I hope you guys enjoy the lunch. So my talk today is about our second phase of the European Eco-Stress Hub. I mean, the acronym for this project is called, for the second phase is called Uranus, and the subtitle is Thermal Infrared Remote Sensing of Terrestrial Ecosystem Processes. Basically, I'm going to cover two parts in this talk. The first one is a brief conclusion of our first phase of the EH project. And the second phase is some brief introduction about our preliminary results of the second phase. So here, from this schematic graph, we can see that this is a very simple conceptualization of the terrestrial ecosystem. There are three important components in the terrestrial ecosystem. The first one is the atmospheric water budget. This is the demand of the evapotranspiration. And the second one is the solar radiation. This is the driver. Basically, this is the engine of the evapotranspiration in the terrestrial ecosystem. And the last one is the soil moisture. This is the fuel for this evapotranspiration. I mean, actually, in thermal infrared remote sensing, normally we use net surface temperature as a proxy of the soil moisture content. And through this kind of surface edge balance process, we can invert the canopy stomach conductance, and then we can couple the surface edge balance process with the carbon cycle. That's why we call it ecosystem functioning. As the right-hand side, we can see two different or contrasting biomes. The upper right is over the humid ecosystem, and the down right is over the arid ecosystem. I mean, the blue dot is the radiation, and the green and red dots are the evapotranspiration. We can see that over this kind of humid ecosystem, the diurnal cycle of radiation and evapotranspiration are very symmetric to each other. That means actually the temperature, I mean, basically the canopy stomach control is not that, what should I say, enormous, or the effect is not that much. So that's why this symmetry is quite dominant. But when it comes to the arid ecosystem, because of the water stress and water limited condition, there's very strong stomatal regulation induced by water stress. And you can see that the asymmetry is quite enormous in this kind of arid ecosystem. That's why in this kind of arid ecosystem, we need LST to inject the stomatal conductance into the surface edge balance, and then subsequent carbon cycle. This is a summary of the targets in our first phase of EEH, which lasted from 2020 August to 2022 July. I mean, the first focus is we implement two different algorithms, including split window algorithm and temperature emissivity suppression algorithm. We compare these two LST retrievals with the state-of-the-art high spatial resolution missions, including Landsat and Aster And the second focus is like we implemented 3 structurally contrasting ET models, including STIC, SEPs, and TSEP on the EcoStress TS LST data, and we evaluate the 3 ET retrievals over different biomes at 19 sites in Europe. And the last focus is definitely a operational data generation. So we generated LST and ET products over the period between August 2018 to December 2021. And currently the data is still at the instantaneous scale, and also, it's source data. So, for the ET is instantaneous, so we didn't integrate into daily scale. So we've done in our second phase, which will be introduced later on. So these are some results for the LST. For the first graph is the comparison among 3 different EcoStress LST products. The first one is the official EcoStress LST product from JPL. And the second and third are the 2 LST products from our EH project. We can see that the RMC, in terms of RMC accuracy and precision, are very close to each other. And the second one is a comparison with the high spatial resolution dataset mission. I can see that the RMC is also very close to the previous 3 EcoStress LST products. So, in the last figure, we compare JPL-TS, EHSW, EHTS, Landsat, and ASTA. We can see that overall, these 5 LST products are very close to each other in terms of these 3 indices, RMC, absolute mu, and sigma. And the lower panel is the impact factor on the LST residues. The first one is the precipitable water vapor content. You can see that actually, the influence is not that obvious, but actually, as compared to the TS algorithm, SW is less sensitive to the precipitable water vapor content. And the second one is the sensitivity analysis to NDVI. We can see that, for different NDVI like bins, EHSW has a relatively lower RMC. And also we can notice that for this kind of moderated vegetative surface with NDVI between 0.4 and 0.6, SW has the highest RMC. This is because of the estimation of emissivity, because we use a vegetation cover method to estimate the emissivity. So in this kind of moderated vegetative situation, it's very difficult to get accurate emissivity. That's where TS show is obvious advantage. The last one is the sensitivity to the residual over different land surface types. You can see that, and this is very interesting, especially over barren surfaces, because for the, let's say, MODIS SW, it just use a land cover-based emissivity map. But here we use the ASTA GED, bare soil background, emissivity background. So you can see that over barren surfaces, the RMC of temperature is enormously improved, which is comparable to the TS LST RMC. And for the other vegetative surfaces, SW has a little bit higher accuracy, but not very actually substantial. So this is the results of ET. As I mentioned, we implement 3 different models with different structures on EcoStress LST products. The first figure is the model developed by Kanishka Manik, the first talk today in the morning. So it's a LUM parametric model. Basically, in this model, we don't have to estimate the conductances and aerodynamic temperature. So everything is done in a physical way without any empirical parameterization. And also, because we include 2 conductances, both aerodynamic conductance and canopy stomatal conductance, that's why we can incorporate the effects or the control from both LST and VPD. But for the other 2 models, they are parametric. They are also good, but they are parametric. And because of the, what should I say, they bypass the inclusion of canopy stomatoconductance, so the VPD control cannot be incorporated, so only LST control is included in these two models. So in terms of the accuracy, you can see that, I mean, our model, a STIC model has the like highest accuracy as this selected 19 sites over different biomes in Europe. I mean, the RMC is below 70, and for the other two models, I mean, SABS and TSAB, I mean, they are above 70, and also the bias and Pearson correlation coefficient is lower. I mean, the bias is higher, definitely. So the low panel is the Taylor diagram, like we used to describe the agreement between the model simulation and the ground measurements. And the x-axis is the aridity index, which reflects the meteorological situation of different size. You can see that when the aridity index is above 0.8, actually the KGE is very close to 1, which means that the agreement between the model simulation and the instruments are very consistent. But when it comes to the dry area, I mean, when the aridity index is below 0.6, we can see that there's quite a lot of discrepancy between the instruments and the model simulation for all the models. But relatively, STIC performs slightly better in this kind of arid and semi-arid regions. We can see that even though it is still below 0.5, but as compared to SABS and TSAB, I mean, is higher, is closer to 1. So, we have 6 different biomes: forest, cropland, grassland, shrubland, wetland, savanna. So these all in Europe, in Germany and Italy, France, and also Czech Republic. So this is the residual analysis on different impact factors. The first panel is the ET bias and the sensitivity of ET bias to soil water content. We can see that when very consistent to previous like exploration, when the soil water content is low, actually the ET bias is higher in all the models. I mean, the trend is very consistent across different models. But relatively, also STIC has a lower ET bias in this kind of dry situation when with SWC below 0.2. For the VPD is the opposite as compared to SWC, because when VPD is higher, that means the atmosphere is drier. I mean, the water deficit of the atmosphere is higher. So we can see that actually also the trend is very, I mean, consistent across different models. When the VPD is below 30, actually, I mean, I mean, bias is very low. But when it comes to dry region, when the VPD is above 30, maybe water models, they have very relatively large ET bias. Okay, but relatively STIC still performs slightly better as compared to other models. So this is the sensitivity analysis to FVC and local solar time. For FVC, you can see that for STIC, I mean, the performance is quite consistent, except for for FVC between 0.2 and 0.4, I mean, it's a little bit higher. But for the other bins of VC, I mean, the mean bias is close to 0. And for local solar time, because we know that, I mean, the orbit of ISS is quite special. So, I mean, the revisit time is quite is various. I mean, during the day. But we can see that for different overpass time of ecostress, STIC also performs quite consistently. So this is a comparison between STIC ET and the PTJPL ET. You can see that, I mean, the accuracy is also relatively higher in terms of the 3 like metrics, especially over the dry region. I mean, in the lower corner. In this kind of situation, I mean, STIC, the advantage of STIC is very substantial, I can say. We infer that it's because of the very loose coupling of temperature in the PTJPL model, because currently, in the current version of PTJPL, I mean, LST is only used in the surface energy net radiation budget calculation. So in this sorry, this is Taylor diagram. I got it wrong. So actually, I mean, STIC is closer to the observation. So this is very consistent with previous results. And we can see that, I mean, over savanna, I mean, the performance of stick is also quite good as compared to PDGPL model. Okay, this is some application of our EHTS for urban heat island monitoring of ROM in 2021 in summer. This is the application of our EHE stick ET for agricultural water stress monitoring in the sub-Sahara region, I think in Mali. We can see the very obvious difference between the water sufficient field and water stressed field. So this is the second phase. We just started this project. So we have this like focuses. In terms of, let's say, refinement of a TS algorithm and analysis of the LST impact on the ET retrieval and also upscale in the instantaneous ET to a daily like estimate. And also we're gonna like couple the water cycle with the carbon cycle in an integrated model. And definitely that's why is we're gonna generate some like products, ET, GPP conductances and also water user efficiency during this period. And also we are very happy to hear that from Simon that the mission will be extended to 2029. This is some brief introduction about our refinement of the TS algorithm, because currently in the TS algorithm, the most, not most important, a very important component is the collaboration between the between the MMD and the minimum M severity. But the relationship is calibrated using leaf M severity and the soil M severity. But actually, when it comes to pixel scale, we cannot use leaf M severity. Normally, we can only see canopy M severity. So here we use the model Technique model developed by Albert Oloso in 1995 to simulate the canopy M severity, and then we regress the relationship between MMD and the minimum M severity. So done. Okay, so this is the results. We can see quite a lot of difference in terms of LST and M severity. But unfortunately, I don't have the time to introduce that. So, but these are some just preliminary results. I can see this is the recalibration. So yeah, that's all I think. And also the data available on our WASD platform. If you're interested, please feel free to download it and play with it. Thank you.
Thanks. Thanks, Diane. Unfortunately, we don't have any time for questions, but maybe at the end of the session, of course. So the next speaker is Jeffrey Louvel, who will be speaking about a new theoretical implementation for ecosystems productivity.
Okay, thank you. Okay. Good afternoon. We're really excited about this meeting because I came from the dark ages of thermal remote sensing. I had a senior NASA program manager say to me, "Why are you doing thermal? We can't get any more information out of that. We just use visible." So it's really gratifying to see all the interest. Today I'm going to do something a little different. Looking at thermodynamics of what you're seeing on the surface when you're using thermal remote sensing. And this is a Gordian knot, and our pilots get tired of flying straight flight lines. So we had them fly this pattern. This is the actual pattern. This is also in memory. James Kay died way too young and worked a lot on thermodynamics. Okay, one of the people we worked with for many years, Eric Schneider and then James Kay, before we even introduced, had this theory about how ecosystems should work and how you could measure the thermodynamics of ecosystem. Well, the problem is they didn't have any data. And they stumbled on the work that I'd been doing. They said, wow, let's look at this. Let's see how this works with our theories of thermodynamics. And Eric has a sense of humor. Life is the second law of the manifestation, the second law of thermodynamics. And I'll show you a little bit about that. And also, I encourage you to read this book, Into the Cool. So what I'm going to look at is non-equilibrium thermodynamic hypotheses. So our systems are not in equilibrium. They have flow of energy. So exergy, it's not a misspelling. People who don't do thermodynamics say energy. Exergy, it's the amount of work that's available. And so I'll talk real quickly because there's a lot of history in this, and I really don't have time to go into it. But just discuss a little bit of the underpinnings of the thermodynamics. then apply it to forest and health recovery and management. Look at what it means to agriculture, also urban areas, urban climatology, and public health. Okay, so if you look at it as purely, if you're an engineer, mechanical engineer, you look energy in, some energy out, you get exergy in, you degrade it, and so that exergy is degraded many ways, depending on the process. And of course, the main way that we're interested in is heat. So there's some ingenious experiments that were done to look at what happens with gradients and how they're dissipated. So a Bernard cell is a very good way of doing it. You just have a cold side and a warm side, and you have a fluid. And then you look at how the energy is transferred. And first you just get molecular, so you get some energy transferred, but not a lot. But then as your gradient increases, then you develop a boundary layer, and then you get structures that go and dissipate that gradient. And so if you look at what's happening in using heat dissipation and entropy, you know, this is only conduction, but when you add structure, you see the rate of transfer of energy goes much quicker. And so if we apply it directly to biology, and a chick embryo is developed, the first part of the development, this is the amount of heat, and then as soon as that system becomes organized, you get some evaporation and respiration. So, you know, the amount of exergy or how much it's using increases tremendously. And a good example is this, and unfortunately, if you live in the South and the Midwest with tornadoes, this is a result of that. So you can tornado bottle, you connect two 1-liter bottles, you fill one with water, you turn it over and time how long it takes one of them to empty. Well, all you do is just give it a twist and add structure, and it dramatically increases the rate that those bottles empty. So if we're looking at ecosystems, we've got a gradient. The sky is about 3K, of course the sun, and so what system will develop that is efficient at using that gradient, using that exergy contained in it? And if we look at some work done on the Hubbard Brook, you know, overwhelmingly evapotranspiration and heat is the main way that the structures dissipate that gradient. And, you know, photosynthesis is very important, of course, but it's just a fraction of that gradient. Okay, so how do we apply this to thermal remote sensing ecosystems, what we're all interested in today? Okay, so the second law of thermodynamics says that ecosystems are there to store energy, increase biomass, use that exergy as efficiently as possible, and it's a win. And so H.T. Odom, whole group, was doing a lot of this type of modeling of energy flows through ecosystems and all that stuff. And so there's a lot of information here. I can't even begin to touch it. So out of this, we developed a series of hypotheses that we can test using thermal remote sensing. So we believe that ecosystems, and we're including both natural, man-made, agriculture systems, follow the second law of thermodynamics. They develop structures to maximize their ability to use that exergy in that gradient. So what does that mean? Okay, one, if we look at the ratio of net radiation, net solar, lower surface temperature, exergy utilization will increase. For agriculture, lower surface temperatures related to both yield, and I haven't heard this in any of these talks, optimum nitrogen usage. So think about, we've got two major drivers of agriculture: the fertilizer, nitrogen, expensive, you know, real problem if you put too much on for waste and everything, and of course water is scarce commodity. Okay, and then the spatial variability of the temperature within that system should be more uniform, the internal equilibrium. So we've got a way of measuring that. We use what we call the beta index. And then the third area, and I'm really gratified to see more work done on these small sats where you can get repeated measurements in a very quick time frame, because you can measure a single temperature and point in time, but you really want a time series to understand what's happening in that system. So this thermal response number does, I'll go into it a little more on that. So of course you're all familiar with the energy budget. So the thermal response number is, I just take a temperature at 0.1 and over a period of time take it 0.2. This is remotely sensed. Look at the net radiation that period and develop a number called the thermal response number. So we all know here that net radiation, the three components, how it's divided up. So obviously, if we losing a lot of water, ET's very high, or if it dries, sensible heat, and depending on the surface, you could get quite a bit into storage. And that makes it nice about net radiation, because for most systems, it's a constraint on the energy available for that system. And also, back when I developed this in 1985, was from aircraft data from the TIMS, which was the first multispectral calibrated airborne sensor. There are a lot of problems. Georectifying, how to get the same area. So if you're doing repeat data, how do you know you're looking at the same surface each time you do it? So if you pull out polygons, you can identify those surfaces, but also with the polygons, depending on the numbers, you've got statistics, internal statistics that you can run on those polygons. Okay, so my first flights were back in 1985 at the Andrews Experimental Forest, and that was a Forest Service experimental station in Oregon. And I did a series of flights over that area, and I did a series of day flights, series of night flights, and just looked at the temperature variability across the landscape, but also I did repeated flights in a period of time, 20 minutes for one set and 8 hours for the night, to see how these systems changed at the various components on the landscape over time. And so if you look at the average surface temperature, this is a research stand 18. These are Doug fir forest. This is another research stand. This is a clear cut. And just look at the temperatures. That tells you some, but really what's really important is looking at the change of temperatures on those surfaces. So you can see with the snowbrush, which is a clear cut, the energy is obviously being partitioned different than, say, in the larger, older Doug fir stand. It's partitioning. So that's key to understanding how these surfaces work. And the other thing is that I wanted something that you could measure entirely in remote sensing. I know it's nice to have all these equations, all these parameters, but you're not going to have that data most of the places, and we're looking at doing global missions. So you need to have something that you can use without relying on a lot of ground data. Okay, the other was the beta index, so you want to know how uniform within that system or polygon. And you just do a beta index and fit a beta curve. It's no big deal. So if you look at mature Douglas fir, this is what it is at night, day, plantation. This is a regeneration clear. Each of these are diagnostic of how that surface is processing and energy can be classified. It's also good if you're trying to do time series and you want to be sure you're doing the same surface each time, because those curves they'll shift one way or another whether the surface is heating or cooling. But if you get a dramatic change or a change in that shape of that curve, you know you're not getting the same polygon. So if just a little table to kind of summarize the temperatures of these quarries, clear-cut Douglas fir, you can see the surface temperatures. Look at the ratio of this, not a big deal difference between these. And as you get older, they increase. Beta index increases as a uniformity of the canopy, and then the TRN, which you can see increases as, that energy is going into latent or sensible heat rather than, mostly latent is the higher the TRN goes. Also, what's nice about this, it's universal. It doesn't matter if you're doing a parking lot, a pine canopy, a ag canopy, it doesn't matter. So that work was done many years ago, and not a lot of progress was made. People weren't interested in funding it. But recently, particularly with EcoStress up and early adopters, some of these ideas are starting to be used. Hamburg was doing some work in conservation and active restoration to see how this compared, were they really restoring these lands? Was it working? And so he did a bunch of treatments, and he saw that the decrease in temperature for these areas as they were developed and recovered and everything. I've got all these citations because there's just too much to go in a lot of detail. I'm just doing a very broad brush of these. And so this was consistent with this thermodynamics theory. Several years ago, around 2000, I worked with a graduate student in Belgium, and we worked on this, and he couldn't get any funding, and I don't think he even finished his dissertation. Anyway, it was 2 minutes, okay. It's grateful to see these guys pick it up, and they did a very good analysis, all kinds of different forests, ag lands, and everything, using the TRN and the other indices. So ag, that's what I hear about. And we did ag flights in corn, and we saw a correlation with yield 0.86 2 months before harvest, and about 80% or 20% of the field produced 80% of the yield. Okay, so we had students working and looking at this this happened to be just other fields to see if these principles held. Is it cooler? Yes, as these different areas were more complex or more advanced in their species and all this stuff. And we're looking at difference in grain yield and how that canopy temperature. This is Akbari in 95. And so we could look at nitrogen also on this. And so in 2006, we had a student working on, we did a series of greenhouse tests and field plot tests, both looking at competition and also nitrogen, and seeing how the temperature changed in relationship to competition using both thermocouples and a thermal IR camera. Looked at leaf whorl temperatures and looked at different nitrogen levels. And so it's really gratifying that we can start thinking about, man, we can kind of look at nitrogen. Do we have enough nitrogen? We're using too much. So Alvazen in 220 in her dissertation did an additional, more extensive series of both field studies and greenhouse studies looking at nitrogen rates in different years and how the applications and how that related to surface temperature, and it was consistent with the theories that we put forth. And even looked at timing of when those nitrogen, that nitrogen was applied, used high level, low level. So, again, I'm putting all these references because there's just too much to really absorb. Next is the urban heat island. So, one of the things that is important when you're doing urban climatology is that storage component and how that surface interacts with the atmosphere. And so, having that thermal response number works really well because obviously these surfaces respond much differently thermally, and so you get a very detailed measurement of how that surface is interacting. And then I have what I call energy fingerprint, which gives you a nice picture of what's the structure of that urban environment is. So in conclusion, I think both managed and natural ecosystems developed to degrade that exergy. And I think we've got indices to look at that, particularly using thermal remote sensing, and people really aren't looking at that. This is a theory behind what you're seeing when you're going out and measuring your crops, your forests, and this stuff. And I think it's a huge potential to look at fire recovery, biodiversity, and the current high-test campaign starting shortly. It'd be a good time to test these. If you set your flight lines, do repeated flight lines, maybe a 40% overlap, side lap on the flight lines, you have the data to do all these indices. So that's it.
Any questions? So we are running out of time, so we'll move on to the next talk by Jennifer Adams about directional effects
experimental monitoring in forests.
Yeah, okay, so my name's Jennifer, and I'm a postdoc at the University of Zurich. So we heard yesterday that directionality is a critical thing that we need to think about and solve when we want accurate land surface temperature data. But also working in forests, as we learned this morning, is not that easy. So today I would like to take on the challenge of trying to look at directionality in forests, and particularly across scales. So just starting with a bit of background about the project that I'm working in. So it's called the TSEC project, which is the Trishna Science and Electronics project. And it's the Swiss contribution towards the Trishna mission, where we specifically look at energy balance modeling in complex ecosystems. So this is in particular mountainous terrain. So since we're working in Switzerland, we know that most of our sites that we're working in are extremely complex and in the mountains. We focus on a variety of different ecosystems. So the biosphere, which is partly the forest, which is the part which I'm going to present today, but we also work in the Arctic tundra. We also work in the cryosphere and the hydrosphere. So in order to look at these energy balance modeling, we have a few kind of different things that we want to look at and different challenges. And to do this, we set up a kind of network of validation sites across all of these spheres. And today, I want to go into a bit more detail about the forest ones. So this is an example of one of our forest sites. So this is the Lageren site. It's not too far from Zurich, just in the north, and it's a long-standing FluxNet site that's been acquiring data since 2004. We have many different types of data. So we have full 3D structural data, full 3D structural models. We have optical data and a long history of remote sensing data, but until now, we don't have any thermal data, so we would really like to put thermal data to complement all of these different data types at this site. So, okay, that's good, but we would like now, so yeah, we kind of started to think about putting thermal instruments on these sites, but then we kind of ran into some hurdles. So firstly, where should we actually put these sensors? So we're working in complex terrain. And so depending where we put the sensor, we could be extremely close to some trees or extremely far away and kind of absorb, look at more of a landscape level. Also, depending where we're looking, we might get very different components of shadowing and the hotspots during the time of the day. So this is one question that we started to ask ourselves. The next question is, how are these instruments actually going to be impacted by directionality? So we know that these instruments have an angular component themselves. And are these mechanisms behind directionality the same as what we see at different scales? So from what we see at a Trishna scale pixel from 50 to 60 meters, is that really the kind of directionality that we're going to observe when we're pointing directly at a tree? And finally, if we use these measurements to validate ecosystem stress products like the evapotranspiration products that we've learned so much about this morning, how will directionality at the kind of tower scale impact the measurements when we actually use them to validate our products? So we kind of started to think about, okay, how can we do this? Well, okay, let's try and think about some multi-angular data that's actually available. So we have a few different types of multi-angular data, whether or not that's from satellite observations. We know that we have a couple of sensors which do have multi-angular observations, but they only have a couple of views. We might use different types of sensors that we can get an idea about, so we can use kind of the edges of the orbits to get different view angles. We could use UAV or airborne data, but I guess as we're going to learn tomorrow that planning an airborne campaign with a directional component is not the easiest thing. So this is definitely something to consider, but right now we don't have that kind of data. We could look at UAV data, and this is definitely something that we're looking into, but we also know that working with UAV data is extremely complex, and there are many uncertainties which are introduced into the retrieval of land surface temperature from the UAVs. Again, we could look at the in-situ observations, but from a single tower, we're not really sure if a single observation from the tower is really going to tell us much when we start going at these larger scales. So what we started to think about is, well, how can we actually measure directionality in a standard way across scales, so going from the tower all the way up to the Trishna pixel? And one way we could do this is using a goniometer. So I guess many of you are familiar with goniometric systems. They allow you to take multi-angular measurements in a full view zenith angle and also an azimuth angle. This is the University of Zurich goniometer system that was developed about 20 years ago, and it's been mostly used for hyperspectral spectroradiometric data, and it hasn't been used yet for thermal data. So we were thinking, okay, perhaps we could use this to try to understand directionality across scales in forests. And the one question that we asked ourselves is then, okay, we have to find a way to kind of reconstruct so-called miniature forests at different scales so that we can then try to understand the different mechanisms of directionality. And to do this, we kind of try to recreate different scenes depending on their scattering mechanisms. So firstly, taking over to the left, this is kind of what we see from the tower. And we could reconstruct this with geometric optical scattering. If we then take a satellite pixel, so this is a Landsat 8 image, we then could recreate this by so-called multiple scattering. We then kind of shrink this down into the goniometer footprint, and we can kind of recreate these different scattering mechanisms. So these are actually plastic trees and forests. And we have the geometric optical scattering is recreated by these miniature trees or these spheres. And the volumetric scattering, which is kind of what we might expect we see from the satellite level, is reconstructed by this kind of artificial grasses and turf. So this is what we call a structure-only forest. And then we want to recreate exactly the same kind of miniature forests, but with actual plants. So they have not only the structure, but then we also have kind of the radiative properties of the soil and the plants inside of this. So we have, at the moment, I'm just going to show you some examples from the so-called structure-only forests. So these are the plastic forests. We have 5 main types of forests which have these different dominations of volumetric and geometric optical scattering. So we have one kind of artificial turf, which is basically what you normally find on a football field or a hockey field. We have a second volumetric scattering scene, which is kind of a lot rougher, so it has a bit more shadowing components within it. We then set 3 different types of geometric optical scattering scenes, and these range from different fractional coverage, so we basically increase or decrease the gap fraction within these scenes. And yeah, we also have kind of a background, which we use as it's a black tarp kind of background, so we just have a measurement just basically of the so-called soil. In order to do this, we have an apogee radiometer, which measures in the 18 to 14 micrometer. We have a meteostation, which measures air temperature and humidity. We also have a GoPro and a rather old but still working neck-tier camera. This isn't really for the analysis, but it's always good to have images of what you're taking so you can kind of help you to tease apart some of what you see. So the goniometer setup, we take in total 54 measurements across the full hemisphere. We have 6 different planes, and we measure from view zenith angles of -60 to 60. We have an integration time of 10 seconds, and we take a number of measurements per angle so we can get a mean and a standard deviation. One thing that I want to point out that was quite a large development of this goniometric system is that it was actually developed for an ASD spectroradiometer, which has a much narrower field of view than the apogee that we're looking at. So if we put the apogee kind of right on the hemisphere, as you see here, we wouldn't be measuring the actual target. We would be measuring the target and contributions from the room. So we developed a so-called arm, which can basically be moved at different angles to ensure that the target size that we're looking at is always the same. And so this is an example of the setup there. And so on to some results. So I show here the so-called tower miniature forest, and this is the geometric optical scattering. So you can see here the polar plots from the different scenes. So we go from the lowest fractional coverage, where we really see the hotspot and the shadowings very clearly, to a kind of medium cover fractional coverage, where we have this kind of, not super strong hotspot. And then we have a kind of very dense forest. So this is, on the very right-hand side, is kind of the density that we might expect from the Lagenen or also the other sites that we're looking at. If we then go to the volumetric scattering, or what we might expect we see from the satellite, we see that we do have the sensor, but then we also have this kind of in-plane scattering. And in particular, we have quite a lot of forward scattering, so scattering in the opposite direction of the sun. So this could be related to the orientation of the leaves or the leaf angle distribution, which is something that we might consider changing. Or it could also be to the sensor temperature. So the apogee sensor that we're using is not cooled, and we know that cooled instruments are incredibly important. And we actually noticed that depending on the angle within the hemisphere, that we actually have different sensor temperatures. So basically, when the radiometer is kind of perpendicular to the sun, to the lamp, it gets heated up a lot more, and we really want to understand how this might impact our measurements. So in order to do this, we have set up a collaboration with the World Radiation Center at Davos. There they have a black body temperature, and they're also able to control extremely well the sensor temperature. So we have taken our apogee radiometers to this site to try to characterize as well as possible the impact of sensor temperature on our measurements. And so finally, some take-home messages. So this goniometer system hasn't been used so far for thermal measurements, and we have finally set them up. Alongside the study that I've shown today, we are also looking at measuring different types of surfaces and trying to build up a kind of database of bidirectional measurements. And we would be very interested to hear from the community what kind of surfaces are useful. Initial results into looking into forest directionality seem sensible, but we do need to take some caution for the sensor temperature. And right now, we're setting up the sites, setting up the scenes for these so-called real forests. And here, we really want to look at the impact of gap fraction, but also component emissivity, different component temperatures, so not only changing the forest, but also the soil underneath and its structure, as well as the fractional coverage. And we also okay, it's great that we've done this in the lab, but we do need to extrapolate this to actual real data and to try to understand if what we've seen in the laboratory can really be put into the context of the real world. So we do have airborne and UAV data to help us do that. And we would also like to use such data to maybe apply or test some of the existing BTDF kernels that are being currently developed. And all of this is basically to help thermal instrumentation at the forest sites that we're looking into. And finally, I would just like to say, if you want to learn more about the TSEC project in general and the different challenges in the other ecosystems that we're working on, we do have 2 posters. One is looking at pre-alpine and alpine lakes by Abel Fazl, and another one is looking into the cryosphere and the Myrtle Rock Glacier by Catherine. And yeah, I thank you very much for your attention.
You can stay. You can say you have kept your time very well. Is there any time? There is time for 1 or 2 questions. No one. I've got one. Like, are you going to do some 3D modeling as well, or like Dart or something like that?
I didn't mention it, but we do have full 3D models of the forest sites that we're working on. But we might also take it back to be more simple and try to recreate exactly what we've done in the laboratory with, like, the Dart model, for example, and try to add that.
Good.
Thanks.
Good work. Okay. So that's all for the ecosystem stress part of this session. So I give the floor to my co-chair, Emmanuel.
So the second part of this session is dedicated to high-resolution thermal observations over the ocean, and especially in coastal zones. So the first presentation is given by Jakob Oyer from DMI, and so the title is The Greatest Science Team Needs for High-Resolution SST Missions.
Thank you, Emmanuel. Yes, so I have to apologize beforehand. I will not show a lot of nice figures and or photos or anything. But what I do want to present is an overview of the coordination activities that we do within the international sea surface temperature community, and also suggest some, have some recommendations and some needs, and suggest a coordination way forward, so we can end up with a very nice, some presentation with very nice results on the high-resolution satellite when these missions come up and flying. So I'm representing the GRIST science team, and we are at DMI, at the Danish Meteorological Institute. We're hosting the project office. But this talk is really on behalf of the science team and the science team chair. So maybe just a few words about what is GRIST. Well, first of all, the acronym, if you don't know it, it stands for Group for High Resolution Sea Surface Temperature. And it was established as out of the GODAE pilot project in 1997 to 2008. And back in those days, high resolution was actually a cool word for 1 kilometer SST observations. So the group has existed since then, but I think the meaning of the word high resolution has changed a bit. But now I think we'll come into business again, and I'll show that in the end, where high resolution means less than 100 meters in this context. But in the GRIST context, it's traditionally 1 kilometer global sea surface temperature observation from satellite. So it's an open science group that tries to coordinate both research and operational developments within the satellite SST world, but also to promote the applications of satellite products, the monitoring and the uptake of these products with the users and with the scientists. And that's on the basis of an agreed framework and best practices. So as you can see, what do we do? Well, we provide a framework. We agree upon a framework for knowledge and data sharing. We agree upon some best practices for data processing and assessing uncertainties. And then we provide a forum for a dialogue between the SST producers among themselves, but also bringing the SST products to the operational world and to scientific researchers. Just want to highlight that it is truly an international group we're dealing with. The project office itself is sponsored by the Copernicus EU program, but otherwise it's all the activities on the individual institutions are covered by themselves. So it's a co-financing, and it involves all the, I would say, most of the major space agencies, major satellite producers, and also big centers for uptake of satellite SST products, as well as research organizations. So what is one of our main achievements? For sure, it's that we have actually one common data format for all sea surface temperature products. So it took some heated discussions. It took years to agree upon that within the science team. I heard yesterday that I think it was mentioned that it's impossible to do that for the LST. Well, here's an example on that. It's not impossible, at least in the SST community. It wasn't easy, but we managed to reach a sort of a consensus and write a document providing format specifications for SST products. And because it involved all the different institutions, space agency and so on, it was actually taken up. And it's more than 10 years ago, but it was taken up. And today we have over 100 SST products that have the exact same format, follow the same specifications. So if you have one program, write one code that reads one SST product, you can use the exact same code to read the other 99 or even more SST products. So that's a real benefit, and we have seen a great user interest in this and a user uptake, increase in user uptake by doing this. So just highlighting that. We had a global data archive, but with the increasing data volumes, we have now decided to make it a sort of decentralized data archive, but with a central catalog, which can be found here at grist.org. Let's see. Oh. Just highlighting that most of the activities or discussions and decisions are taken during the annual science team meetings that are held once a year all over the world, as you can see here. Also to reach out to users and new communities to get them involved in the GRIST community. And the last one was actually last year in Barcelona. where we were so fortunate to have participation of Philippe and the CNES and discussing about the Trishna mission and the possibilities there, and that was quite nice and very interesting to see, or to have this discussion about the new opportunities that these higher resolution missions offer. And the outcome was that there was very positive feedback and a general consensus that there is a need and a very high user need for the high resolution SSTs in coastal regions, coastal zones, and there will be a pull in the coming years, for instance, from the Copernicus Marine services upon data streams and applications. So there is a huge potential here. That will only grow in the years to come. But it's also important to make some coordination on this, to have to coordinate some of these developments and the formatting internationally. And we made it a priority for GRIST, at least to look into some of these priority areas, or to make it a priority area for the coming years in order to increase the user uptake and facilitate the user uptake of these SST products from Trishna and LSTM. So there are, from the meeting, the meeting in Barcelona last year, we had the initial discussions. They will continue. I'll come back to that. But there were some recommendations that we had immediately came up front, or some needs and requirements, and just saying that if we want this to be a success, the high-resolution coastal SST product, it's very nice to have a consistency as much as possible with the existing GRIST products, to have a common data format, to have specific SST retrievals and cloud masking. It's not the same as for the land community, as far as we can tell. So have a dedicated retrievals, have dedicated cloud masking over the coastal zones, provide quality with the retrieved temperatures, provide uncertainty components. Of course, it has to be open access. And then we also, within the SST community, we have an established way of validating the products. And I think the Ocean provides a very nice setup for validating satellite observations, and especially also the high-resolution satellite observations. And we have ongoing projects about collecting fiducial reference measurements, which is traceable, in situ measurements that are traceable to SI standards and documented, and provide a validation framework of the global SST products. That's ongoing activities that could be linked very easily with these high-resolution products. Lastly, is just recommendations. We would like to see that there would be some integration of the high-resolution SST and also some intercomparison with the existing global products that are well established. And again, consistency between the coastal products and the traditional 1 kilometer product would be very beneficial. And also across the different zones, like going from SST, from the ocean, coastal ocean to the land, or going from the ocean to the ice in the margin ice zone, and the sea ice surface temperature could be really useful for the users. So these discussions have started within GRIST. We are very open to input from outside, and I really encourage you to, if you're interested in this and interested in our developing SST products for the coastal zones or the missions, please come to the next Science Teams meeting here in India. It will be in October this year. And it's very timely. It will be hosted by ISRO, and it's very timely with the development of the Trishna mission and the LSTM as well. So we'll have a special session on the high-resolution satellite missions and the coastal SST products. So there'll be more discussions and also a way forward and what developments are needed. We'll go more in detail on this meeting. So I encourage you to join. Thank you.
You can stay, maybe, Jacob. So, any questions for Jacob? Where is the microphone, please? Oh. No?
No.
Yeah. Here is a microphone.
Because this using sea surface temperature, do you have any plan in the future to take it to the global ocean evaporation mapping as an application?
Yes, well, that could be, I mean, that's an uptake. That could be an application, yes. We don't have plans in my office as such, but there are a lot of, I mean, there are a lot of applications of the SST product. So yeah, come and ask, talk with us if you're interested in doing that. Okay. Or if, I don't recall as such that we had participation from institutions doing that, but all applications of these products are welcome.
Thank you.
Just a quick question. So MODIS, SLSTR, all these other instruments, their standard products are in GRISC format?
Yes.
So even though the other products are in different formats, their standard products from, like the land products are in different formats, the ocean products are all in GRISC format?
Yes. Okay. That's, yeah, that's true. There are a few that don't follow the format, but it's not just Europe, US. It's also yeah, Chinese products and so on.
Okay, so you don't take the products and reformat them. It's literally the agency releases them in that format.
Exactly. It's the producers. We have provided our sort of a compliance checker, like a CF compliance checker or whatever that you can use as a producer to see if your product follows the specifications. Mm-hmm.
Thank you, Jacob. So the next speaker is David Wessey from the University of South Carolina. The title of the presentation is High-Resolution Sea Surface Temperature from EcoStress.
So EcoStress has been described extensively by Simon in several different venues yesterday. So you've seen most of this information. The things that I'm going to mention right now are that there are 3 active thermal bands in EcoStress. And the NEDTs for those are on the order of 0.13, 0.1, and 0.29 Kelvin. There are 2 black bodies on the instrument. One's at 295K, one's at 325K, and they're imaged on every mirror scan, and that allows for the removal of non-uniformity across the focal plane. What we've done is a validation in the ocean of EcoStress, taking the Collection 1 archive from 2018 through most of 2022. And there's a real advantage to doing this in the ocean rather than on land. And one of the reasons is there are many more observations per month available in the ocean than there are on land. Emissivity is extremely tightly constrained over the ocean, whereas on land it's highly variable spatially. And so we did a validation using about 200,000 triple matchups among EcoStress, LST, and then best quality NOAA in situ observations, and then best quality geostationary observations from the Europeans, the Americans, and the Japanese. And then we also did radiance transfer modeling at each one of these locations. And used ERA5 as our atmospheric information. Leah Paul had a poster yesterday, and it describes a matchup database that the French have been developing that's specifically for Trishna on the European coast, and so that's a kind of parallel effort to what NOAA has done in the past. So as examples of the kind of patterns that we found, here we've done a comparison of LST versus in situ observations, and here are some examples of different kinds of masking of the data. The upper left corner is EQUAM best, that's the in situ best quality data, and then using the EcoStress cloud mask as the to pick the EcoStress data set. And what you see is there are a lot of points that are well below the diagonal line, which represent clouds that are that have not been identified by the EcoStress cloud mask. If we then take the NOAA cloud mask in the lower left corner, we find that we get a much cleaner data set, and then if we do a robust outlier removal, we get an even much cleaner data set, which is the upper right-hand corner. The result is there's a median bias on the collection 1 of about 1.1 degrees Kelvin and a residual standard error of about ½ a degree. So another set of data that's retrieved all the time by EcoStress is the emissivity. And here in the bottom row, I have histograms of emissivity retrieved in the 3 different wave bands, the 8.78 on the left, the 10.49 in the middle, and the 12.09 on the right. The pink histograms are the retrieved emissivity from EcoStress. The blue histograms are the emissivities from the RTOF simulations, and the red vertical lines are the Aster Spectral Library emissivities. And what we see is that EcoStress is producing emissivities, at least over the ocean, that are quite a bit too low. The result of this is that because the emissivities are low, you end up as basically a balance against the low temperature bias, because lower emissivities result in reduced bias. And so the diagonal lines in the upper graph show the effect of the emissivities on bias. But the main message is that EcoStress is retrieving emissivities that are too low, at least over the ocean. We've been interested in how this translates into the intertidal zone. This is a zone that's exposed at low tide. And so we've taken apogee radiometers. We have one pointing up, one pointing down. We have thermocouples on the ground so we can directly estimate emissivity. And what you see in the upper right-hand graph is a time series of 6 hours during low tide of what happens to emissivity. It starts out at on a sand surface, it starts out at about 0.97 emissivity, and then over the next 3 hours, it drops down to about 0.91. And then it's stable for several hours, and then the last half hour just before the tide comes in, before you can actually see any change in the surface of the sediment, capillary action is moving water up through the sand grains, and the emissivity rises rapidly back up to 0.9, up to about 0.97. By contrast, into sandy mud, which holds much more water, the emissivity is relatively constant. So from the point of view of Trishna and SBG and LSTM that are trying to get ideas of what temperature is like over this transition zone between the land and the ocean, this is a zone that changes, the transition zone changes on hourly timescales. And so there's great need for very accurate emissivities in this zone, because they determine what algorithm you're actually going to be able to use to get an estimate of temperature. And this is a place where aquaculture is done, so there are millions and millions of euros of money that are at stake for getting good temperatures. Now in the open ocean, EcoStress is a real game changer. The upper left, or the left-hand graph is an image from EcoStress, and the right hand is a Virzan 20 image. And what you end up with is the EcoStress shows all kinds of very fine structures that are completely invisible in VIIRS. So these are internal waves on very small spatial scales, on the order of less than a kilometer spatial scale, that can't be resolved with an instrument that has a kilometer pixel scale. So this is a real game changer. This is small scale, sub-mesoscale structures that really have an importance from the dynamics of the ocean, ocean-atmosphere coupling, et cetera. We can actually believe what the EcoStress numbers look like by comparing to sail drones, which are autonomous vehicles that are deployed in the ocean. The upper left-hand image is an EcoStress picture from the California coast crossing at the upwelling zone. The middle graph shows, on the black line are the EcoStress pixel data. The red dots are the sail drone data, and you can see that the sail drones match very well the gradients that are transitioned by the sail drone. The lower left image is I've outlined the individual pixels, and what you can see is that in some cases sail drones are sampling at the same pixels, the same scale as EcoStress. EcoStress and sail drones are sampling at the same spatial scale. So we really can resolve small scale features in 2D now with EcoStress that you could only resolve in 1D with sail drones. EcoStress is potentially very useful in this context for understanding gradients in general. So the upper left image here is the Western Mediterranean. There are two big gyres and strong gradients. The upper left image is the gradient magnitude from VIIRS. The lower left image is the gradient magnitude from EcoStress. In EcoStress, you have to go through a lot of extra work in order to get the gradients because there's a lot of noise in the EcoStress image. But when you do it, you find that, in fact, the EcoStress image is resolving gradients that are as much as 40 times steeper than the gradients resolvable with VIIRS. And this is because the pixel scale is so much smaller. So this, again, is a real game changer. It's possible to resolve extraordinary intense pattern in the ocean that you can't get any other way. EcoStress does have this problem that it's noisy. You can see stripes in the left-hand image. You can see checkerboard patterns in the right-hand image. Those are artifacts that are non-Gaussian. They're systematic artifacts, and they're something that has to be cleaned up in order to really make this a truly operational kind of SST production system. But if we can resolve those kinds of problems, we really will have the best instrument available for quantifying ocean temperature on very small scales. To try to understand what the origin of these noise patterns are, we've looked at cross-track noise as a function of position on the focal plane. That's what we have in the left-hand graph. Those are the four lines represent images from different temperature conditions. One from Sakhalin Island that's very cold, that's black. The red one is from the Arabian Gulf. And what you find is the middle of the focal plane is noisier than the two edges of the focal plane. So that's a systematic pattern that exists in the instrument. And then the right-hand set of three images represent brightness temperature anomalies across the focal plane. And what you notice is that the pixels 1 to 100 or 100 to 128 on the focal plane, there is a reduction or there's an increasing negative bias as you go from pixel 100 to pixel 128. And it's about a 0.25 degree bias, and it occurs in all three wavebands. So what that leads to is the checkerboard pattern, because as the swaths are imaged, the right-hand edge of one swath is overlapped by the left-hand edge of the next swath. And so when you do the remapping, you're mapping pixels that are cold from one end of the focal plane next to pixels which are warm from the other end of the focal plane. So if we can fix this, that will get rid of much of the systematic noise, and we'll have a much cleaner product. So Jorge Vasquez at PODAC and I have a new project to develop a split window algorithm. And so our plan is to develop a pipeline for an L2 SST product, try to fix the checkerboarding and striping issues, and then archive the product at PODAC using GRIST standard formatting. Emmanuel Autré, sitting here in the front, is doing a similar kind of effort in preparation for Trishna. So we've done some split window tests, and basically a whole number of algorithms all do very well. You don't get a bias, but you have fairly high residual standard errors, and that's a potential issue in having a product that is really useful for the ocean community. Laura Orgambida, a student of Emmanuel, is going to give a talk about her efforts in the same order next, immediately after mine. So the lessons that we've gained from EcoStress. Number one, SST is an essential climate variable. It's really critical to understanding the Earth's energy balance, and uncertainty less than 0.2 K is a goal for climate data records, which are necessary to really measure the rate of climate change over the ocean. NEDT in EcoStress and all these new proposed missions are actually very high relative to some of the primary instruments that are used now for SST production. The NEDTs are in the order of 0.1, 0.15, 0.2 in the primary temperature waveband. Compare that to VIIRS, which is about an order of magnitude smaller noise level. Same thing for SLSTR and the same thing for MODIS. So this is something that's of potential concern to SST production, that the noise level of the new instruments seem to be higher than the intrinsic noise level of the current operational instruments. For SST applications, another message is that we really need black bodies that span the temperature range of actual SST, which ranges between about 273 and 305. The EcoStress black body is at 295, which is hotter than most SST measurements, so that is a potential issue in terms of calibration. There are also some potential nonlinearities with many of the sensors, and that can be solved by having ramp soak cycles in the black bodies during it on orbit or using pre-flight data. And then geolocation is really difficult in the coastal zone. The land-water boundary on sand flats can move as much as 20 kilometers between high tide and low tide. So on a time scale of hours, your land mass is changing dramatically. And so that's a really critical issue. So there are many kind of lessons that we gained from looking at these very high-resolution images. EcoStress is astounding what it gives us, and it tells us there are a number of things we need to worry about in the future. So shameless advertising, Jorge and I are looking for a postdoc, so if there's anybody here, please contact us.
Thank you, David. Any questions? Yes. Where is the microphone, please?
Thanks very much. Great talk, David. I just wanted to say that we are actually learning from these studies, and in fact on SPG, the black bodies will have a much wider separation and will match more typical terrestrial temperatures. On the ISS, we wanted it to, but it's the fluid cooling.
You're limited by what's available in terms of cooling and so on.
Yeah, and we can't do anything about that. And then the other thing is the geolocation will also be much better. And what's interesting is the geolocation without GCPs. LSTM is talking about 50 meters. On SPG, we're talking about 120 meters, compared with much, kilometers on the ISS. So I think those two things will really help.
That's all great news.
And we are learning from.
So is there any interest in doing ramp soak cycles like they do on VIIRS for temperature rise and then cooling of the black bodies during flight, and say once a month?
We can certainly do that if it turns out that improves things. At the moment, we're doing the studies to decide the best way to do the on-orbit calibration.
Great.
Thank you. So the next speaker is, no, sorry, another question. No, go.
Very quickly, sorry. Maybe I missed it at the end, but it was not clear to me the origin of this nonlinearities drift, and that you recover by warming up and cooling down back, if I understood correctly. Is that what you said?
So the mercury cadmium telluride sensors, which are like what's on Aster, what's on AVHRR and on EcoStress, they are somewhat nonlinear. And so some instruments like Aster and AVHRR, they use a quadratic term in the calibration equation. And that can be, in the case of AVHRR, it's done with pre-flight data. And Aster, it's done with pre-flight data. But in VIIRS, they have a cycle that they run something like once a month, where they do a stair-step set of changes in the temperature of one of the black bodies, and then they let them cool down in a stair-step. And that gives them multiple calibration points, which get them that quadratic term, which helps in resolving some of the biases that occur at temperatures away from those of the black bodies.
Okay, I misunderstood. I thought it was the nonlinearity of the detector which was not stable. Okay, right, thank you.
Thank you. So the next speaker is Laura Orgambide from Ifremer. The title of the presentation is Designing New Ultra-High Resolution Sea Surface Temperature Products in Coastal Areas for in the context for the future Trishna mission.
So hello everybody. At IFREMER we are working on designing a new ultra-high resolution sea surface temperature product, especially for coastal areas in order to prepare the future Trishna mission. So sea surface temperature is an essential climate variable. It is not only used to understand and predict the climate, but it is also used to study marine biodiversity, to monitor water quality and other offshore activities. And actually, the GRIST provides 1 kilometer resolution SST products that are derived from thermal sensors like VIRS, AVH-RR, or Sentinel-3, SLSTR, and they are useful to study the mesoscale and submesoscale features, but they suffer notoriously quality in coastal areas. And with the new upcoming missions like Trishna, LSTM, SBG, there is a good opportunity to create high spatial resolution SST products. So at IFREMER, we launched the project called Callista. So Callista for a coastal 100-meter resolution sea surface temperature from satellite infrared sensors. And the objective is to prepare the future Trishna mission, but we use the EcoStress and Landsat 9 data. And with this data, we use a split window algorithm, and then we calibrate and validate the estimated SST product with the GRIST. On one end, we validate it with the GRIST SST products, which is my job, and on the other end, we validated the estimated SST with the in-situ measurements. This part of in-situ measurements is the part of my, it is the job of my colleague Ilya. So she made a very nice poster. So it is very interesting to see what she made. So we downloaded EcoStress and Landsat 9 data over the IBI zone, so the Iberia-Biscay-Irish zone. It is a very interesting zone because it is a representative of the oceanographic and the atmospherical cases. And we also use the GRIST SST products from Sentinel-3, Xiaomi, and Metop. So with this data, we collocate so the GRIST SST product with the EcoStress or with the Landsat. We do a matchup data frame. Then we split this data frame into two parts. The first part is the test data set. And with the test data set, we can estimate the coefficients of the split window equations thanks to a linear equation, a linear regression. So we have 4 split window equations. They vary, differs from if we use the brightness temperature at 8 micron or at 10 or 12. And in total, it is important to understand that we have 16 combinations to assess. 16 because we test 4 equations with with the VIRS, SLSTR, and AVH-RR, and also because we use the RTTOV method. And then after doing this, after estimating these coefficients, we try to get some statistical indicators with the validation data set and select which one we will use for the final product. A few moments to explain how we have created the matchup data frame. So first of all, we take the brightness temperatures of EcoStress or Landsat. We apply the mask, the cloud mask, the land mask, and also the bad quality mask. For EcoStress, we convert the SWAS data to grid data. Then we apply a rolling mean smoothing, and then we can resample the pixels to the resolution of the GRIST SST products. So here you have an example where we can see the difference, and it is important that, to understand that we collocate the different products. During the pre-processing step, we noticed that there were a lot of masking problems, and so we are going to talk about it later. So with these masking problems, it was important for us to select our data very carefully to set this data then into the matchup database. So this database is made of 168 scenes that we selected with a visual inspection. And these panels presents the basic statistics of the distribution of the validation dataset and of the data that is used for the coefficient estimation. So here we have around 3 million of matchups, and we try to evenly distribute them over the temperature range, but also over day or night flag. And it is important also to notice that most of the matchups have a time delta inferior to more or less 30 minutes. Here we compare the land surface temperature product with the GRIS SST products, and we noticed that there were a bias of 1 Kelvin, and this bias is a cold bias over the Atlantic and Mediterranean regions. Here are the first results of our NLC SST equation adjusted with Sentinel-3. So we can see that the SST bias is around 0 Kelvin when it is compared to the Sentinel-3 validation dataset. But the bias is around minus 0.2 Kelvin when compared to the METOP or the VIRS validation dataset. So we think that this difference comes from the difference between the products of the GRIS. And it is important to notice that these are first results. This is not yet fixed because I think there is still many outliers because there are still masking problems, and also there are a lot of noise in our images. And we can note also that this graphic is for the validation of the pixel of the coast, and not for the pixels that are close to the coast, which will be validated with the in-situ measurements. Here are the SST estimation results from RTTOV method. So here from these first results, we try to investigate which variable would have influence over the SST estimation. So here we can see that wind speed and precipitation vapor have a higher impact. So we still need to go further into this analysis for the moment, and we also want to do. We also plan to test the sensibility of the algorithm with the Jacobians. I really wanted to show you these images because a large part of our work was to assess the quality of the images. And as you can see, there is a clear underestimation of the cloudy pixel, even at day and nighttime. And also, we saw some images where the cold fronts are sometimes detected as cloudy pixels. So the first solution we found was to avoid clouds was to select visually our images. But we think that it could be interesting to use external data like Savory, MassCloud. And also, we think that for the final product, it is very important to have a cloud mask. So we need to work also on that. And a last slide is about the quality assessment of EcoStress land mask. And as you see, it's not very good. So what we found as solution was to apply a shoreline shapefile. And here are some images of the shapefile, of the SHUM shapefile, land sea limit. But you can see it is not perfect because there are still sand parts and rocks that are considered then as sea pixels. So the remaining challenges is to create a dynamic land and sea ice mask. And we think that we can achieve this thanks to the tidal flats map. And also for the northern parts, we think it could be interesting to have a sea ice map. So that's it. I finish with an example of EcoStress estimated product and a few keywords to show our future work. That's it.
Thank you, Laura. Any question? No, so I won't ask anything because I'm a co-author, but I would like to add a comment. As shown by Laura, I think the critical part for the moment is really the cloud masking issue. Since it's very difficult to work with a great number of images, because finally, for the moment, we have to apply a visual inspection to construct our datasets. So we can find temporary solutions, as mentioned by Laura, for example, by using maybe observations from geostationary satellite images. Or starting to develop and to adapt cloud masking algorithm that could work for very high resolution data. So that's it.
Okay, so I invite all the 6 speakers to remain here for additional questions, maybe. The 3 EcoStress and the 3 coastal. So the 3 EcoStress was mostly dealing with multimodal European EcoStress ET products, tier-based ecosystem thermodynamics applied to restoration impact, and nutrient access monitoring, and finally the directionality characterization with goniometer or using mounted tier cameras over forest mockups. So we had a variety of issues.
During the 3 presentations concerning the ocean, so we have seen that there is an international context dealing with sea surface temperature observations with a group, an international group that has been existing since a very long time. In the second presentation, so David has shown the capability of EcoStress to retrieve very very sharp fronts in coastal zones compared to observations with coarser resolution, and it's very important since they play a very important role in the exchange of heat, of momentum, of gases. And he also highlighted remaining issues in this data set. In the presentation from Laura, so we saw that the construction of an SST product in coastal zone is still very challenging, with the different masks that have to be constructed, actually, the cloud mask, but also the land water mask, and also the sea ice mask. So, thank you.
So any more questions about this? Yes?
Hi, I have a question about the SST from EcoStress. So from the presentation, I got to know that the EcoStress has a little bit higher uncertainty than the traditional sensor vias. So is there any way to fuse them, even though they have different uncertainty budget? Is there any way to do it, to make a final good quality SST data of high spatial resolution?
It's possible. The difficulty is figuring out a way to fuse the signal rather than the noise, and that's the complexity. And I don't know, Simon, did you have? Right, and collection 2 has solved a lot of the bias issue. The pattern noise and so on, that has not been completely resolved by collection 2, but hopefully collection 3 will have solved that. So, you know, that's sometime down the line.
But we can reduce the uncertainty, even though we fix the bias, isn't it?
So the bias has been largely fixed by the collection 2. The noise is still there, so you still have the pattern noise and you still have the NEDT noise. So there's both Gaussian and pattern noise, and that's what gives you the stripes and the checkerboard, which crops up also in terrestrial situations.
Mm-hmm. Okay, thanks.
Hello. I have a question for the first presenter about the algorithm. Because you work over a vast area and you have many different end covers, have you explored the algorithm using a different vegetation index than EVI, because you use it as a proxy for emissivity?
You mean for LST retrieval or ET retrieval?
Yeah, for the proxy's emissivity.
Okay, for EHSW algorithm. Right. So basically for this algorithm, we just use the NDVI, and then we calculate the FVC, fractional vegetation cover, and then we use the ASTA-GED bare soil emissivity as the background, and then we just add the vegetation effect to the bare soil emissivity. In this way, we compose the emissivity. No, we don't. We don't try, because actually, I mean, the purpose of using NDVI is to calculate FVC rather than use the NDVI itself. So we don't see too much point in this in the adjustment. Yes, thank you.
I have just another question. It's for EcoStress again, sorry. You showed very clearly that the emissivity is changing very, very rapidly in the intertidal zone. Do you have any suggestion on how we can compute the SST and distribute it to the user in this particular area with this
Well,
changing emissivity?
Yeah, theoretically, if the TES algorithm is working perfectly, then you'll get the right emissivity. But part of the problem is the spatial scale, because on a sand flat like Mont Saint-Michel Bay, which has got a 20-kilometer wide sand flat on the extreme tides, a place like that, on the pixel scale of something like EcoStress or any of these other new instruments, the emissivity should be relatively uniform. But on a shore that's smaller, where there's a steeper slope, like the place where we did that, which is Plage de Gatso and the southern end of Oloron, that shore is steep enough that at least adjacent pixels are likely to have different emissivity. And perhaps within pixels, there'll be different emissivity because of the length of time that it's been since the tide left particular points on the shore level. So you have to take a DEM to know where the tide level should have. So you need a tide model, you need a DEM, and you need some knowledge of the hydraulic conductivity of the sediment because that determines how fast the water drains. And you also need to know something about grain size because if there's a higher mud content, then there is higher water content in the sediment. And higher water content means that the emissivity doesn't change much during a low tide, whereas very little mud content, the water drains, and you have these rapid emissivity changes. So it becomes a very complicated issue to deal with this, but it's important because from the point of view of at least aquaculture, there are millions of euros that are spent in this particular zone between high and low tide. And there are people growing clams in Spain in large tidal flats like that. They're doing similar things in other countries. In France, there's some culture of palourde, the clams. There's also a lot of oyster culture, and we don't yet know what the emissivity changes are on oyster bags during low tide. That's something we're going to try to measure next week in Arcachon Bay.
I have a question for Jeff. So regarding this TRN that you showed, thermal response number, and how do you handle it if the second acquisition is cloudy?
Yeah, okay, so that's been a problem with it because with aircraft data, you could do it anytime you want. So, you know, with the SPG, we're going to get day-night pairs. That's a little long probably because you're going to dampen that energy of flux and that. But I think with all the new all the ideas I heard, particularly yesterday on the new microsats and the frequency repeat, it's going to fit right in with that. And also, of course, you can use it with the geostationary, the GOES too, but at a much larger scale, of course.
No, I mean, I personally I'm quite a big fan of this taking this gradient, but also I would like to know your thought about what do you think, which is the best time difference that we should take? For example, between two acquisitions.
I probably can't give you, I've done it from everything from 8 minutes, 20 minutes, 8 hours. So as you increase your time, you decrease that magnitude just because of your energy's evening out. 20, 30 minutes, even an hour will work fine. But again, it may depend on your ecosystems and how quickly it's changing and when you do the measurements too. So it's, it's very dynamic.
Thank you.
Yep.
Just the last question from Sally.
Yes, I am on. So I have a question for the SST group, which is what David showed in terms of changes in the sand flat versus the mud flat in terms of emissivity. Do you think the same sort of problem will be true for emissivity calculations in agriculture on land when the crop has not yet grown? So after first seeding, depending on whether the land is wet or whether the land is dry or whether the land is just damp, shouldn't you see the same sort of problems with emissivity calculations that we're seeing in the coastal zone?
Presumably, yes. If you have a fully developed plant canopy, then you're really getting the emissivity of healthy plant leaves, and so that's going to be relatively stable. But if it's the first few weeks after planting, where the individual shoots are very small, then most of the cover of the ground is actually earth rather than living, and so the emissivity changes would be very rapid. Within a few minutes of turning on a center pivot rotating device, you'd immediately get a very rapid change in emissivity. And then if it's a hot sunny day, the soil, once they turn the water off, the soil is going to start to dry. And so depending upon what the mud content is of the soil, you'll get very rapid change. Now, in places where they grow, the best places to grow wine, the soil is really bad and it's sandy and rocky, and so those places, we probably see the same effects that we got. In soils that are more loamy, you'd expect to see relatively stable emissivity.
Thank you. So we can applaud all the speakers again. So it's time for a coffee break now. C'est sûr que c'est déjà le coffee break. Petite section, il n'y a pas 40 présents.
Sí.
They're supposed to ring the bell outside or something, I don't know. So it looks like six talks. Presenting tomorrow in the Calval, anything or?
No, presented yesterday.
Yes.
Not tomorrow.
Okay.
It's some people that work with the whole team of Caselles.
Luis and
yeah. They do measurements in the Albufera in the rice area.
Ah, yeah. The law sites?
Yeah.
Yeah. Okay.
Martin Perillot. The Lanson Valencia Texas.
Okay.
That is in the rice area. You continue to do measurements in this area in California as well, but you will present this.
Simon, I think tomorrow is.
Okay.
Yeah, Russell Ranch, it's an agricultural site, and then the lakes, and we just put one of our radiometers at La Croix, one of the traditional sites. It's like kind of barren, stony ground.
Yeah, I know. I was spent some time in La Croix when I doing my doctoral thesis.
Okay.
For measure emissivity in arid areas.
Yeah.
Because La Croix there are wet and dry.
Ah.
So in the middle you have the two.
So like, you mean like soil moisture wet or?
No, at this time, Marc-Philippe Bestol, I said before, doing a big box, 2 meters high. It's very heavy to measure with this. You need a crane in order to execute this measurement. And they measure the whole time
with battery
with a device that in order that the black leaf and the radioactive and the reflected leaf change all time. And we at this time we register with in a paper the changes. But this was interesting because you can see it perfectly the inertial effect because nowadays is difficult. Sometimes you take the measurement but you have enough information before and after.
Yeah. So just the gradients.
Continue measurement and where you can have good interpretation.
Because you have to correct the downwelling, and like that may change from day to day.
Now interesting is to measure the impact of the turbulence, etc. But it's not easy at all.
So, what do you think?
We need to start, no?
Now is the.
Halley, no? The pronunciation? Halley.
Yes.
Okay, thank you. Well, yes, can you hear me? We start the oral session number 8, Urban Heat and Cryosphere. The first presentation is given by my colleague Glyn Halley, and the title is High-Resolution Thermal Imaging of Urban Heat Island and Heat Waves.
Okay, so we're about to get started here in the last session. Kind of some niche topics for land surface temperature science and applications. I'm going to talk about how we can use high-resolution thermal data to map urban heat islands and heat waves. So my talk will be mostly focused on ecostress data, probably no surprise, with a strong societal applications component. And I'll leave more the technical urban talks to after me, Laura and others. Oh, not too much. Okay. So 2022 was a pretty extraordinary year in terms of extreme heat on a global scale. Europe experienced its hottest summer ever on record. The US experienced its third hottest summer. And there was an extreme heat wave just before the summer solstice in Europe that broke a lot of records for the month of June across a lot of the European countries. For example, here you can see Rome reached its record temperature of just over 40 degrees for the first time in June. And you can see this displayed nicely with a Sentinel-3 land surface temperature image here over Italy. While the US also experienced an extreme heat wave in that month, it was only later in the year, in fact in September, that the hottest ever and the most severe heat wave was ever recorded over a number of western states in the US. And it broke a number of records in terms of its severity, duration. Several areas experienced temperatures of 40 degrees or more over about 7 days, which is pretty extreme. And this is a real harbinger of things to come, because recent studies have shown that urban heat wave metrics, such as their frequency, duration, their intensity, they're all increasing at pretty significant rates. As you can see by this plot on the right here showing the frequency, especially over the last 20 years in the 21st century. So the land surface temperature derived from thermal infrared data is one of the really critical tools for monitoring urban heat islands, and in particular the surface urban heat island. And so yeah, I'm just showing some example thermal data that we specifically use at JPL that all employ the TESS temperature emissivity separation algorithm. So starting with MODIS in 2000, we get twice daily data at kilometer scales, giving us kind of the city block level temperatures in the urban environment, but with the real advantage of being able to look at long-term trends over the last 20 years. Now with EcoStress in 2018, we have the potential for 5 bands every 3 to 5 day revisit with a 70-meter resolution. And at this resolution, especially if we sharpen the data to 30 meters in the urban environment, we can really start being able to discriminate these finer scale details over urban areas. For example, differences between golf courses, cemeteries, large industrial roofs. And then we also fly HITESS, which is our airborne hyperspectral imager. And depending on the altitude, we get about a 1 to 10 meter resolution. And with HITESS, we can really now drill down to kind of the street level temperature scale, where we can determine differences between individual trees, roads, and individual roofs. And this data is really important to us. It's almost our secret sauce, if you will, for training our sharpening algorithms, which is really critical in these urban areas. With SPG coming up in 2027, we'll have enhanced capabilities with an additional band. So we'll have 6 thermal bands and also 2 mid-infrared bands to get more at the hot targets every 3 days and at 60-meter resolution, similar to EcoStress. And if you look at the historical and the future multispectral program of record, you can see that over the last 20 years, we really only had ASTER and EcoStress.
And now in the 2028-2030 timeframe, we could have up to 4 high-resolution thermal sensors, which is a really, really exciting time for thermal imaging science and applications, especially in the urban areas. So traditionally, the 2-meter air temperature has been used primarily to convey urban heat extremes over continental and sort of regional scales. Here's an example of the extreme heat wave last year in India that lasted almost a month, showing the Aero 5 temperatures. But it's really only when we get down to the land surface temperature scales, such as ecostress, such as this example over the northern parts of Delhi, where we can really see this fine scale structure detail in urban heat islands. So you can see these urban villages here interspersed among agricultural regions that are almost 15 degrees hotter than the surrounding areas. And so we think that the typical temperatures reported in these regions are a lot lower than what actual urban villages are experiencing. And then with EcoStress, we can now sharpen the data within the city and go in and actually pinpoint specific areas and types of urban surfaces that are emitting and the hottest during the nighttime. For example, in this case, it was the compact, low-rise concrete settlements that had the hottest temperatures due to their higher thermal mass. Staying with India, India has some of the fastest growing cities currently. This is an example of one of these cities in Lucknow, India. And what I'm showing here is changes in impervious fraction from Landsat over the last 10 years and corresponding changes in the VIIRS 375 meter LST. This is another product that we use. And so we see 2 things here. We can see increases in temperature in the inner core of the city due to densification. And then we also see the sort of temperature expanding outwards from the city due to urban sprawl in these sort of peripheral areas. And they think this is due to just poor housing management, where a lot of the immigrants end up living on the outskirts of the city where land and accommodations are a lot cheaper. But again, if we zoom in with EcoStress in this area of this sort of hotspot in the southern end of the city, we can now go in with our 30-meter data and identify exactly which neighborhoods in this area are the hottest. In this case, it is these very dense, sort of congested residential areas just north of the airport. So I couldn't help showing a nice image of Rome. This is from EcoStress during another heatwave event last year in July. This is I believe this was a nighttime event. So you can really see the urban heat island really nicely. And we do a little bit of manicuring here. So this is sharpened data, removes some of the noise, and then we also overlay it on a background Google image so that we can kind of see what's going on in the background with the land cover as well. And then if we zoom into this area here where we are in Frascati right now, we can actually see sort of this fine scale variability and the hotter urban concrete surfaces that are about 10 degrees hotter than the surrounding rural areas. So other than the pretty images, how do we make the data more useful from a societal perspective? So this is a nice study that we did in Los Angeles where we looked at these redlining districts. Now, the redlining was a tactic employed in the 1930s and 1940s where communities were segregated according to their desirability to live in. So, for example, these red areas were less desirable to live in. Mortgages were more difficult to obtain. Usually people of color were living here. So you can see sort of very congested sort of concrete, low-rise buildings with not much vegetation. And then the green areas were considered desirable to live in. And so a lot more tree cover, sort of much more cooler areas. And so what we did was we looked at EcoStress data. We took an average summertime temperature during 2020, and we classified those temperatures according to 3 different zones within these red line districts. And what we see, not surprisingly, is that some of these areas are almost 15 degrees warmer than some of the more greener red-lined areas. And so this is interesting because policies employed back, more than 100 years ago are still persisting to this day and resulting in inequality in terms of urban heat. So what can we do about this? Well, this is a nice example showing how Streets LA, funded by the city back in 2017, in a pilot program, they were funded to paint a couple of the streets in the San Fernando Valley with this cool paint emulsion called Cool Seal. And it's a kind of a grayish looking paint. It has higher reflective qualities than typical asphalt, and so it results in quite a significant cooling. And so when we looked at EcoStress data over one of these areas, we saw this very distinctive arc of cooler temperatures that coincided really nicely with this Stephanie Drive and surrounding streets that were painted in this area. And so we saw about a 2 to 3 degree cooling from both day and night data with pixels overlaid over these streets. And so Greg Sparks, who I've worked with quite a lot, he was the CEO at the time, he was very excited with this image, and he took it to the state and showed the state, and they gave him another $4 million, called it his $4 million image. He then got another $2 million to plant shade trees in some of the disadvantaged communities, and then another $2 million from the government in 2022-23. So he now calls it his $8 million image. So it's just a great example of using EcoStress not only to quantify these mitigation efforts, but also to use it to advocate for more money to reduce heat and improve the quality of life in these areas. This is also a very nice study from our colleagues at Caltech. What they did was they took EcoStress LST, median household income in the Los Angeles County area, and also Landsat NDVI. And what they found was a strong negative correlation with land surface temperature decreasing for these sort of more wealthier affluent communities that are also much greener, as you can see by the colors of the points in this image. And so you can actually quantify and say that there's about 3 degrees of cooling for every $50,000 of household income increase. And so, you know, while these relationships may sound intuitive, it's for the first time we can actually put actual degree metrics on some of these relationships. And this is important because, you know, every degree really matters when it comes to human health. So if we look at the number of emergency room visits per day during these heat wave periods, and we classify them according to typical hypothermia conditions, heat cramps, heat stroke, we see a very strong increase in the number of ER visits as in these more disadvantaged, poorer communities that have these much warmer temperatures. And there are also these other underlying issues that are often overlooked, such as mental health, cognitive function, which really start becoming more apparent above about 30 degrees Celsius. And in fact, if you look at the NOAA National Hazard Statistics, it's heat that results in by far more deaths than any other natural disaster in the US. In fact, if you add up all the deaths for 2021, they add up to more deaths than any other natural disaster combined. And this is true if you look at both 10-year and also 30-year averages. So I'm trying to try and end off on a slightly lighter note, and at least in Europe, you know, you guys have these fountains that you can cool off in during the heat wave periods. In the US, we don't have many fountains. So I'll end there. Thank you.
Thank you. Any question? Microphone, please.
So I have a question. Do you know maybe how many streets were painted during the Street LA project with $8 million?
Yes, I can tell you down to the detail of exactly which streets, exactly which time, and I have a whole...
in general.
In general, like the total amount? That's really hard to say in terms of giving an actual number. Oh, okay. So they started on individual streets, and then they started with what they called their sort of residential cooling program. So they were painting entire suburban areas, and mostly in these disadvantaged communities in Southeast LA that were experiencing most of the heat. And so, you know, I'd really love someone to go in there and look more at the EcoStress and high-test data, which we have before and after the street paintings, and go in there and take this result a step further, which would be really great.
Okay.
I have a question here to Stephanie Drive. So do you know how much does painting the street on reflective paint contribute to decreasing the air temperature, not the land surface temperature, but air temperature?
Yeah, that's a really good question, which they were trying to answer at some point. But what they found was with a thermal radio, so they had like a little gizmo where they would drive a little vehicle across the street and take gradients of the air temperature with just a simple thermocouple. And they found about a 10-degree gradient between the asphalt and the painted street on a very, very hot day. So on a kind of a normal cool day, there wasn't much of a difference, but that difference ramped up on the very hot days. So about 10 degrees.
10 degrees Fahrenheit?
Yes.
Okay.
So what is that in?
Okay,
seven,
sorry,
eight?
thank you. We move to the next presentation. Laure Roupiot, the title is Combining Use of Dart and Solent Microclimate to Investigate the Impact of Urban Surface Characteristics on LST Estimation.
Yeah, thank you. It's a long title. The work presented here, it's a combined work of 3 teams, ONERA, CESBio, and CEREMA. It's really a work that we started recently, so I will show you more proof of concept with really preliminary results. But the idea after is to have a tool that will really allow to investigate in depth the LST retrieval, what's going on cities to get a better LST estimation. So, I mean, I got a great introduction of how much LST in city is useful, so I won't go more into detail into that. So now we are a bit limited with the resolution, temporal and spatial we have, but with the upcoming missions, we will have really an unprecedented investigation of the urban climate. But to do so, we need accurate and spatially comparable LST over cities, because we will have different acquisition time. I mean, the time should be more or less the same, but different angles, different configuration, urban configuration, different urban forms, many different things that we have to take into consideration to be able to compare the LST we derive from the data. And estimating LST in urban area, it's still a big, big challenge because of the surface heterogeneity. We have very large variety of emissivity and artificial material. We have a 3D structure with canyon and everything. So it's make it really complex. For now, most of the products with LST is done assuming flat surface. So of course, in city, it's a bit complicated. So the question we have to answer is which surface parameter should we consider in our retrieval algorithm over cities? Shall we take a sky view factor? Shall we take the building height? It's really difficult to answer. And also, what are the uncertainty in our methodological assumption? How reliable are the LST we derive? And what are the unknown? Because surface property, if we need emissivity, we will never get like the really, really high emissivity of all the city really detailed. I mean, it's really difficult to get. So if we do assumption, how wrong we are. And to answer this question, we need detailed modeling of 3D radiative process. So to answer that question, we decide to investigate the impact of urban surface on LST with modeling approach. And to do that, we combine DART and Solent model. So first, before to introduce you why to change those 2 models and what we can do with it, I will just give you a brief overview of what are those 2 models. So DART, you already saw that name several times in presentation before. So it's a radiative transfer model that allows to simulate remote sensing observation and radiative budget of urban and natural landscape. I mean, the presentation I will give of DART is really, really short, and it's really far bigger and broader than I would say, but it's to give you some small information. So it's developed at CESBio. And for now, it's a team of 10 persons. It's freely available under licenses from Toulouse 3. It's a huge code with a lot of C++ lines. And it has a graphical user interface that allows to use it quite easily. And on the right, you have an example of images that can be simulated with DART. So we use it, for example, when we prepare missions, when we don't have the satellite images yet, or to analyze the impact of viewing angles or many things. And here you have a web page where you can have more information. So basically, as input, you give some acquisition configuration, like satellite, plane, or other location, a date, a send direction, sensor characteristic. Basically, you can do more or less everything you want. You give some optical and structure database, so you describe your atmosphere, if you want to have one. You describe your surface, and you also give the 3D geometry of the scene. So for us, will be the city. And all these inputs go into different modules that process them and give them into Dart that can give as outputs some remote sensing images for the configuration you provided. As I say, it does far more things, but I will stop there for now. So the second model is Solène Microclimate, which is maybe a little bit less known. So it's a set of urban microclimate simulation tool, and it's used for modeling mostly at neighboring scale. It's used for urban planning and looking at the impact of urban planning on urban heat island effect, thermal comfort, energy consumptions, and a lot of other things. It has been developed at Creno, and now it's based at Cerema. And you can have also a web page for more information. I guess it's in French, maybe in English, I don't know. And here you have an example of the outputs of this model. It simulates air temperature, surface temperature for a district. This was a simulation run from the future Paris Olympic Village to see what will be the impact and how the people will feel in there. So, as I said, it's a urban microclimate simulation tool. It couples a thermoradiative model for surface temperature calculation and a CFD for airflow calculation. As input, you provide real or future weather file, depending if you want to study a real condition or future like it has been done in the Olympic Village. You provide a 3D scene as well, and the thermal and the optical properties of the material. And it's processed in the different module, the radiative module. You can add vegetation or water information, airflow, thermal model, and you get as output the LST, the air temperature, district comfort indicators, different things. And inside the building, it's less of interest for us, but I want to mention it. You can have wall temperature, air temperature, or energy needs. I won't talk more about air temperature, but this is also a model we want to use to bridge the gap between LST and air temperature when we study urban comfort or urban climate. But it's not the topic of this presentation. So if we resume, both models work in 3D. They work in 3D detailed urban landscape. Dart provides 3D high spectral resolution radiation transfer and allows to simulate remote sensing observation. But it has no thermal model, so you have to provide LST as input. And in urban area can be complicated to say this wall is this temperature, this roof is this temperature. To have coherent, physically distribute LST can be complicated. And Solène Microclimate provides a complete 3D energy balance, so compute LST at the metric scale over the whole mockup, and air temperature, as I said, as a spare information. But it's a simplified radiative budget in two broadbands, in solar and in the thermal infrared. So if you want to simulate a satellite with particular band, you cannot simulate remote sensing observation. So then we came to the idea to say, okay, why not to chain Dart and Solène to generate thermal infrared images, but with a physically based LST distribution into the scene. So then we can study more this detailed radiative exchange in the canopy and what we will measure from the satellite point of view. So basically, this chaining has to assure coherence between the two models. We can just run Solène, take the LST, put them in Dart. Won't work that much. We have to be sure, of course, it's the same date and location of simulation, that the mockup, the 3D, is exactly the same, that the material properties that we use, the optical one, are coherent, and that we have the same atmospheric radiative forcing. So what we do, we take simulation, we build up simulation in both models, assuring it's the same ephemerid and location. In Dart, we can define spectral band we're interested in. We take surface properties from Dart because these spectral, they are detailed. Then we aggregate it and we put them into Solène to be coherent. And we build the 3D mockup in Solène because we start from there. Dart provides also the atmospheric irradiance because it has this atmospheric module. Then providing the optical properties and the atmosphere to Solène with the 3D mockup, it computes the 3D LST distribution. Then this LST, we provide it back to Dart that compute the corresponding thermal infrared images. So this was the proof of concept. It's a really basic, simple 3D mockup, but we wanted to know if it works before to do more complicated analysis. So we did a small geometry, two simple buildings facing each other. We give optical properties to the roof, to the wall, and to the ground. Into Solène, we compute the energy budget simulation. It's the LST you see in the middle images. And then we gave that into Dart, and we computed the radiative transfer and image simulation for the 4 Trishna bands. This is just an example, and it's top of atmosphere radiance output of Dart. So this is just a simple run to test that everything we wanted is working. Okay. and some preliminary results, we build up a more complex mock-up to say, okay, if you want to study a full district, this is the Strasbourg district around the cathedral, for people who know that area. So we build the mock-up, we put it into Solène to compute the LST, and then we compute brightness temperature at different view zenith angle with DART, just to see. And this we already see on those images that depending on the view angle, you will have a very, very different temperature if you aggregate it. So at the, for example, this is at 1 meter scale, but if you aggregate it like at 40 or 50, depending on the view angle, you will have really different temperature. So this is a tool that will allow to look at those effects, among other things. So to conclude, this chaining will allow to investigate the impact of urban surface heterogeneity and 3D structure on LST, based on detailed DART simulation of radiative exchange in the urban canopy for any sensor configuration, and physically based LST from Solène. And what we will do is that we want to work to analyze the LST we will retrieve for the at the scale of the future satellite missions that you saw there. So the idea is to improve the urban LST, taking into account the adjacency effect, the cavity effect, or any other effect that the surface can have on the result. Evaluate the uncertainty due to unknown optical properties, local LST variation, methodology assumption, to provide as well as an LST to say, okay, the LST you provide you, it's credible to 1K, 2K, 3K, which sometimes we don't know. And finally, to investigate directional effect to generate comparable products among missions that can be acquired at different viewing angles. And it's the last example, the last figure, like the district I showed you on the previous slide. If we did an average over the whole scene, so we have one brightness temperature value, and it has been computed for view zenith angle between 0 and 60, and view azimuth between 0 and 360. And we can see that, 60 of view zenith, it's pretty high, but still we have a difference of 10 degrees between the nadir and the 60-degree view angle. So we need to study that. This is at 1 meter resolution. For sure, at 50 or 60, we have other results, but we can expect an impact, so we have to study that further. Thank you.
Any question?
Have you done any direct comparisons of some airborne data with that specific city location to see how DART compares with the airborne data?
DART has been validated several times in other projects, so I didn't do DART's validation for now, but later on we will use also airborne data and other. For now, we're just the concept of chaining, but both model DART and Solène have been validated separately for other studies, and now that it's running and that I have some output, the next step will be to compare with real data, but not yet. It's really, really fresh, brand new results.
Yeah, it's fantastic. But having an actual area that you can fly over, where you built the model for, I think is really interesting.
Yeah, we have this data acquired over Toulouse in 2021. So it will be maybe we can build a district over Toulouse, because building the mock-up takes some time. I had this one from Strasbourg, so for the result I took it. But the idea is, do it on Toulouse or maybe Los Angeles if you have some mock-up as well, or because you can do them on SketchUp and adapt them or others, so it's pretty easy. Some city already have mock-ups, so maybe it's no point. So. I really wanted to show this tool because I think it can interest a lot of people also to use it. Both software are free, and so.
We should ask Lara to do LA for us for the Trishna campaign next year. Yeah.
Thank you.
All right, next up we have Ana Oliveira. Her title is an urban energy-based balance-guided machine learning approach for synthetic nocturnal surface urban heat island prediction with an example in Naples.
Hi everyone. My name is Ana Oliveira, as presented. I come from the Plus Atlantic Collab. It's a small and young research institute in Portugal, and we are targeting technology and research transfer for the society. And considering this introduction Actually, my background is a bit different from most people in this room. I'm an architect. I have worked in the industry for more than 5 years as an urban planner and an architect, and I got slowly introduced to the remote sensing and thermal imagery afterwards. A first acquaintance with this was back in 2018 or 2019, actually, here at ESRIN for the GREASE meeting. And the reason I came to this community was because I wanted to do something better than what I was actually doing while working as an architect. So what drew me to this was that I wanted to produce something with my work that was meaningful for the society, especially considering that in Portugal, as in Italy and other southern and western boundary countries in the mid-latitudes, are more exposed to heat waves. We already seen some examples of impacts in terms of health, but we also know that, for instance, in Portugal, Italy, Spain, and Athens, and Greece, we have an aging population. So you have a coupling effect of how the climate change is exposing these people to hazardous conditions. And we are also suffering from some difficulties in terms of adaptation because it requires some investment from the public authorities, but they often lag to respond because they cannot see the meaning of the advanced response in terms of getting some money and value back, considering the political drivers, let's say. So considering this, during my PhD thesis, which is half of what I'm going to present now, I draw some of my own requirements as a user, from a perspective of the user. And what I wanted to do was to produce something that was computationally efficient. So I looked into machine learning models, which are less demanding in terms of computational effort. I also looked at scalability because it was useful for me to produce something that I could replicate in other cities that have the same constraints and the same requirements as myself. And I saw this from the community of urban planners and architects I work with across boundaries. On the other hand, I also wanted to go for an open science approach, so something that is replicable, low cost, and easy to deploy elsewhere, so that I could compensate for the difficulties in having societal adoption. So going for this, the first trial was to define what could be the areas of interest. I've been using an index to detect heat waves that is based actually in Australian research, and it uses a quadratic model to disclose heat waves from non-heat wave days. And the reason they use this is because it has been proved as a reliable indicator of human mortality and morbidity. Considering this, I have also developed an indicator of vulnerability by multiplying to the log scale normalization of elderly population in Europe to find out which cities are more exposed. From this onwards, I looked into the cities that were comparable to Lisbon, and in Lisbon we have a special situation in terms of geography. So it's a coastal and estuary city, which means that is subject to the ocean breezes and land breezes, and this is quite a different scenario when you are comparing, say, with Paris or even Rome in some aspects, because you are surrounded by the ocean, and this affects the satellite imagery as well as the air temperature. So what I was targeting was actually the urban heat island effect in itself, and how I could design better spaces to respond and mitigate this effect. But as we can see from these plots, and these plots are not mine, I took them from the sources cited below, there is a problem with satellite imagery that I had at the time. So back then, eco-stress imagery was only starting to become available. I didn't use it back then, but I did use Landsat. And Landsat, in my target areas of interest, overpasses during the mid-morning. This means that there is a coincidence in terms of air temperature, and this means that if I'm targeting urban thermal comfort, which responds to air temperature and not surface temperature, I'm using the wrong thermal data for that, at least in the landscape that I'm working in, which is Mediterranean cities, where the outskirts of the city are quite dry, and hence they are very hot during the daytime. So this first part relates to a case study in Naples. So what you can see from the left-hand side, hand side is the local climate zones maps produced from Urban Atlas Open Data. These are replicable, and the toolbox is published. And on the right-hand side, you can see diurnal land surface temperature during a heat wave day from Landsat 8. Of course, if we compare the urban areas, which are the red ones, with the thermal signature, you cannot disclose the city whatsoever because we are during the summer, we do not have forestry outside, and this is also a coastal area, so you suffer here from several co-founder effects that hinder you from finding a surface urban tiling during the day. But then, if you look at hourly data from SEVERI and geostationary satellites, and if you look into the nocturnal imagery, you can see the urban tiling during the night, which is something that you expect as the signature of the artificialization. And this has to do with the lag between the thermal gains and storage during the day that is re-emitted during the night to the atmosphere. But we do not have Landsat imageries during the night. So this was my first challenge, let's say. So I did find out in the Landsat repository a nocturnal imagery. This is quite rare, but I used it to train a spatial prediction model. This spatial prediction model actually is relying on the energy fluxes computed from the optical imagery from the same day, but during the day. So what I did was try to reverse engineer the energy cycle, compute all the flux components, and as you can see from the pictures here, and this is the latent heat flux, and here is the storage one, which is also quite interesting. You can see how the energy incoming from the sun, considering these models, and these models were applied by me but not developed by me, they have a very good spatial correlation with what is the urban tiling during the night. So this agrees with the literature that says that what we are storing during the day, it's re-emitted during the night, and it's this nocturnal imagery that should be used as a proxy for human exposure. So actually, these are some plots of the daily cycles in which you can see definitely how the fluxes are different in terms of being urban versus a rural city, location, in which you see that the storage heat flux is much greater in artificial land cover. But the idea was to put all of this together in a random forest machine learning model, and using the hourly SEVERI data as also a predictor to downscale the Landsat nocturnal imagery and replicate as a synthetic image. And the results were quite good. We got a very good model that specially predicts the Landsat imagery or replicates the Landsat imagery with less than 0.1 Kelvin and with a huge R squared. But getting to this point, I was like, okay, so I can replicate the Landsat imagery, but there is no more nocturnal imagery in the repository, and just predicting spatially does not do much to help anyone. So I tried to approach the problem differently. And this is what we have been doing at Plus Atlantic more recently. So in Lisbon, we have very few air stations, atmospheric stations, but we do have, as in most cities, if you look for it, many NetAtmos stations. This is a company that provides low-cost devices, and you can access the data from citizens via API. So what we did was gather all this citizen data. We trialed that to distinguish what are outliers, because often citizens do not know how to locate a device properly. We took out the outliers, and we used numerical models together with satellite imagery to replicate what is the thermal signal from the city. And this, in addition, with landscape effects such as the topographic exposure and shelter effect from the prevailing wind, we were able to downscale the near-surface air temperature up to a metric scale. And now we can disclose which neighborhoods are warmer during the day on an hourly basis and how much green space we should have. This model is currently operational. This is not a numerical prediction model, it's a machine learning one, but relies on a numerical prediction model. And basically what we are doing is a downscaling exercise based on non-understanding in terms of relationships. And what we intend to do going forward is also to take the tool a step further for the local urban planners to do what I wanted to do like 10 years ago, which was to produce scenarios and see if I move this neighborhood and introduce more green infrastructure, what would be the relative impact in terms of air temperature and thermal comfort. Thank you.
We have time for a question or two. Kimberly?
I just wanted to share that I'm very impressed. I thought your multidisciplinary approach was excellent, and I appreciated your background story. Really good science communication.
Thank you so much.
We move to the next presentation by Cuckoo Sara. The title is a study on the diurnal land surface temperature cycle during a warmer and cooler year using high spatial resolution land surface temperature data.
So, hello everyone. So, I'm Cuckoo Sara. I'm a PhD student at Indian Institute of Technology, Bombay. Sorry, the slides are gone way beyond. Okay. So today I'm going to present on the topic, the study on diurnal land surface temperature cycle during a warmer year and a cooler year during using high spatial resolution land surface temperature data. So as Glenn has mentioned before, the human-induced climate change has led to prolonged extreme heat wave events across different regions all over the world. And it has a serious effect on the human health as well as the agricultural production and ecosystem, especially in countries like India, where it is densely populated. So traditionally, air temperature is used for monitoring the onset, severity, and the withdrawal of heat waves. However, it has certain limitations like air temperature is measured 2 meters above the surface. Also, there is limited weather stations available across India. So it is impossible to get very accurate, continuous data. So if we take land surface temperature, many studies have already proved that it can be a better proxy for air temperature because remotely sensed land surface temperature it is available continuously. If we take the polar orbiting satellites, it gives land surface temperature, like MODIS will give land surface temperature 4 times per day, whereas fine resolution sensors like EcoStress, Landsat will give data just 1 time a day. But the thing is it is not necessary that the hotspots, the maximum temperature of a day should occur during the overpass time of these satellites. So it is diurnal, if we take the diurnal land surface temperature, it can be a better indicator it gives a thermal summary of the land surface temperature of different land cover types. So along with land surface temperature, diurnal temperature can be more effective in monitoring the heat waves. So geostationary satellites gives land surface temperature at every 15 minutes or 30 minutes. But the problem here is the coarse resolution of the geostationary satellites. So in our study, we have combined a data downscaling with a diurnal temperature cycle model to predict field scale land surface temperature and the diurnal cycle. So the objective is to study the variation of diurnal land surface temperature parameters for different land cover types during a warmer year and a cooler year. So these are the study areas we have selected. The first one is Bathinda it is a district in Punjab. So the people majorly depend for their livelihood on the agriculture. So the major crop type used here is wheat. And in 2022, if we see, there was a sudden increase in the temperature during the month of March. So that was the maturing period of wheat crop. So due to this sudden increase in heat, temperature, the production suddenly declined. And in fact, in 2022 was the having the lowest wheat production over 2 decades since 2000. And next is the Jalgaon district in Maharashtra. So here also frequent heat waves are reported. So the major land cover types here are built-up lands, croplands, and barren lands, and few patches of other vegetations. So for downscaling, we have used a principal component-based regression method where the MODIS observations, 4 MODIS observations and VARS observations were downscaled from 980 meter to 70 meter using different indices from high-resolution sensors like Landsat. So vegetation indices, built-up indices, then emissivity, topographic data, and backscattering coefficient from Sentinel-1 was used for downscaling the data. And after downscaling these 4 MODIS observations, it was fed into a diurnal temperature model called GOD01, which is a semi-empirical model, which is actually a 5-parameter model. Since we have 4 observations, we kept 1 parameter as fixed, and the 4 parameters were calculated using an optimization technique. And these calculated parameters were fed into the model to fit these 4 MODIS observations. So the data sets used were MODIS, Terra, day and night data, then VARS data, and the Aqua night data. And the fine resolution data sets used were Landsat and Sentinel-1 SRTM data. And all these data were collected for the warmer and cooler year, like identical dates, these data sets were collected. So moving on to the results. So first, in order to identify the warmer and cooler year, we calculated the thermal anomaly maps for the period of 2015 to 2022. So from here, we can see that 2019 is a very warm year. And so for comparison, 2017 was used as cooler year. So these are the disaggregated LSTs at 70 meters. So you can see here that during daytime, in 2019, the pixels were really warm. And also, if you see the nighttime, the urban pixels are warm, indicating urban heat island. And using these 4 observations, downscaled observations, we fitted the diurnal temperature cycle using GOD01 TS model. So these are the diurnal temperature cycle for different land cover types. So if you see barren land, the morning temperature and the afternoon temperatures are pretty high for the year 2019. The blue curve indicates diurnal cycle for 2019, and orange one is for 2017. And if we see the cropland, even though the morning temperature is pretty close for 2017 and 19, the temperature drastically increases during the year 2019, could be due to vegetative stress. And if we see built-up land, the night temperature is pretty high, indicating urban heat island. So these are the anomaly maps prepared for Bathinda district in Punjab. So as I said previously, 2022 was a heat wave year, and all the pixels are very warm here compared to the other years, because it was supposed to be very cool during the month of March, but on the year 2022 is pretty warm. So for comparison, 2022 diurnal cycles were compared with 2020. So if we see here, the figure A is the Landsat 8 LST. And if we see in detail, like the highlighted region, if you see the Modus Terra LST, the final details are missing in the Modus Terra LST, whereas the downscaled LST was able to capture these patterns. And if we take 2 points, P1 and P2, we can see that even though these are two different features, land cover types, the temperature in Modus is exactly the same. And if we take the downscaled LST, we can see that at the point P1, the temperature is pretty higher compared to the Modus LST. So these hotspots are missed in the Modus coarse resolution LST, whereas it can be captured in the downscaled LST. So this is the, that's why high resolution LST is very important for identifying these kind of hotspots, which can be missed in the coarse resolution LSTs. So these are the different diurnal cycle comparisons for different land cover types in the year 2022 and 2020. So here we can see that for all the land cover types, the diurnal, the temperature is drastically higher compared to 2020. So the conclusions are the temperature and duration of heat wave anomalies can vary for different land cover types in the same region. So it is very important to have a high resolution data to analyze the heat waves over a finer detail. And LST can be used as a proxy along with heat stress indexes. It can be used in conjunction with other variables to calculate the heat stress index so that we can use it to monitor and mitigate the heat events. And identifying hotspots and the time at which temperature peaks can help in mitigating the impact of heat waves. So if we see, like in the case of crop, if we can identify what time the temperature is peaking, we can irrigate those crops during that period, so thereby effectively monitoring the heat wave effect over crops during that period. So with this, thank you.
Okay, thank you. Any question? Yes.
Thank you for that really interesting presentation. My question is perhaps a bit of a naive one. Could this potentially be applied to a satellite like Himawari, where you get geostationary data? Because then you would have far more points to fit a far more accurate DCC model. Because I'm a bit wary about fitting such a complex curve to what is essentially only 4 points.
Yeah, actually we were able to fit these curves within an accuracy of 2 to 3 Kelvin. But however, if we can downscale the geostationary data to much finer scale, we can effectively use those diurnal cycle for these studies. In fact, I'm working on downscaling geostationary to these finer scales.
Yeah, I think Sysmanides a couple of years ago published a paper on doing just that. That might be a good place to begin looking.
Okay, thank you.
I have a quick two-part sort of question. I was wondering why you downscaled to 70 meters in particular?
Because while developing that model, like we were comparing it with eco-stress data, so for that convenience, we were using 70 meters.
And your Modus and Veers data, can you tell us which products you are using? The LST, for the Modus and Veers LST products?
Mode 11 daily product I was using.
Okay, and the Veers?
VIRS also VNP 21A1D and 21A1M.
I would just suggest using the Mod 21 and the VNP 21 because they use the same algorithm, so you'd get a more consistent result between the two. Just a suggestion.
Okay, thank you.
Okay, two talks left are on cryosphere studies. So next we have Roberto Colombo, monitoring snow processes and snow density by thermal inertia.
Thank you very much. Okay, good afternoon. I'm going to present a possible new application which make use of surface temperature, basically the thermal inertia, for monitoring snow melt evolution, snowpack evolution, and snow density. This is the outline. I will do a short introduction, and then I will provide you some information related to different experiments that we have done. One is related to the temporal evolution of the snowpack, and the other one is related to the spatial variability. So starting from the beginning, everybody knows that snow is a crucial resource, natural resource. Basically, is the ability to contain fresh water, and basically, the so-called snow water equivalent is which represents the water which is stored into the snowpack, is basically a function of the snow height or the snow depth, which can be theoretically derived from remote sensing, multiplied for the snow density, which is a variable which is still difficult to estimate from a remote sensing perspective, multiplied for the snow cover area within the basin. So basically, snow density is a crucial variable which control conductivity and control inertia of the snowpack. And in this plot, we can see, for example, the empirical regression between the thermal conductivity and the snow density, which allow to estimate conductivity starting from manually measurements of snow density in the field. And basically, snow show unique radiative properties. Reflectance of snow is well known to change according to different parameters. We can see, for example, in this plot where we have the reflectance on the y and the wavelength on the x-axis, and different the different shape of reflectance change according metamorphism, or change according the presence of liquid water content, or as in this case, the reflectance change according the amount of dust which is on the snowpack. On the contrary, in the thermal domain, snow exhibit a behavior like a black body, so emissivity is generally more or less equal to 1 at 11 micrometers, and spectral emissivity is reduced or is affected by changing of the grain size. And this we can see, for example, the behavior of spectral emissivity. So this just to say that albedo and temperature change rapidly in the snowpack, and we believe that thermal inertia can reflect variability of the snowpack evolution, and this is the hypothesis that under this study. So the idea to monitor the snow variability according this parameter. This parameter, basically the so-called snow apparent thermal inertia, is a well-known variable which is monitored since a long time. We start, for example, from the 80 years by using the first NASA Explorer mission, which was the heat capacity mapping missions. And there were a lot of studies demonstrating the possibility to exploit thermal inertia for planetary geology, for lithological mapping, and mainly for evaluating the water content into the soil. But surprisingly, was never tested on snow density. So we can derive the so-called apparent thermal inertia by solution of the thermal diffusion equation, and is a function of the co-albedo, so 1 minus albedo, and basically of the difference of surface temperature into different times, mainly in the morning time at midday where the maximum temperature occur, and during night time, for example, 6 o'clock in the morning. Then we also to keep into account the incoming shortwave radiation and, of course, the phase differences. And in this context, the main objective of these studies was to evaluate the thermal inertia for monitoring snow melt processes at local scale in the temporal domain, and to evaluate new perspectives to infer snow density from space. So we selected 2 different areas. For the temporal analysis, we used the experimental site located at the Tornion in the northern part of the alpine area in the Italian side. It's a well-equipped, fully equipped experimental site. There are ICOS towers plus different instruments for measuring a lot of vegetation and snow parameters. And we exploited a long time series starting from 2012 up to 2017, so we have a lot of temporal data. While for the spatial analysis, we investigated different catchments. This is, for example, the Cervino Mountains, and this is the mountainous catchment. You can see here the valley and the region, the border, and we had a lot of information in this area. Okay, regarding the methods that we have used for the temporal analysis, we parameterized the Crocus model, which is an energy and mass balance model, which allows to estimate different snowpack parameters, like the output variable listed here, starting from the data collected from the meteorological station. And regarding the spatial analysis, we used an hybrid approach which makes use of Landsat 8 data to estimate surface temperature during the daytime, and Landsat data for estimating albedo during daytime. Instead, for the nighttime surface temperature, we exploited a proxy, which is the so-called dew point temperature, because there was not available any kind of image at this kind of spatial resolution. So we can compute the temperature differences and the apparent thermal inertia, and by using the snow density manual measurements, we just developed an empirical regression model to evaluate if there is an agreement between these 2 variables. Here we can see some results according to the temporal analysis. This is just an example of the output of the modeled data by Crocus. You can see, for example, this is the seasonal time. This is, for example, the behavior of the snow depth and the snow water equivalent. Here you can see how the surface temperature change across the season, how is the density, up to arrive to the variability of the thermal inertia along the profile and across the season. And if we consider an idealized sequence, what we have found is that the thermal inertia exhibit low values during the accumulation period, where we have fresh and dry snow, and start to increase with the beginning of the warming phase, which state the start of the melting season, and then it dents according the presence of liquid water content on surface, and after, for example, snowfall, the thermal inertia decrease and proceed with the temporal evolution. And by using modeled data, we fitted this kind of relationship between the mean snow density of the whole snowpack, but also the upper layer, considering the first 30 centimeters. And we found this nonlinear relationship, which basically allow, if we invert this relation, to estimate snow density starting from the remote sensing observation of thermal inertia. And regarding the spatial analysis, just to show briefly the results that we get in terms of validation for Landsat data. So this is quite good results, encouraging, because we can see the surface temperature of Landsat data plotted versus surface temperature measured at the different automatic weather stations at 11:30, and we can see that there is a good agreement beside this point, but the snow was quite patchy at the time. And instead, the bottleneck of this study that we did, and is useful, this slide, to underline the importance not only of the revisit time or the high spatial resolution for the new land surface emission, but also for having nighttime image. Because when we plot the dew point temperature versus the surface temperature at the automatic meteorological station, we detect this kind of scatter plot, and this, of course, introduces uncertainty. So it's something that can be overcome by using nighttime temperature. So moving to the some maps, this is the behavior of the difference in surface temperature in January, so in winter period. We can see that the delta is quite large. We can see that on the ridge there is about 30 degrees of differences between morning and midday. And when we move to the May, so a period like now, where the snow is almost wet, we can see that the difference of surface temperature strongly decrease, and there is also a spatial variability of the surface of this difference in surface temperature. And this is the maps of apparent thermal inertia, and we can see basically, looking at this map, that apparent thermal inertia may help to infer dry and wet snow. For example, in the upper part of the catchment, we can see low values of apparent thermal inertia, while at the bottom part of the catchment, we can see the highest values of apparent thermal inertia. So there is a variability that indeed reflects variability of the snowpack. And this is the nonlinear regression that we found when we plot measured surface density versus the thermal inertia. We can found by a validation approach that we can reasonably estimate the snow density with a root mean square error in cross validation around 80 kilogram per cubic meters, which is more or less in the same range that we found when we measure manual density during the snow campaign. So this is the final map that maybe we can provide as a product in the future. So the snow density from space, we can observe a strong variability in space and time. I don't want to go in detail, but there is a range of value which is really reasonable, and the variability is across, is related to snow conditions and is related to the topography, to the morphology. And in spring, for example, when both wet, dry and dry snow coexist, we can see that we can we can try to define a threshold to set up a value which we can say, okay, before this value maybe we are in dry snow, and after this threshold we are in wet snow. And this could be comparable to something that the people working in the radar community are doing. So maybe we can try also to compare the results that we can get from different part of the electromagnetic spectrum. So basically, to conclude, I would say that these results provide evidence that the snow thermal inertia is really sensible to the snow melt phases, and snowpack, as we have seen in the maps, exhibit spatial and temporal variability of inertia, distinguishing between fresh snow and wet snow. And we can reasonably use an empirical regression model, still empirical, to estimate snow density with a reasonable error and uncertainty about 10 to 15%. Although there is a strong potential to improve this study, since there are a lot of uncertainty derived in the input parameters that we can improve, of course. And however, this study can be considered a first attempt to the exploitation of thermal inertia for snow monitoring, and basically may help for a new application in the study of the cryosphere. And I would say that a new perspective can be provided by the new generation of surface temperature missions like LSTM, SBG, or Trishna, because we can benefit from the combined temporal resolution for increasing the spatial resolution and for getting nighttime images, which really help in mountainous landscape to exactly understand the physical process which occur at this scale. An important point is that we think that we should consider a proper data harmonization for managing in a proper way all these sources of data. So not only in terms of a radiometrical point of view, but also in terms of geolocation point of view. So just that's all. Thank you.
One question from Jeff.
So you mentioned that the emissivity changed with grain size. Now, the original multispectral thermal instruments for geology, for defining minerals, and we used to call decorrelation stretch for emissivity. Do you think there's enough change that can be detected with current instrumentation? And is it worth pursuing?
I don't know really. Are you asking if it is possible to exploit the spectral emissivity to move toward grain size? I don't know, because this is something that is possible to do with a certain accuracy by using the reflectance domain. If we have the hyperspectral shape of reflectance, we can infer grain size. So I don't know if in the future maybe combining the absorption feature in the reflectance domain plus the spectral emissivity in the thermal domain, we can benefit and maybe we can improve the estimation of snow grain size. But in principle, really, I don't know.
Okay, thank you.
Well, I can say that we've demonstrated it with Mod 21 emissivity data over Greenland, looking at different snow melt phases between 11 and 12 micron bands. I was wondering, do you plan to use eco-stress data at all, day-night pairs, to determine
I tried, but it's difficult to find a couple of morning and midday data.
Close in time.
Yes, because there are a rapid change. Snow is really rapid. So if you consider a nighttime image on Monday, you cannot take on Friday the diurnal image.
Okay.
Because you don't know what happens in the middle.
Yeah.
Basically, the best requirement should be 1 day of temporal revisit time.
Which we'll have soon, maybe?
Yeah, exactly. It's
All
cross
right.
the thing.
All right, thank you. It's
Okay.
a good example of cryospheric studies with thermal.
Thanks.
Right.
Okay, thank you. We move to the last presentation by Sara Arioli towards a better understanding of snow surface temperature variability in mountain regions.
Okay, hi everybody, thanks for making it to the last presentation of the day. My name is Sara Arioli, I'm a PhD student at the IGE lab in Grenoble and in France. And I'm gonna talk about surface temperature of snow in complex terrain, so in mountain areas. And this is a collaboration, is a work that we do in collaboration with the CESB lab in Toulouse, also in France, in the context of the preparation of the Trishna mission. So, very quickly, as Roberto already said, the surface temperature is a very relevant parameter for snow because temperature is actually the parameter that drives mainly the evolution of snow from fresh snow to aged snow. So, we all know the snow grains change, the snow changes, and so the temperature drives this change, and with this change of the microstructure of snow, also there is a change of the optical properties of snow, so it is really important. Also, as for other surfaces, the snow surface temperature is the result of the closure of the energy budget. And as we are in complex terrain, the energy budget gets way more complicated, and for this reason, the distribution of the surface temperature of snow is very also complicated, and there is a strong variability of the surface temperature over small horizontal scales. So I will quickly go over all the perspectives that we're looking into. I will mainly talk about observations today, but I will also quickly go through modeling and data simulation. I would like to start with data simulation, just quickly citing work that is being conducted at CESBio by our colleagues. In particular, what I want to highlight is that in this paper that you can find at the QR, Esteban Alonso made an observing system simulation experiment, meaning that he generated some synthetic surface temperature data that he has simulated to compute the snow water equivalent, so the amount of water that is contained into the snowpack. And what is relevant to the Trishna mission, as well as LSTM and SBG, is the fact that he simulated the assimilation considering a revisit time of satellite of 16 days, so as for Landsat, and of 3 days as for Trishna, and he actually found an important improvement in the simulations of snow water equivalent, which is an essential climate variable. Also, very quickly, the modeling part. We developed the model at IGE, which is a RAFSAT model, which computes the surface temperature of snow by closure on the energy budget over complex terrain. So we use the decometric resolution to represent the topography, but this also represents the resolution of the sensors of the future thermal missions. And also it has a very accurate computation of the radiative fluxes over complex terrain thanks to a ray tracing model. You can find references of a paper about the model on the QR code. Otherwise, I invite you to go see the poster 258, which is presented by Ghislain Picard. Okay, and now back to observations. Snow covers a large area of the northern hemisphere in winter. It occupies usually remote places, so of course it makes sense to go looking into satellite data. It's a great tool. The problem is that when we look into complex terrain, we have a resolution problem, because the resolution is usually relatively coarse with respect to the topography. We have the fact that the contribution of the atmosphere is way more complex over mountain areas. And then we have some problems that are related to snow in particular, the fact that there are emissivity variations, both with the observation angles and also with the grain type, as was cited before. And also the revisit time combined with the clouds sometimes can make the information about the snow surface temperature not really informative. So we tried to look into uncooled thermal infrared cameras. Of course, the measurements we can make with these cameras are not as extensive, but still we have an improvement in resolution, both temporal and spatial. With these instruments, we have a reduced atmospheric contribution. We can actually mount it, use it to play and gain insights into the role of emissivity. But this camera is also known to have some instability problems and a dependency on the internal temperature, which is why we decided to use a thermal camera, but also to couple it with radiometers, with the overall goal, of course, to obtain accurate measurements of the snow surface temperature using a TIR camera. So these are the two measurement sites where we have our thermal cameras with the position of the radiometers. I mainly work at the Col de l'Otarie, so I will talk about the Col de l'Otarie for the next slides. But we also have another site in the Pyrenees, the Pic du Midi, and these two sites are complementary with respect to their geographical features. So last year, winter 2021-2022, we installed the camera, we installed our radiometers, we acquired a lot of measurements. This is just to give you an idea of how many measurements of the surface temperature and of some complementary variables we have. It was a very dry winter, so we also have loads of cloudless images, both with Landsat TIRs and EcoStress to compare to. And now into the data. This is a small time series that compares the data measured with the TIR camera and the TIR radiometer. First thing that we notice is there is a relatively big cold bias. This cold bias is around 2 degrees. So the camera measures the colder temperature. We know that this bias is actually probably even bigger because here we didn't, this is raw data, so we didn't correct for the fact that the camera has a window and the transmission is less than 1. So this bias is pretty much even higher. But we also notice some other things. First of all, you can see in the green areas that our radiometers are not very accurate. Indeed, those 2 days that I highlighted are days of surface melt, and our radiometers measure the temperatures above 0 degrees, which of course doesn't really make sense for snow. And also in the gray area, you can see some noise in the measurement of the camera, which is not reproduced by the radiometers, and this is because that noise is not due to actual changes of the surface temperature, but to instability of the camera due to big changes in its internal temperature that, as you can see, was varying way too much. This is just a quick comparison with a Landsat 9 LST, so level 2 image, on a day of surface melt. So here we expect the whole surface to be at 0 degrees. Landsat has some 0 degrees pixels and some warmer ones on the side. We find again with our camera a 2 degrees bias, cold bias, which confirms overall that, yeah, we really had a significant bias last year over our data, and yeah, we needed to understand what was going on. So we pointed out some problems. First one was the inaccurate ground truth. For that, we just took our radiometers, replaced them, but by higher quality ones. And then we looked a bit deeper into 2 other problems: the high noise caused by the temperature, internal temperature instability, and the lack of a precise characterization of the window. So for the first problem, so the internal temperature, what we did is that we insulated the camera inside of the box where it was located with its electronic and added a Peltier unit to keep the temperature constant at 15 degrees. We tested this setup in a lab, in a climatic chamber, and actually obtained variations of the internal temperature of the camera below 1 degree for external temperature variations of 25 degrees. So we were quite satisfied with this point. And then we moved on to the camera window. As I said, the camera has a window, and as the transmission of this window is clearly not equal to 1, we needed to understand whether the rest of the emission was coming from the window itself or from a reflection of the sensor or camera emission. So we estimated these parameters using both the window transmission curves, but also doing some tests with a black body and using radiometers on the window directly, and elaborated the camera model. So moving on to this winter's campaign, things changed quite a bit. As you can see, the data has some holes because I filtered out clouds. The spring has been quite cloudy, so I couldn't get a prettier time series, let's say. We still notice that we have some overshoots. You can see them on the warmer temperatures in the green parts, and also some undershoots of the temperature of the camera that are highlighted in pink. We still don't know if this, especially the overshoots, are maybe due to the overheating, and if overall on the 2 phenomena we have an effect of the emissivity, we have an effect of atmosphere. We didn't test this yet, but still on average we are way below a 1 degree bias right now. So we are quite confident in the method and willing to investigate further to reduce the remaining effects. So quickly, conclusion number 1 clearly is the fact that we managed to get measurements of the snow surface temperature with an average bias of less than 1 degree with an uncooled thermal infrared camera. And also, we have right now these 2 years of data. They are very big data sets that we are willing to share with the community. So I'm actually writing a data paper right now, and we will to share this data set soon. For what concerns the perspectives, I think this work is interesting because this data could actually serve as validation, of course, for satellites as Trishna, but also later on LSTM and SBG. This kind of data can also be used to validate models, which is pretty much our plan, and data simulation experiments. Also, we could use this kind of experience, this kind of camera setup to get insights into the role of the atmosphere and the emissivity of the snow cover in complex terrain. And finally, we already elaborated at IGE a setup for a thermal camera like this that we can mount on a drone. So always stabilized in temperature. It's very lightweight, so we can perform drone flights with it. We actually did our first flight with this setup last week. So I'm going to analyze the data in the next few weeks, see how it goes. But yeah, we're quite confident that such an application could interest the community. So thank you, and yeah, if you have any question, let me know. And I just remind you to go see the poster about our model. Thanks.
Any question? No. Thank you.
Jeff, do you want to come up and talk about your upcoming thermal book?
Okay, should have that slide. Okay, good, great. So back in 2004, Dell and I put together a book on thermal remote sensing landscape processes. And with all the advances, it's a good timing to come out with basically a second edition. And this has been in progress for a while, but unfortunately, Dell died several years ago, and everything kind of came to a halt. But we decided to resurrect it. And what's different about this book, it's going to be open source, online, free. And with the advances in technology, the authors can put in tutorials in their chapters and data sets and this sort of thing. And we have ways to keep that updated too. Part of my rationale for this book is that I'm the lead application science for SGB and try and prepare the applications community for the what's to come in the future. So this book was proved to be pretty popular when it came out back then, and I think it's a good time to do this. If you get, I guess I'll advance it. Okay. And this is the outline of the book. It can change. We got flexibility. But you know, one of my objectives here is to the American perspective on it. So this is just some of the chapters and what we're doing on it, and to try to cover about everything. One chapter I didn't have on the new technology and some of the microsats, which is very interesting. That will be added. Okay, so this is just sort of a plug. You can see myself, Simon, Carrie is here, Christine's not. So they'd be happy, just email me and you know, we can work on it. Timeline is, we've got about a year to do the book. So it's kind of short, but I think rather than the traditional way of doing the book where you do the whole book at once and then publish it, we always have chapters that lag behind, so it could take years. So what I think I'll probably do is try to publish the chapters as they've been reviewed and put out. And that way, the graduate students, if they're contributing, they can get a publication out and this sort of thing. So I'm happy to answer any questions, email myself, and I'm really excited about this. I think it'll be a good foundation for thermal remote sensing. Thanks.
Thank you. I invite the 6 speakers for additional questions. You can go. Maybe also you. And some additional questions?
So everyone wants happy hour.
Well, this is also time for recommendations. I want to say a recommendation related with night surface temperature. I think that the potential of night surface temperature is very important. There are a lot of applications, snow, as you saw, and also thermal inertia, urban heat island, frost snow casting, etc. And then my recommendation is we can use, if it is possible for our applications, night surface temperature.
Going once, going twice.
Then
I had a quick question for Anna. I was wondering if there is EcoStress and Aster nocturnal high-resolution thermal data. Do you plan to ever use that, or maybe to even validate your machine learning approach or approaches?
Yes. So that is not something that we have started yet, but definitely it's something that is on our horizon. But because currently I was full-time on my PhD when I did that, and I'm not anymore, so it's more a context of getting the chance to have the opportunity to do that in the scope of ongoing work activities, but yes.
That's great, yeah.
Scientifically speaking, yes.
Okay.
Okay. Well, if there is not more question, we can move to the poster session. Thank you.
Just to remind everybody that tomorrow we start half an hour earlier, so the buses also are leaving a little bit earlier. And with that, please have a glass of wine and enjoy the poster session.